We are very far from having such a deep understanding of planetary evolution at the present time, but we are much closer than would have been thought possible only a few decades ago. Every new set of discoveries raises a host of questions which we were never before wise enough even to ask. I will mention just a few of them. It is now becoming possible to compare the compositions of asteroids with the compositions of meteorites on Earth. See Chapter 15. Asteroids seem to divide neatly into silicate-rich and organic matter-rich objects. One immediate consequence appears to be that the asteroid series is apparently undifferentiated, while the less massive asteroid Vesta is differentiated. But our present understanding is that planetary differentiation occurs above a certain critical mass. Could Vesta be the remnant of a much larger parent body now gone from the solar system? The initial radar glimpse of the craters of Venus shows them to be extremely shallow. Yet there is no liquid water to erode the Venus surface, and the lower atmosphere of Venus seems to be so slow-moving that dust may not be able to fill the craters. Could the source of the filling of the craters of Venus be a slow molasses-like collapse of a very slightly molten surface? The most popular theory on the generation of planetary magnetic fields invokes rotation-driven convection currents in a conducting planetary core. Mercury, which rotates once every 59 days, was expected in this scheme to have no detectable magnetic field. Yet such a field is manifestly there, and a serious reappraisal of theories of planetary magnetism is in order. Only Saturn and Uranus have rings. Why, there is on Mars an exquisite array of longitudinal sand dunes nestling against the interior ramparts of a large eroded crater. There is in the Great Sand Dunes National Monument near Alamosa, Colorado, a very similar set of sand dunes nestling in the curve of the Sangre de Cristo Mountains. The Martian and the terrestrial sand dunes have the same total extent, the same dune-to-dune spacing, and the same dune heights. Yet the Martian atmospheric pressure is 1/200, that on Earth, the winds necessary to initiate the saltation of sand grains are 10 times that for Earth, and the particle-size distribution may be different on the two planets. How, then, can the dune fields produced by wind-blown sand be so similar? What are the sources of the decameter radio emission on Jupiter, each less than 100 kilometers across, fixed on the Jovian surface, which intermittently radiate to space? Mariner 9 observations imply that the winds on Mars at least occasionally exceed half the local speed of sound. Are the winds ever much larger? What is the nature of a transonic meteorology? There are pyramids on Mars about 3 kilometers across at the base and 1 kilometer high. They are unlikely to have been constructed by Martian pharaohs. The rate of sandblasting by wind-transported grains on Mars is at least 10,000 times that on Earth, because of the greater speeds necessary to move particles in the thinner Martian atmosphere. Could the facets of the Martian pyramids have been eroded by millions of years of such sandblasting from more than one prevailing wind direction? The moons in the outer solar system are almost certainly not replicas of our own rather dull satellite. Many of them have such low densities that they must be composed largely of methane, ammonia, or water ices. What will their surfaces look like close up? How will impact craters erode on an icy surface? Might there be volcanoes of solid ammonia with a lava of liquid NH3 trickling down the sides? Why is Io, the innermost large satellite of Jupiter, enveloped in a cloud of gaseous sodium? How does Io help to modulate the synchrotron emission from the Jovian radiation belt in which it lives? Why is one side of Iapetus, a moon of Saturn, 6 times brighter than the other? Because of a particle size difference, a chemical difference. How did such differences become established? Why on Iapetus and nowhere else in the solar system in so symmetrical a way? The gravity of the solar system's largest moon, Titan, is so low and the temperature of its upper atmosphere sufficiently high that hydrogen should escape into space extremely rapidly in a process known as blow-off. But the spectroscopic evidence suggests that there is a substantial quantity of hydrogen on Titan. The atmosphere of Titan is a mystery, and if we go beyond the Saturnian system, we approach a region in the solar system about which we know almost nothing. Our feeble telescopes have not even reliably determined the periods of rotation of Uranus, Neptune, and Pluto, much less the character of their clouds and atmospheres and the nature of their satellite systems. The poet Diane Ackerman of Cornell University writes, "Neptune is elusive as a dappled horse in fog. Pulpy, belted, vapory, frost-bitten, what we know wouldn't fill a lamer's fist." One of the most tantalizing issues that we are just beginning to approach seriously is the question of organic chemistry and biology elsewhere in the solar system. The Martian environment is by no means so hostile as to exclude life, nor do we know enough about the origin and evolution of life to guarantee its presence there or anywhere else. The question of organisms both large and small on Mars is entirely open, even after the Viking missions. The hydrogen-rich atmospheres of places such as Jupiter, Saturn, Uranus, and Titan are in significant respects similar to the atmosphere of the early Earth at the time of the origin of life. From laboratory simulation experiments, we know that organic molecules are produced in high yield under such conditions. In the atmospheres of Jupiter and Saturn, the molecules will be convected to pyrolytic depths, but even there, the steady-state concentration of organic molecules can be significant. In all simulation experiments, the application of energy to such atmospheres produces a brownish polymeric material, which in many significant respects resembles the brownish coloring material in their clouds. Titan may be completely covered with a brownish organic material. It is possible that the next few years will witness major and unexpected discoveries in the infant science of exobiology. The principal means for the continued exploration of the solar system over the next decade or two will surely be unmanned planetary missions. Scientific space vehicles have now been launched successfully to all the planets known to the ancients. There is a range of unapproved proposed missions that have been studied in some detail. See Chapter 16. If most of these missions are actually implemented, it is clear that the present age of planetary exploration will continue brilliantly. But it is by no means clear that these splendid voyages of discovery will be continued, at least by the United States. Only one major planetary mission, the Galileo project to Jupiter, has been approved in the last 7 years, and even it is in jeopardy. Even a preliminary reconnaissance of the entire solar system out to Pluto and a more detailed exploration of a few planets by, for example, Mars rovers and Jupiter entry probes will not solve the fundamental problem of solar system origins. What we need is the discovery of other solar systems. Advances in ground-based and spaceborne techniques in the next 2 decades might be capable of detecting dozens of planetary systems orbiting nearby single stars. Recent observational studies of multiple star systems by Helmut Abt and Saul Levy, both of Kitt Peak National Observatory, suggest that as many as 1/3 of the stars in the sky may have planetary companions. We do not know whether such other planetary systems will be like ours or built on very different principles. We have entered, almost without noticing, an age of exploration and discovery unparalleled since the Renaissance. It seems to me that the practical benefits of comparative planetology for earthbound sciences, the sense of adventure imparted by the exploration of other worlds to a society that has almost lost the opportunity for adventure, the philosophical implications of the search for a cosmic perspective, these are what will, in the long run, mark our time. Centuries hence, when our very real political and social problems may be as remote as the very real problems of the War of the Austrian Succession seem to us, our time may be remembered chiefly for one fact. This was the age when the inhabitants of the earth first made contact with the cosmos around them. Chapter 11. A planet named George. And teach me how. To name the bigger light, and how the less, that burn by day and night. William Shakespeare. The Tempest. Act I, Scene 2. Of course they answer to their names, the gnat remarked carelessly. I never knew them to do it, said Alice. What's the use of their having names, said the gnat, if they won't answer to them? Lewis Carroll through the looking-glass. There is on the moon a small impact crater called Galilee. It is about 9 miles across, roughly the size of the Elizabeth, New Jersey, greater metropolitan area, and is so small that a fair-sized telescope is required to see it at all. Near the center of that side of the moon, which is perpetually turned toward the Earth, is a splendid ancient battered ruin of a crater 115 miles across called Ptolemaeus. It is easily seen with an inexpensive set of field glasses and can even be made out by persons of keen eyesight with the naked eye. Ptolemy, 2nd century AD, was the principal advocate of the view that our planet is immovable and at the center of the universe. He imagined that the sun and the planets circled the Earth once daily, embedded in swift crystalline spheres. Galileo, 1564 to 1642, on the other hand, was a leading supporter of the Copernican view that it is the sun which is at the center of the solar system and that the Earth is one of many planets revolving around it. Moreover, it was Galileo who, by observing the crescent phase of Venus, provided the first convincing observational evidence in favor of the Copernican view. It was Galileo who first called attention to the existence of craters on our natural satellite. Why, then, is crater Ptolemaeus so much more prominent on the Moon than crater Galileo? The convention of naming lunar craters was established by Johannes Hoelke, known by his Latinized name of Hevelius. A brewer and town politician in Danzig, Hevelius devoted a great deal of time to lunar cartography, publishing a famous book, Selenographia, in 1647. Having hand-etched the copper plates used for printing his maps of the telescopic appearance of the Moon, Hevelius was faced with the question of what to name the features depicted. Some proposed naming them after biblical personages, others advocated philosophers and scientists. Hevelius felt that there was no logical connection between the features on the Moon and the patriarchs and prophets of thousands of years earlier, and he was also concerned that there might be substantial controversy about which philosophers and scientists, particularly if they were still alive, to honor. Taking a more prudent course, he named the prominent lunar mountains and valleys after comparable terrestrial features. As a result, we have lunar Apennines, Pyrenees, Caucasus, Juras, and Atlas Mountains, and even an alpine valley. These names are still in use. Galileo's impression was that the dark, flat areas on the Moon were seas, real watery oceans, and that the bright and rougher regions densely studded with craters were continents. These, Maria Latin for seas, were named primarily after states of mind or conditions of nature. Mare Frigoris, the Sea of Cold; Lacus Somnorum, the Lake of Dreams; Mare Crisium, the Sea of Crises; Sinus Iridum, the Bay of Rainbows; Mare Serenitatis, the Sea of Serenity; Oceanus Procellarum, the Ocean of Storms; Mare Nubium, the Sea of Clouds; Mare Fecunditatis, the Sea of Fertility; Sinus Aestuum, the Bay of Billows; Mare Imbrium, the Sea of Rains; and Mare Tranquillitatis, the Sea of Tranquility, a poetic and evocative collection of place names, particularly for so inhospitable an environment as the Moon. Unfortunately, the lunar Maria are bone dry, and samples returned from them by the U.S. Apollo and Soviet Luna missions imply that never in their past were they filled with water. There never were seas, bays, lakes, or rainbows on the Moon. These names have survived to the present. The first spacecraft to return data from the surface of the Moon, Luna 2, touched down in Mare Imbrium, and the first human beings to make landfall on our natural satellite, the astronauts of Apollo 11, did so 10 years later in Mare Tranquillitatis. I think Galileo would have been surprised and pleased, despite Hevelius's misgivings. The lunar craters were named after scientists and philosophers by Giovanni Battista Riccioli in a 1651 publication, Almagestum Novum. The title of the book means the new Almagest, the old Almagest having been the life's work of Ptolemy. Almagest, a modest title, means the greatest in Arabic. Riccioli simply published a map on which he placed his personal preferences for crater names, and the precedent and many of his choices have been followed without question ever since. Riccioli's book came out 9 years after the death of Galileo, and there has certainly been adequate opportunity to rename craters later. Nevertheless, astronomers have retained this embarrassingly ungenerous recognition of Galileo. Twice as large as crater Galileo is one called Hell after the Jesuit father Maximilian Hell. One of the most striking of the lunar craters is Clavius, 142 miles in diameter, and the site of a fictional lunar base in the movie. 2001, A Space Odyssey. Clavius is the Latinized name of Christoffel Schlüssel, equal key in German. Clavius, another member of the Jesuit order and a supporter of Ptolemy. Galileo engaged in a protracted controversy on the priority of discovery and the nature of sunspots with yet another Jesuit priest, Christopher Scheiner, which developed into a bitter personal antagonism and which is thought by many historians of science to have contributed to the house arrest of Galileo, the proscription of his books, and his confession extracted under threat of torture by the Inquisition that his previous Copernican writings were heretical and that Earth did not move. Scheiner is commemorated by a lunar crater 70 miles across, and Hevelius, who objected altogether to the naming of lunar features after people, has a handsome crater named after himself. Riccioli gave the names Tycho, Kepler, and interestingly Copernicus to 3 of the most prominent craters on the Moon. Riccioli himself and his student Grimaldi received large craters at the limb or edge of the Moon, Riccioli's being 106 miles across. Another prominent crater is named Alphonsus after Alfonso X of Castile, a 13th century Spanish monarch who had commented, after witnessing the complexity of the Ptolemaic system, that had he been present at the creation, he could have given God some useful suggestions on ordering the universe. It is amusing to imagine Alfonso X's response were he to learn that 700 years later a nation across the Western Ocean would send an engine called Ranger 9 to the Moon, automatically producing images of the lunar surface as it descended, until finally it crashed in a pre-existing depression named after his Castilian Majesty, Alphonsus. A somewhat less prominent crater is named after Fabricius, the Latinized name of David Goldschmidt, who in 1596 discovered that the star Mira varied periodically in brightness, striking another blow against the view championed by Aristotle and supported by the Church that the heavens were unchanging. Thus, the prejudice against Galileo in 17th century Italy did not, in the naming of lunar features, carry over as a completely consistent bias in favor of Church Fathers and Church doctrines on matters astronomical. Of the approximately 7,000 designated lunar formations, it is difficult to extract any consistent pattern. There are craters named after political figures who had little direct or apparent connection with astronomy, such as Julius Caesar and Kaiser Wilhelm I, and after individuals of heroic obscurity, for example, crater Wurzelbauer, 50 miles in diameter, and crater Billy, 31 miles in diameter. Most of the designations of small lunar craters are derived from large and nearby craters, as, for example, near the crater Mosting are the smaller craters Mosting A, Mosting B, Mosting C, and so on. A wise prohibition against naming craters after living individuals has been breached only occasionally, as in assigning a few quite small craters to American astronauts of the Apollo lunar missions, and by a curious symmetry in the age of détente to Soviet cosmonauts who remained behind in Earth orbit. In this century, an attempt has been made to name consistently and coherently surface features and other celestial objects by giving this function to special commissions of the International Astronomical Union, IAU, the organization of all professional astronomers on the planet Earth. A previously unnamed bay of one of the lunar seas, examined in detail by the American Ranger spacecraft, was officially designated Mare Cognitum, the known sea. It is a name not so much of quiet satisfaction as of jubilation. IAU deliberations have not always been easy. For example, when the first somewhat indistinct photographs of the far side of the Moon were returned by the historically important Luna 3 mission, the Soviet discoverers wished to name a long, bright marking on their photographs the Soviet mountains. Since there is no major terrestrial mountain range of this name, the suggestion was in conflict with the Hevelius Convention. It was accepted, nevertheless, in homage to the remarkable feat of Luna 3. Unfortunately, subsequent data suggest that the Soviet mountains are not mountains at all. In a related instance, Soviet delegates proposed naming one of the 2 Maria on the lunar far side, both very small compared with those on the near side, Mare Moscoviense, the Sea of Moscow. But Western astronomers objected that this again departed from tradition because Moscow was neither a condition of nature nor a state of mind. It was pointed out in response that the most recent namings of lunar Maria, those on the limbs, which are difficult to make out with ground-based telescopes, have not quite followed this convention either, as Mare Marginis, the marginal sea, Mare Orientale, the eastern sea, and Mare Smithi, the Smith Sea. Perfect consistency having already been breached. The issue was decided in favor of the Soviet proposal at an IAU meeting in Berkeley, California. In 1961, it was officially ruled by Audouin Dollfus of France that Moscow is a state of mind. The advent of space exploration has now multiplied manyfold the problems of solar system nomenclature. An interesting example of the emerging trend can be found in the naming of features on Mars. Bright and dark surface markings on the red planet have been viewed, recorded, and mapped from Earth for several centuries. While the nature of the markings was unknown, there was an irresistible temptation to name them nevertheless. Following several abortive attempts to name them after astronomers who had studied Mars, G.V. Schiaparelli in Italy and E.M. Antoniadi, a Greek astronomer who worked in France, established around the turn of the 20th century the convention of naming Martian features after allusions to classical mythological personages and place names. Thus we have Thoth Nepenthes, Memnonia, Hesperia, Mare Boreum, the northern sea, and Mare Acidalium, the sour sea, as well as Utopia, Elysium, Atlantis, Lemuria, Eos, Dawn, and Euchronia, which I suppose can be translated as good times. In 1890, scholarly people were much more comfortable with classical myth than they are today. The kaleidoscopic surface of Mars was first revealed by American spacecraft of the Mariner series, but chiefly by Mariner 9, which orbited Mars for a full year, beginning in November 1971, and radioed back to Earth more than 7,200 close-up photographs of its surface. A profusion of unexpected and exotic detail was uncovered, including towering volcanic mountains, craters of the lunar sort but much more heavily eroded, and enigmatic sinuous valleys which were probably caused by running water at previous epochs in the history of the planet. These new features cried out for names, and the IAU dutifully appointed a committee under the chairmanship of Gerard de Vaucouleurs of the University of Texas to propose a new Martian nomenclature. Through the efforts of several of us on the Martian Nomenclature Committee, a serious attempt was made to deprovincialize the new names. It was impossible to prevent major craters being named after astronomers who had studied Mars, but the range of occupations and nationalities could be significantly broadened. Thus, there are Martian craters larger than 60 miles across named after the Chinese astronomers Li Fan and Li Uxin, after biologists such as Alfred Russel Wallace, Wolf Vishniak, S.N., Vinogradsky, L. Spallanzani, F. Reddy, Louis Pasteur, H. J. Muller, T. H. Huxley, J. B. S. Haldane, and Charles Darwin, after a handful of geologists such as Louis Agassiz, Alfred Wegener, Charles Lyell, James Hutton, and E. Swiss, and even after a few science fiction writers such as Edgar Rice Burroughs, H. G. Wells, Stanley Weinbaum, and John W. Campbell, Jr. There are also two large craters on Mars named Schiaparelli and Antoniadi. But there are many more cultures on the planet Earth, even ones with identifiable astronomical traditions, than are represented by any such list of individual names. In an attempt to offset, at least in part, this implicit cultural bias, a suggestion of mine was accepted to call the sinuous valleys after the names of Mars in other, largely non-European languages. On this page is a table of the most prominent. By a curious coincidence, Ma'adim, Hebrew, and Al-Kahira, Arabic, the war god after whom Cairo is named, are cheek by jowl. The landing site for the first Viking spacecraft was in Chryse, near the confluence of the Ares, Tiu, Simud, and Shalbatana valleys. Tabi lay, Tibel, name language. Al-Kabira, Egyptian Arabic. Ares Greek. Aukeku, Quechua, Inca. Hua, Sing, Chinese. Ma'adim, Hebrew, Mangala, Sanskrit. Nirgal, Babylonian, Kasei, Japanese. Shalbatana, Akkadian. Simud, Sumerian. Tiu, Old English. For For the massive Martian volcanoes, one suggestion was to name them after major terrestrial volcanoes, such as Ngorongoro or Krakatoa, which would permit some appearance on Mars of cultures with no written astronomical tradition. But this was objected to on the ground that there would be confusion when comparing terrestrial and Martian volcanoes. Which Ngorongoro are we talking about? The same potential problem exists for terrestrial cities, but we seem able to compare Portland, Oregon with Portland, Maine without becoming hopelessly confused. Another suggestion made by a European savant was to name each volcano Mons, mountain, followed by the name of a principal Roman deity in the appropriate Latin genitive case. Thus, Mons Martis, Mons Jovis, and Mons Veneris. I objected that at least the last of these had been preempted by quite a different field of human activity. The reply was, "Oh, I hadn't heard." The outcome was to name the Martian volcanoes after adjacent bright and dark markings in the classical nomenclature. We have Pavonis Mons, Elysium Mons, and satisfyingly, for the largest volcano in the solar system, Olympus Mons. Thus, while the volcano names are very much in the Western tradition, by and large the most recent Mars nomenclature represents a significant break with tradition. An important number of features have been named neither after evocations of classical times nor after European geographical features and 19th century Western visual astronomers. Some Martian and lunar craters are named after the same individuals. This is the Portland case again, and I think it will cause very little confusion in practice. It does have at least one salutary benefit. On Mars, there is today a large crater named Galileo. It is about the same size as the one named Ptolemaeus, and there are no craters on Mars named Shiner or Riccioli. Another unexpected consequence of the Mariner 9 mission is that the first close-up photographs of the moons of another planet were obtained. Maps now exist, which show about half the surface features on the two Martian moons, Phobos and Deimos, the attendants of the war god Mars. A subcommittee on Mars satellite nomenclature which I chaired assigned craters on Phobos to astronomers who had studied the moons. A prominent crater at Phobos' south pole is named after Asaph Hall, the discoverer of both moons. Astronomical Apocrypha has it that Hall was on the verge of giving up his search for the Martian moons when he was directed by his wife to return to the telescope. He promptly discovered them and named them Fear, Phobos, and Terror, Deimos. Accordingly, the largest crater on Phobos was given Mrs. Hall's maiden name, Angelina Stickney. Had the impacting object that excavated crater Stickney been any larger, it probably would have shattered Phobos. Deimos is reserved for writers and others who were in some way involved with speculations about the moons of Mars. The two most prominent features are named after Jonathan Swift and Voltaire, who, in their speculative romances Gulliver's Travels and Micromegas, respectively, prefigured before the actual discovery the existence of two moons around Mars. I wanted to name a third daimonic crater after René Magritte, the Belgian surrealist, whose paintings Le Château des Pyrénées and Le Sens de Réalité pictured large rocks suspended in the sky of an aspect astonishingly like the two Martian moons, except for the presence in the first painting of a castle, which, so far as we know, does not surmount Phobos. The suggestion was, however, voted down as frivolous. This is the moment in history when the features on the planets will be named forever. A crater name represents a substantial memorial. The estimated lifetime of large lunar, Martian, and Mercurian craters is measured in billions of years, because of the enormous recent increase in the number of surface features that need to be named, and also because the names of almost all dead astronomers have already been given to one or another celestial object. A new approach is needed. At the IAU meeting in Sydney, Australia, in 1973, several committees were appointed to look into questions of planetary nomenclature. One clear problem is that if craters on other planets are now named after a category other than people, we will be left with only the names of astronomers and a few others on the moon and planets. It would be charming to name craters on, say, Mercury after birds or butterflies or cities or ancient vehicles of exploration and discovery. But if we accept this course, we will leave the impression on globes and maps and textbooks that we esteem only astronomers and physicists, that we care nothing for poets, composers, painters, historians, archaeologists, playwrights, mathematicians, anthropologists, sculptors, physicians, psychologists, novelists, molecular biologists, engineers, and linguists. The proposal that such individuals be commemorated with unassigned lunar craters would result, say, in Dostoevsky or Mozart or Hiroshige assigned craters 1/10 of a mile across, while Pitiscus is 52 miles in diameter. I do not think this would speak well for the breadth of vision and intellectual ecumenicism of the name-givers. After a protracted debate, this point of view has prevailed in significant part, due to its vigorous support by Soviet astronomers. Accordingly, the Mercury Nomenclature Committee, under the chairmanship of David Morrison of the University of Hawaii, has decided to name Mercurian impact craters after composers, poets, and authors. Thus, major craters are named Johann Sebastian Bach, Homer, and Murasaki. It is difficult for a committee of largely Western astronomers to select a group of names representative of all of world culture, and Morrison's committee requested help from appropriate musicians and experts in comparative literature. The most vexing problem is to find, for example, the names of those who composed Han Dynasty music, cast Benin bronzes, carved Kwakiut totem poles, and compiled Melanesian folk epics. But even if such information comes in slowly, there will be time. The Mariner 10 photography of Mercury, which discovered the features to be named, covered only half the surface of the planet, and it will be many years before the craters in the other hemisphere will be photographed and named. In addition, there are a few objects on Mercury that have been recommended for other sorts of names for special purposes. The proposed 20-degree meridian of longitude passes through a small crater which the Mariner 10 TV experimenters have suggested calling Hun Cal, the Aztec word for 20, the base of Aztec arithmetic, and they have suggested calling an enormous depression in some senses comparable to a lunar mare, the Calorus Basin. Mercury is very hot. Finally, all of these names apply only to the topographic features of Mercury. The bright and dark markings, glimpsed dimly by past generations of ground-based astronomers, have not yet been mapped reliably. When they are, there will probably be new suggestions for naming them. Antoniadi proposed names for such features on Mercury, some of which, such as Solitudo Hermae Trismegisti, the Solitude of Hermes, the Thrice Great, have a fine ring and perhaps will ultimately be retained. No photographic maps of the surface of Venus exist, because the planet is perpetually enshrouded by opaque clouds. Nevertheless, surface features are being mapped by ground-based radar. Already it is apparent that there are craters and mountains and other topographical features of stranger aspect. The success of the Venera 9 and 10 spacecraft in obtaining photographs of the planet's surface suggests that someday photographs may be returned from aircraft or balloons in the lower Venus atmosphere. The first prominent features discovered on Venus, regions highly reflective to radar, were given unassuming names such as Alpha, Beta, and Gamma. The present Venus Nomenclature Committee, under the chairmanship of Gordon Pettengill of the Massachusetts Institute of Technology, proposes 2 categories of names for Venus surface features. One category would be pioneers in radio technology whose work led to the development of the radar techniques that permit mapping the surface of Venus, for example, Faraday, Maxwell, Heinrich Hertz, Benjamin Franklin, and Marconi. The other category, suggested by the name of the planet itself, would be women. At first glance, the idea of a planet devoted to women may appear sexist, but I think the opposite is true. For historical reasons, women have been discouraged from pursuing the sorts of occupations now being memorialized on other planets. The number of women after whom craters have so far been named is very small. Sklodowska, Madame Curie's maiden name; Stickney, the astronomer Maria Mitchell, the pioneer nuclear physicist Lisa Meitner, Lady Murasaki, and only a few others. While by the occupational rules for other planets, women's names will continue to appear occasionally on other planetary surfaces, the Venus proposal is the only one that permits adequate recognition to be made of the historical contribution of women. I'm glad, however, that this idea will not be applied consistently. I would not myself want to see Mercury covered with businessmen and Mars with generals. In a fashion, women have traditionally been commemorated in the asteroid belt, see Chapter 15, that collection of rocky and metallic boulders which circle the Sun between the orbits of Mars and Jupiter. With the exception of a category of asteroids named after heroes of the Trojan War, it used to be that all asteroids were named after women. First, it was largely women of classical mythology, such as Ceres, Urania, Circe, and Pandora. As available goddesses dwindled, the scope broadened to include Sappho, Dike, Virginia, and Sylvia. Then, as the floodgates of discovery opened and the names of astronomers' wives, mothers, sisters, mistresses, and great-aunts were exhausted, they took to naming asteroids after real or hoped-for patrons and others, with a female ending appended, as, for example, Rockefelleria. By now, more than 2,000 asteroids have been discovered, and the situation has become moderately desperate. But non-Western traditions have hardly been tapped, and there are a multitude of Basque, Amharic, Ainu, Dobu, and Kung feminine names for future asteroids. In anticipation of an Egyptian-Israeli détente, Eleanor Helen of the California Institute of Technology proposed calling an asteroid she discovered Ra Shalom. An additional problem or opportunity, depending on how one views it, is that we may soon obtain close-up photographs of asteroids with surface details that will cry out to be named. Beyond the asteroid belt, on the planets and large moons of the outer solar system, no non-descriptive names have so far been bestowed. Jupiter, for example, has a great red spot and a north equatorial belt, but no feature called, say, Smedley. The reason is that when we see Jupiter, we are looking at its clouds, and it would not be a very fitting, or at least not a very long-lived memorial to Smedley to name a cloud after him. Instead, the present major question on nomenclature in the outer solar system is what to name the moons of Jupiter. The moons of Saturn, Uranus, and Neptune have satisfying or at least obscure classical names, see Table 2, but the situation for the 14 moons of Jupiter is different. Table 2. Names of the satellites, of the outer planets, Saturn, Neptune, Janus, Triton, Mimas, Nereid, Enceladus, Tethys, Uranus, Dione, Miranda, Rhea, Ariel, Titan, Umbriel, Hyperion, Titania, Iapetus, Oberon, Phoebe, Pluto, Charon. The 4 large moons of Jupiter were discovered by Galileo, whose theological contemporaries were convinced by a vague amalgam of Aristotelian and biblical ideas that the other planets could have no moons. The contrary discovery by Galileo was disconcerting to fundamentalist churchmen of the time. Possibly in an effort to circumvent criticism, Galileo called the moons the Medicean satellites after his funding agency. But posterity has been wiser. They are known instead as the Galilean satellites. In a similar vein, when William Herschel of England discovered the 7th planet, he proposed calling it George. If wiser heads had not prevailed, we might today have a major planet named after George III. Instead, we call it Uranus. The Galilean satellites were assigned their Greek mythological names by Simon Marius, commemorated on the moon by a crater 27 miles across, a contemporary of Galileo and a disputant with him for the priority of their discovery. Marius and Johannes Kepler felt that it would be extremely unwise to name celestial objects after real people, and particularly after political personages. Marius wrote, "I want the thing done without superstition and with the sanction of theologians." Jupiter especially is charged by the poets with illicit loves. Especially well known among these are 3 virgins whose love Jupiter secretly coveted and obtained, namely Io, Callisto, and Europa. Yet even more ardently did he love the beautiful boy Ganymede, and so I believe that I have not done badly in naming the first Io, the second Europa, the third, on account of the splendor of its light, Ganymede, and lastly the 4th, Callisto. However, in 1892, E. Barnard discovered a 5th moon of Jupiter with an orbit interior to Io's. Barnard resolutely insisted that this satellite should be called Jupiter 5, and by no other name. Since then, Barnard's position has been maintained, and of the 14 Jovian moons now known, only the Galilean satellites had, until recently, names officially sanctioned by the IAU. However unreasonable it may be, people show a strong preference for names over numbers. This is clearly illustrated in the resistance of college students to being considered only a number by the college bursar, by the outrage of many citizens at being known to the government only by their social security number, and by the systematic attempts in jails and prison camps to demoralize and degrade the inmates by assigning them a numeral as their only identity. Soon after Barnard's discovery, Camille Flammarion suggested the name Amalthea for Jupiter 5. Amalthea was in Greek legend the goat that suckled the infant Zeus. While being suckled by a goat is not precisely an act of illicit love, it must have seemed to the Gallic astronomer adequately close. The IAU Committee on Jovian Nomenclature, chaired by Tobias Owen of the State University of New York at Stony Brook, has proposed a set of names for Jupiter 6 through 13. Two principles guided their selection. The name chosen should be that of an illicit love of Jupiter, but one so obscure as to have been missed by those indefatigable colors of the classics who name asteroids, and must end with an A or an E, depending on whether the moon goes around Jupiter clockwise or counterclockwise. But in the opinion of at least some classical scholars, these names are obscure to the point of bewilderment, and the result leaves many of the most prominent Jovian paramours unrepresented in the Jupiter system. The result is particularly poignant in that Hera, Juno, the wife so often scorned by Zeus, Jupiter, is not represented at all. Evidently, she was inadequately illicit. An alternative list of names, which includes most of the prominent paramours as well as Hera, is also shown in the table below. Were these names employed, it is true, they would duplicate asteroid names. This is in any case already a fact for the 4 Galilean satellites, where the amount of confusion thus engendered has been negligible. On the other hand, there are those who support Barnard's position that numbers are sufficient. Prominent among these is Charles Kowal of the California Institute of Technology, the discoverer of Jupiter 13 and Jupiter 14. There seems to be merit in all three positions, and it will be interesting to see how the debate turns out. At least we do not yet have to judge the merits of contending suggestions for naming features on the Jovian satellites. Table 3 proposed names for Jovian satellites. Satellite IAU Committee names alternative names, suggested here: J.V. Amalthea, Amalthea, V.I. Himalaya, Maya, V. Elara Hera, V. Pasiphae Alcmene, X. Sinope, Leto, X. Lysithea Demeter, X.I. Carmis Semele, I.N.A.N. Ankh Danae, the Leda X 4, but that time is not long off. There are 31 known moons of Jupiter, Saturn, Uranus, and Neptune. None has been photographed close up. The decision has recently been made to name features on the moons in the outer solar system after mythological figures from all cultures. However, very soon the Voyager mission will obtain high-resolution images of about 10 of them, in addition to the rings of Saturn. The total surface area of the small objects in the outer solar system greatly exceeds the areas of Mercury, Venus, Earth, Moon, Mars, Phobos, and Deimos together. There will be ample opportunity for all human occupations and cultures to be represented eventually, and I dare say provisions for non-human species can also be made. There are probably more professional astronomers alive today than in the total prior recorded history of mankind. I suppose that many of us will also be commemorated in the outer solar system: a crater on Callisto, a volcano on Titan, a ridge on Miranda, a glacier on Halley's Comet. Comets, incidentally, are given the names of their discoverers. I sometimes wonder what the arrangement will be, whether those who are bitter rivals will be separated by being placed on different worlds, and whether those whose discoveries were collaborative will nestle together, crater rampart to crater rampart. There have been objections that political philosophers are too controversial. I myself would be delighted to see two enormous adjacent craters called Adam Smith and Karl Marx. There are even enough objects in the solar system for dead political and military leaders to be accommodated. There are those who have advocated supporting astronomy by selling crater names to the highest bidders, but I think this goes rather too far. There is a curious problem about names in the outer solar system. Many of the objects there have extremely low density, as if they were made of ice, great fluffy snowballs tens or hundreds of miles across. While objects impacting these bodies will certainly produce craters, craters in ice will not last very long. At least for some objects in the outer solar system, named features may be transient. Perhaps that is a good thing. It would give us a chance to revise our opinions of politicians and others, and will give eventual recourse if flushes of national or ideological fervor are reflected in solar system nomenclature. The history of astronomy shows that some suggestions for celestial nomenclature are better ignored. For example, in 1688, Erhard Weigel at Jena proposed a revision of the ordinary zodiacal constellations, the lion, virgin fish, and water carrier that people have in mind when they ask you what sign you are. Weigel proposed instead a heraldic sky in which the royal families of Europe would be represented by their tutelary animals, a lion and a unicorn for England, for example. I hate to imagine descriptive stellar astronomy today had that idea been adopted in the 17th century. The sky would be carved into 200 tiny patches, one for each nation-state existing at the time. The naming of the solar system is fundamentally not a task for the exact sciences. It has historically encountered prejudice and jingoism and lack of foresight at every turn. However, while it may be a little early for self-congratulation, I think astronomers have recently taken some major steps to deprovincialize the nomenclature and make it representative of all of humanity. There are those who think it is a pointless, or at least thankless, task, but some of us are convinced it is important. Our remote descendants will be using our nomenclature for their homes, on the broiling surface of Mercury, by the banks of the Martian valleys, on the slopes of Titanian volcanoes, or on the frozen landscape of distant Pluto, where the sun appears as a point of bright light in a sky of unremitting blackness. Their view of us, of what we cherish and hold dear, may be determined largely by how we name the moons and planets today. Kowal has also recently discovered a very interesting small object orbiting the sun between the orbits of Uranus and Saturn. It may be the largest member of a new asteroid belt. Kowal proposes calling it Chiron after the centaur who educated many Greek mythological gods and heroes. If other trans-Saturnian asteroids are discovered, they can be named after other centaurs. Chapter 12. Life in the Solar System. "I see nobody on the road," said Alice. "I only wish I had such eyes," the king remarked in a fretful tone. "To be able to see nobody. And at that distance, too, why, it's as much as I can do to see real people by this light." Lewis Carroll. Through the looking glass more than 300 years ago, Anton van Leeuwenhoek of Delft explored a new world. With the first microscope, he viewed a stagnant infusion of hay and was astounded to find it swarming with small creatures. On April 24, 1676, observing this water by chance, I saw therein with great wonder unbelievably very many small animalcules of various sorts, among others, some that were 3 to 4 times as long as broad. Their entire thickness was, in my judgment, not much thicker than one of the little hairs that cover the body of a louse. These creatures had very short, thin legs in front of the head, although I can recognize no head. I speak of the head for the reason that this part always went forward during movement. Close to the hindmost part lay a clear globule, and I judged that the very hindmost part was slightly cleft. These animalcules are very cute while moving about, oftentimes tumbling all over. These tiny animalcules had never before been seen by any human being. Yet Leeuwenhoek had no difficulty in recognizing them as alive. 2 centuries later, Louis Pasteur developed the germ theory of disease from Leeuwenhoek's discovery and laid the foundation for much of modern medicine. Leeuwenhoek's objectives were not practical at all, but exploratory and adventuresome. He himself never guessed the future practical applications of his work. In May of 1974, the Royal Society of Great Britain held a discussion meeting on the recognition of alien life. Life on Earth has developed by a slow, tortuous, step-by-step progression known as evolution by natural selection. Random factors play a critical role in this process, as, for example, which gene at what time will be mutated or changed by an ultraviolet photon or a cosmic ray from space. All the organisms on Earth are exquisitely adapted to the vagaries of their natural environments. On some other planet with different random factors operating in extremely exotic environments, life may have evolved very differently. If we landed a spacecraft on the planet Mars, for example, would we even be able to recognize the local life forms as alive? One theme which was stressed at the Royal Society discussion was that life elsewhere should be recognizable by its improbability. Take trees, for example. Trees are long, skinny structures above ground, fatter at the top than at the bottom. It is easy to see that after millennia of rubbing by wind and water, most trees should have fallen down. They are in mechanical disequilibrium. They are unlikely structures. Not all top-heavy structures are produced by biology. There are, for example, pedestal rocks in deserts. But were we to see a great many top-heavy structures all closely similar, we could make a reasonable guess that they were of biological origin. Likewise for Leeuwenhoek's animalcules, there are many of them, closely similar, highly complex and improbable in the extreme. Without ever having seen them before, we correctly guess they are biological. There have been elaborate debates on the nature and definition of life. The most successful definitions invoke the evolutionary process. But we do not land on another planet and wait to see if any nearby objects evolve. We do not have the time. The search for life then takes on a much more practical aspect. This point was brought out with some finesse at the Royal Society discussion when, after an exchange remarkable for its rambling metaphysical vagueness, Sir Peter Medawar rose to his feet and said, "Gentlemen, everyone in this room knows the difference between a live horse and a dead horse. Pray, therefore, let us cease flogging the latter." Medawar and Leeuwenhoek would have seen eye to eye. But are there trees or animalcules on the other worlds of our solar system? The simple answer is that no one yet knows. From the vantage point of the nearest planets, it would be impossible to detect photographically the presence of life on our own planet. Even from the closest orbital observations of Mars made to date, from the American spacecraft Mariner 9 and Viking 1 and 2, details on Mars much smaller than 100 meters across have remained invisible. Since even the most ardent enthusiasts of extraterrestrial life do not anticipate Martian elephants 100 meters long, many important tests have not yet been performed. At the present time, we can only assess the physical environments of the other planets, determine whether they are so severe as to exclude life, even forms rather different from those we know on Earth, and, in the case of the more clement environments, perhaps speculate on the life forms that might be present. The one exception is the Viking lander results, briefly discussed below. A place may be too hot or too cold for life. If the temperatures are very high, say several thousands of degrees centigrade, then the molecules that make up the organism will fall to pieces. Thus, it is customary to exclude the sun as an abode of life. On the other hand, if the temperatures are too low, then the chemical reactions that drive the internal metabolism of the organism will proceed at too ponderous a pace. For this reason, the frigid wastes of Pluto are customarily excluded as an abode of life. However, there may be chemical reactions which proceed at respectable rates at low temperatures, but which are unexplored here on Earth, where chemists dislike working in laboratories at -230 degrees Celsius. We must be careful not to take too chauvinistic a view of the matter. The giant outer planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, are sometimes excluded from biological considerations because their temperatures are very low. But these temperatures are the temperatures of their upper clouds, deeper down in the atmospheres of such planets as in the atmosphere of the Earth. Much more clement conditions are to be encountered, and they appear to be rich in organic molecules. By no means can they be excluded. While we human beings enjoy oxygen, this is hardly a recommendation for it, since there are many organisms that are poisoned by it. If the thin protective ozone layer in our atmosphere, made by sunlight from oxygen, did not exist, we would rapidly be fried by ultraviolet light from the sun. But on other worlds, ultraviolet sunshades or biological molecules impervious to near ultraviolet radiation can readily be imagined. Such considerations merely underline our ignorance. An important distinction among the other worlds of our solar system is the thickness of their atmospheres. In the total absence of an atmosphere, it is very difficult to conceive of life. As on Earth, the biology on other planets must, we think, be driven by sunlight. On our planet, the plants eat the sunlight and the animals eat the plants. Were all the organisms on Earth forced by some unimaginable catastrophe into a subterranean existence, life would cease as soon as accumulated food stores were exhausted. The plants, the fundamental organisms on any planet, must see the sun. But if a planet has no atmosphere, not only ultraviolet radiation, but X-rays and gamma rays and charged particles from the solar wind will fall unimpeded on the planetary surface and frizzle the plants. Furthermore, an atmosphere is necessary for exchange of materials so that the basic molecules for biology are not all used up. On Earth, for example, green plants give off oxygen, a waste product, into the atmosphere. Many respiring animals, like human beings, breathe the oxygen and give off carbon dioxide, which the plants in turn imbibe. Without this clever and painfully evolved equilibrium between plants and animals, we would rapidly run out of oxygen or carbon dioxide. For these two reasons, radiation protection and molecular exchange, an atmosphere seems required for life. Some of the worlds in our solar system have exceedingly thin atmospheres. Our moon, for example, has at its surface less than 1/1,000,000th the atmospheric pressure on Earth. 6 places on the near side of the moon were examined by Apollo astronauts. No top-heavy structures, no lumbering beasts were found. Nearly 400 kilograms of samples have been returned from the moon and meticulously examined in terrestrial laboratories. There were no animalcules, no microbes, almost no organic chemicals, or even any water. We expected the moon to be lifeless, and apparently it is. Mercury, the closest planet to the sun, resembles the moon. Its atmosphere is exceedingly thin, and it ought not to support life. In the outer solar system, there are many large satellites the size of Mercury or our own moon, composed of some mix of rock, like the moon and Mercury and ices. Io, the second moon of Jupiter, falls into this category. Its surface seems to be covered with a kind of reddish salt deposit. We are very ignorant about it, but because of its very low atmospheric pressure, we do not expect life on it. Then there are planets with moderate atmospheres. Earth is the most familiar example. Here, life has played a major role in determining the composition of our atmosphere. The oxygen is, of course, produced by green plant photosynthesis, but even the nitrogen is thought to be made by bacteria. Oxygen and nitrogen together comprise 99% of our atmosphere, which has evidently been reworked on a massive scale by the life on our planet. The total pressure on Mars is about 1/2 of 1% that on Earth, but the atmosphere there is composed largely of carbon dioxide. There are small quantities of oxygen, water vapor, nitrogen, and other gases. The Martian atmosphere has not obviously been reworked by biology, but we do not know Mars well enough to exclude life there. It has congenial temperatures at some times and places, a dense enough atmosphere, and abundant water locked away in the ground and polar caps. Even some varieties of terrestrial microorganisms can survive there very well. Mariner 9 and Viking found hundreds of dry riverbeds, apparently indicating a time in the recent geological history of the planet when abundant liquid water flowed. It is a world awaiting exploration. A third and less familiar example of places with moderate atmospheres is Titan, the largest moon of Saturn. Titan appears to have an atmosphere with a density between that of Mars and Earth. This atmosphere is, however, composed largely of hydrogen and methane and is surmounted by an unbroken layer of reddish clouds, probably complex organic molecules. Because of its remoteness, Titan has attracted the interest of exobiologists only recently, but it holds the promise of a long-term fascination. The planets with very dense atmospheres present a special problem like Earth. Their atmospheres are cold at the top and warmer at the bottom. But when the atmosphere is very thick, the temperatures at the bottom become too hot for biology. In the case of Venus, the surface temperatures are about 480 degrees Celsius. For the Jovian planets, many thousands of degrees centigrade. All these atmospheres we think are convective, with vertical winds vigorously carrying materials both up and down. Life probably cannot be imagined on their surfaces because of the high temperatures. The cloud environments are perfectly clement, but convection will carry hypothetical cloud organisms down to the depth and fry them there. There are two obvious solutions. There might be small organisms that reproduce as fast as they are carried down to the planetary skillet, or the organisms might be buoyant. Fish on Earth have float bladders for a similar purpose, and both on Venus and on the Jovian planets, organisms that are essentially hydrogen-filled balloons can be envisioned for them to float at modest temperatures on Venus. They need to be at least a few centimeters across, but for the same purpose on Jupiter, they must be at least meters across, the size of ping-pong balls and meteorological balloons, respectively. We do not know that such beasts exist, but it is of some little interest to see that they can be envisioned without doing violence to what is known of physics, chemistry, or biology. Our profound ignorance of whether other planets harbor life may end within this century. Plans are now afoot for the chemical and biological examination of many of these candidate worlds. The first step was the American Viking missions, which landed two sophisticated automatic laboratories on Mars in the summer of 1976, almost 300 years to the month of Leeuwenhoek's discovery of hay infusoria. Viking found no curious structures nearby or sauntering by, which were top-heavy and no detectable organic molecules. Of 3 experiments in microbial metabolism, 2 in both landing sites repeatedly gave what seemed to be positive results. The implications are still under vigorous debate. In addition, we must remember that the 2 Viking landers examined closely, even with photography, less than 1/millionth of the surface area of the planet. More observations, particularly with more sophisticated instrumentation, including microscopes, and with roving vehicles, are needed. But despite the ambiguous nature of the Viking results, these missions represent the first time in the history of the human species that another world has been seriously examined for life. In the following decades, it is likely that there will be buoyant probes into the atmospheres of Venus, Jupiter, and Saturn, and landers on Titan, as well as more detailed studies of the surface of Mars. A new age of planetary exploration and exobiology dawned in the 7th decade of the 20th century. We live in a time of adventure and high intellectual excitement, but also, as the step from Leeuwenhoek to Pasteur shows, in the midst of an endeavor which promises great practical benefits. Chapter 13. Titan, the enigmatic moon of Saturn. On Titan, warmed by a hydrogen blanket, ice-ribbed volcanoes jet ammonia dredged out of a glacial heart. Liquid and frozen assets uphold an empire, bigger than Mercury, and even a little like primitive Earth. Asphalt plains and hot mineral ponds. But how I'd like to take the waters of Titan, under that fume-ridden sky, where the land's blurred by cherry mist, and high above, like floating wombs, clouds tower and swarm, raining down primeval, bisque, while life waits in the wings. Diane Ackerman. The Planet's New York, Morrow, 1976. Titan is not a household word or world. We do not usually think of it when we run through a list of familiar objects in the solar system. But in the last few years, this satellite of Saturn has emerged as a place of extraordinary interest and prime significance for future exploration. Our most recent studies of Titan have revealed that it has an atmosphere more like the Earth's, at least in terms of density, than any other object in the solar system. This fact alone gives it new significance as the exploration of other worlds begins in earnest. Besides being the largest satellite of Saturn, Titan is also, according to recent work by Joseph Vifurka, James Elliott, and others at Cornell University, the largest satellite in the solar system, about 5,800 kilometers, 3,600 miles, in diameter. Titan is larger than Mercury and nearly as large as Mars, and yet there it is in orbit around Saturn. We might obtain some clues about the nature of Titan by examining the 2 major worlds in the outer solar system, Jupiter and Saturn. Both have a general reddish or brownish coloration, that is, the upper layer of clouds that we see from the Earth has this hue primarily, Something in the atmosphere and clouds of these planets is strongly absorbing blue and ultraviolet light, so that the light that is reflected back to us is primarily red. The outer solar system, in fact, has a number of objects that are remarkably red. Although we have no color photographs of Titan because it is 800 million miles away and has an angular size smaller than the Galilean satellites of Jupiter, photoelectric studies reveal that it is, in fact, very red. Astronomers who thought about the problem once believed that Titan was red for the same reason that Mars is red, a rusty surface. But then the reason for Titan's red color would be different from the reason for Jupiter's and Saturn's, because we do not see to a solid surface on those planets. In 1944, Gerard Kuiper detected spectroscopically an atmosphere of methane around Titan, the first satellite found to have an atmosphere. Since then, the methane observations have been confirmed, and at least moderately suggestive evidence for the presence of molecular hydrogen has been provided by Lawrence Trafton of the University of Texas. Since we know the amount of gas necessary to produce the observed spectral absorption features, and we know from its mass and radius the surface gravity of Titan, we can deduce the minimum atmospheric pressure. We find it is something like 10 millibars, about 1% of the Earth's atmospheric pressure, a pressure that exceeds that of Mars. Titan has the most Earth-like atmospheric pressure in the solar system. Not only the best, but the only visual telescopic observations of Titan have been made by Audouin Dollfus at the Meudon Observatory in France. These are hand drawings done at the telescope during moments of atmospheric steadiness. From the variable patches that he observed, Dollfus concluded that things are happening on Titan that do not correlate with the satellite's rotation period. Titan is thought always to face Saturn as our moon does the Earth. Dollfus guessed that there might be clouds, at least of a patchy sort, on Titan. Our knowledge of Titan has made a number of substantial quantum jumps forward in recent years. Astronomers have successfully obtained the polarization curve of small objects. The idea is that initially unpolarized sunlight falls on Titan, say, and is polarized on reflection. The polarization is detected by a device similar in principle to, but more sophisticated and sensitive than, Polaroid sunglasses. The amount of polarization is measured as Titan goes through a small range of phases between full Titan and slightly gibbous Titan. The resulting polarization curve, when compared to laboratory polarization curves, gives information on the size and composition of the material responsible for the polarization. The first polarization observations of Titan, made by Joseph Weverke, indicated that the sunlight reflected back from Titan is most likely reflected off clouds and not off a solid surface. Apparently, there is on Titan a surface and a lower atmosphere that we do not see, an opaque cloud deck and an overlying atmosphere, both of which we do see, and an occasional patchy cloud above that. Since Titan appears red and we view it at the cloud deck, there must, according to this argument, be red clouds on Titan. Additional support for this concept comes from the extremely low amount of ultraviolet light reflected from Titan as measured by the orbiting astronomical observatory. The only way to keep Titan's ultraviolet brightness small is to have the ultraviolet absorbing stuff high up in the atmosphere. Otherwise, Rayleigh scattering by the atmospheric molecules themselves would make Titan bright in the ultraviolet. Rayleigh scattering is the preferential scattering of blue rather than red light, which is responsible for blue skies on Earth. But material that absorbs in the ultraviolet and violet appears red in reflected light. So there are two separate lines of evidence, or three, if we believe the hand drawings, for an extensive cloud cover on Titan. What do we mean by extensive? More than 90% of Titan must be cloaked in clouds to match the polarization data. Titan seems to be covered by dense red clouds. A second astonishing development was inaugurated in 1971 when D. A. Allen of Cambridge University and T.L. Murdoch of the University of Minnesota found that the observed infrared emission from Titan at a wavelength of 10 to 14 microns is more than twice what is expected from solar heating. Titan is too small to have a significant internal energy source like Jupiter or Saturn. The only explanation seemed to be the greenhouse effect, in which the surface temperature rises until the infrared radiation trickling out just balances the absorbed visible radiation coming in. It is the greenhouse effect that keeps the surface temperature of the Earth above freezing and the temperature of Venus at 480 degrees Celsius. But what could cause a titanian greenhouse effect? It is unlikely to be carbon dioxide and water vapor as on Earth and Venus, because these gases should be largely frozen out on Titan. I have calculated that a few hundred millibars of hydrogen, 1,000 millibars is the total sea level atmospheric pressure on Earth, would provide an adequate greenhouse effect. Since this is more than the amount of hydrogen observed, the clouds would have to be opaque at certain short wavelengths and more nearly transparent at certain longer wavelengths. James Pollock at NASA's Ames Research Center has calculated that a few hundred millibars of methane might also be adequate and moreover might explain some of the details of the infrared emission spectrum of Titan. This large amount of methane would also have to hide under the clouds. Both greenhouse models have the virtue of invoking only gases thought to exist on Titan. Of course, both gases might play a role. An alternative model of the Titan atmosphere was proposed by the late Robert Danielson and his colleagues at Princeton University. They suggest that small quantities of simple hydrocarbons, such as ethane, ethylene, and acetylene, which have been observed in the upper atmosphere of Titan, absorb ultraviolet light from the sun and heat the upper atmosphere. It is then the hot upper atmosphere and not the surface that we see in the infrared. On this model, there need be no enigmatically warm surface, no greenhouse effect, and no atmospheric pressure of hundreds of millibars. Which view is correct? At the present time, no one knows. The situation is reminiscent of studies of Venus in the early 1960s, when the planet's radio brightness temperature was known to be high. But whether the emission was from a hot surface or a hot region of the atmosphere was, appropriately, hotly debated. Since radio waves pass through all but the densest atmospheres and clouds, the Titan problem might be resolved if we had a reliable measure of the radio brightness temperature of the satellite. The first such measurement was performed by Frank Briggs of Cornell with the giant interferometer of the National Radio Astronomy Observatory in Green Bank, West Virginia. Briggs finds a surface temperature of Titan of minus 140 degrees Celsius with an uncertainty of 45 degrees. The temperature in the absence of a greenhouse effect is expected to be about minus 185 degrees Celsius. Briggs's observations, therefore, seem to suggest a fairly sizable greenhouse effect and a dense atmosphere. But the probable error of the measurements is still so large as to permit the zero greenhouse case. Subsequent observations by two other radio-astronomical groups give values both higher and lower than Briggs's results. The higher range of temperatures, astonishingly, even approaches temperatures in cold regions of the Earth. The observational situation, like the atmosphere of Titan, seems very murky. The problem could be resolved if we could measure the size of the solid surface of Titan by radar. Optical measurements give us the distance from cloud top to cloud top. The problem may have to await studies by the Voyager mission, which is scheduled to send 2 sophisticated spacecraft by Titan, one very close to it in 1981. Whichever model we select is consistent with the red clouds. But what are they made of? If we take an atmosphere of methane and hydrogen and supply energy to it, we will make a range of organic compounds, both simple hydrocarbons, like the sort that are needed to make Danielson's inversion layer in the upper atmosphere, and complex ones. In our laboratory at Cornell, Bishun Kere and I have simulated the kinds of atmospheres that exist in the outer solar system. The complex organic molecules we synthesize in them have optical properties similar to those of the Titanian clouds. We think there is strong evidence for abundant organic compounds on Titan, both simple gases in the atmosphere and more complex organics in the clouds and on the surface. One problem with an extensive Titanian atmosphere is that the light gas hydrogen should be gushing away because of the low gravity. The only way that I can explain this situation is that the hydrogen is in a steady state. That is, it escapes but is replenished from some internal source, volcanoes most likely. The density of Titan is so low that its interior must be almost entirely composed of ices. We can think of it as a giant comet made of methane, ammonia, and water ices. There must also be a small admixture of radioactive elements which, while decaying, will heat their surroundings. The heat conduction problem has been worked out by John Lewis of MIT, and it is clear that the near-surface interior of Titan will be slushy. Methane, ammonia, and water vapor should be outgassed from the interior and broken down by ultraviolet sunlight, producing atmospheric hydrogen and cloud organic compounds at the same time. There may be surface volcanoes made of ice instead of rock, spewing out in occasional eruptions not liquid rock, but liquid ice, a lava of running methane, ammonia, and perhaps water. There is another consequence of the escape of all this hydrogen. An atmospheric molecule that achieves escape velocity from Titan generally does not have escape velocity from Saturn. Thus, as Thomas McDonough and the late Neil Bryce of Cornell have pointed out, the hydrogen that is being lost from Titan will form a diffuse toroid, or donut of hydrogen gas around Saturn. This is a very interesting prediction, first made for Titan but possibly relevant for other satellites as well. Pioneer 10 has detected such a hydrogen toroid around Jupiter in the vicinity of Io. As Pioneer 11 and Voyager 1 and 2 fly near Titan, they may be able to detect the Titan toroid. Titan will be the easiest object to explore in the outer solar system. Nearly atmosphereless worlds such as Io or the asteroids present a landing problem because we cannot use atmospheric braking. Giant worlds such as Jupiter and Saturn have the opposite problem. The acceleration due to gravity is so large and the increase in atmospheric density is so rapid that it is difficult to devise an atmospheric probe that will not burn up on entry. Titan, however, has a dense enough atmosphere and a low enough gravity. If it were a little closer, we probably would be launching entry probes there today. Titan is a lovely, baffling, and instructive world which we suddenly realize is accessible for exploration, by flybys to determine the gross global parameters and to search for breaks in the clouds, by entry probes to sample the red clouds and unknown atmosphere, and by landers to examine a surface like none we know. Titan provides a remarkable opportunity to study the kinds of organic chemistry that on Earth may have led to the origin of life. Despite the low temperatures, it is by no means impossible that there is a Titanian biology. The geology of the surface may be unique in all the solar system. Titan is waiting. Chapter 14, The Climates of Planets. Is it not the height of silent humor to cause an unknown change in the Earth's climate? Robert Graves, The Meeting. Between 30 and 10 million years ago, it is thought, temperatures on Earth slowly declined by just a few centigrade degrees. But many plants and animals have their life cycles sensitively attuned to the temperature, and vast forests receded toward more tropical latitudes. The retreat of the forests slowly removed the habitats of small furry binocular creatures, weighing only a few pounds, which had lived out their days brachiating from branch to branch. With the forests gone, only those furry creatures able to survive on the grassy savannas were to be found. Some tens of millions of years later, those creatures left two groups of descendants, one which includes the baboons and the other called humans. We may owe our very existence to climatic changes that on the average amount to only a few degrees. Such changes have brought some species into being and extinguished others. The character of life on our planet has been powerfully influenced by such variations, and it is becoming increasingly clear that the climate is continuing to change today. There are many indications of past climatic changes. Some methods reach far into the past, others have only a limited applicability. The reliability of the methods also differs. One approach, which may be valid for 1 million years back in time, is based on the ratio of the isotopes oxygen 18 to oxygen 16 in the carbonates of shells of fossil foraminifera. These shells, belonging to species very similar to some that can be studied today, vary the oxygen 16-oxygen 18 ratio according to the temperature of the water in which they grew. Somewhat similar to the oxygen isotope method is one based upon the ratio of the isotopes sulfur 34 to sulfur 32. There are other, more direct fossil indicators. For example, the widespread presence of corals, figs, and palms denotes high temperatures, and the abundant remains of large hairy beasts, such as mammoths, indicate cold temperatures. The geological record is replete with extensive evidence of glaciation, great moving sheets of ice that leave characteristic boulders and erosional traces. There is also clear geological evidence for beds of evaporites, regions where briny water has evaporated, leaving behind the salts. Such evaporation occurs preferentially in warm climates. When this range of climatic information is put together, a complex pattern of temperature variation emerges. At no time, for example, is the average temperature of the Earth below the freezing point of water, and at no time does it even approach the normal boiling point of water. But variations of several degrees are common, and even variations of 20 or 30 degrees may have occurred, at least locally. Fluctuations of a few degrees centigrade happen over characteristic times of tens of thousands of years, and the recent succession of glacial and interglacial periods has this timing and temperature amplitude, but there are climatic fluctuations over much longer periods, the longest being on the order of a few 100 million years. Warm periods appear to have occurred about 650 million years ago and 270 million years ago. By the standards of past climatic fluctuations, we are now in the midst of an ice age. For most of the Earth's history, there were no permanent ice caps, as in the Arctic and Antarctic today. We have, over the past few hundred years, made a partial emergence from our ice age caused by some as yet unexplained minor climatic variation, and there are certain signs that we may plunge back into the global cold temperatures characteristic of our epoch as seen from the perspective of the immense vistas of geological time. It is a sobering fact that 2 million years ago the site of the city of Chicago was buried under a mile of ice. What determines the temperature of Earth? As seen from space, it is a rotating blue ball streaked with varying cloud patches, reddish-brown deserts, and brilliant white polar caps. The energy for heating the Earth comes almost exclusively from sunlight. The energy conducted up from the hot interior of the Earth amounting to less than 1,000th of 1% of that, arriving in the form of visible light from the sun. But not all the sunlight is absorbed by the Earth. Some is reflected back to space by polar ice, clouds, and the rocks and water on the surface of the Earth. The average reflectivity, or albedo, of the Earth, as measured directly from satellites and indirectly from Earthshine reflected off the dark side of the Moon, is about 35%. The 65% of sunlight that is absorbed by the Earth heats it to a temperature which can readily be calculated. This temperature is about -18 degrees Celsius, below the freezing point of seawater, and some 30 degrees Celsius colder than the measured average temperature of the Earth. The discrepancy is due to the fact that this calculation neglects the so-called greenhouse effect. Visible light from the sun enters the Earth's clear atmosphere and is transmitted through to the surface. The surface, however, in attempting to radiate back into space, is constrained by the laws of physics to do so in the infrared. The atmosphere is not so transparent in the infrared, and at some wavelengths of infrared radiation, such as 6.2 microns or 15 microns radiation, would travel only a few centimeters before being absorbed by atmospheric gases. Since the Earth's atmosphere is murky and absorbing at many wavelengths in the infrared, the thermal radiation given off by the surface of the Earth is impeded in escaping to space. In order to have a close equality between the radiation received by the Earth from the Sun and the radiation emitted by the Earth to space, the surface temperature of the Earth must then rise. The greenhouse effect is due not to the major atmospheric constituents of the Earth, such as oxygen and nitrogen, but almost exclusively to the minor constituents, especially carbon dioxide and water vapor. As we have seen, the planet Venus is probably a case where the massive injection of carbon dioxide and smaller amounts of water vapor into a planetary atmosphere has led to such a large greenhouse effect that water cannot be maintained on the surface in the liquid state. Hence, the planetary temperature runs away to some extremely high value in the case of Venus, 480 degrees Celsius. We have so far been talking about average temperatures. The temperature of the Earth varies from place to place. It is colder at the poles than at the equator because, in general, sunlight falls directly on the equator and obliquely on the poles. The tendency for the temperatures to be very different between equator and poles on Earth is moderated by atmospheric circulation. Hot air rises at the equator and moves at high altitudes to the poles, where it settles and returns to the surface. It then retraces its path, but at low altitudes from pole back to equator. This general motion, complicated by the rotation of the Earth, its topography, and the phase changes of water, is responsible for weather. The observed average temperature of about 15 degrees Celsius on the Earth today can be explained quite well by the observed intensity of sunlight, global albedo, the tilt of the rotational axis, and the greenhouse effect. But all of these parameters can, in principle, vary, and past or future climatic change can be attributed to changes in any of them. In fact, there have been almost 100 different theories of climatic change on Earth, and even today the subject is hardly marked by unanimity of opinion. This is not because climatologists are by nature ignorant or contentious, but rather because the subject is exceedingly complex. Both negative and positive feedback mechanisms probably exist. Suppose, for example, there were a decrease of a few degrees in the Earth's temperature. The amount of water vapor in the atmosphere is determined almost entirely by temperature, and declines by snowing out as the temperature declines. Less water in the atmosphere implies a smaller greenhouse effect and a further lowering of the temperature, which may result in even less atmospheric water vapor, and so on. Likewise, a decline in temperature may increase the amount of polar ice, increasing the albedo of the Earth and decreasing the temperature still further. On the other hand, a decline in temperature may decrease the amount of cloudiness, which will decrease the average albedo of the Earth and increase the temperature, perhaps enough to undo the initial temperature decrease, and it has been proposed recently that the biology of the planet Earth acts as a kind of thermostat to prevent too extreme excursions in temperature, which might have deleterious global biological consequences. For example, a decline in temperature may cause an increase of a species of hardy plants that has extensive ground cover and low albedo. Three of the more fashionable and more interesting theories of climatic change should be mentioned. The first involves a change in celestial mechanical variables. The shape of the Earth's orbit, the tilt of its axis of rotation, and the precession of that axis all vary over long periods of time because of the interaction of the Earth with other nearby celestial objects. Detailed calculations of the extent of such variations show that they can be responsible for at least a few degrees of temperature variation, and with the possibility of positive feedbacks, this might by itself be adequate to explain major climatic variations. A second class of theories involves albedo variations. One of the more striking causes for such variations is the injection into the Earth's atmosphere of massive amounts of dust, for example from a volcanic explosion such as Krakatoa's in 1883. While there has been some debate on whether such dust heats or cools the Earth, the bulk of present calculations shows that the fine particulates very slowly falling out of Earth's stratosphere increase the Earth's albedo and therefore cool it. There is recent sedimentological evidence that past epochs of extensive production of volcanic particulates correspond in time to past epochs of glaciation and low temperatures. In addition, episodes of mountain building and the creation of land surface on the Earth increase the global albedo because the land is brighter than the water. Finally, there is the possibility of variations in the brightness of the sun. We know from theories of solar evolution that over many billions of years the sun has been getting steadily brighter. This immediately poses a problem for the most ancient climatology of the Earth, because the sun should have been 30 or 40% dimmer some 3 or 4 billion years ago, and this is enough, even with the greenhouse effect, to have resulted in global temperatures well below the freezing point of seawater. Yet there is extensive geological evidence, for example, underwater ripple marks, pillow lavas produced by the quenching of magma in the ocean, and fossil stromatolites produced by oceanic algae, that there was ample water then available. One proposed way out of this quandary is the possibility that there were additional greenhouse gases in the early atmosphere of the Earth, especially ammonia, which produced the required temperature increment. But apart from this very slow evolution of the brightness of the sun, is it possible that shorter-term fluctuations occur? This is an important and unsolved problem, but recent difficulties in finding neutrinos which should, according to current theories, be emitted from the interior of the sun have led to the suggestion that the sun is today in an anomalously dim period. The inability to distinguish between the various alternative models of climatic change might appear to be nothing more than an unusually annoying intellectual problem, except for the fact that there appear to be certain practical and immediate consequences of climatic change. Some evidence on the trend of global temperature seems to show a very slow increase from the beginning of the Industrial Revolution to about 1940 and an alarmingly steep decline in global temperature thereafter. This pattern has been attributed to the burning of fossil fuels, which has two consequences: the liberation of carbon dioxide, a greenhouse gas, into the atmosphere, and the simultaneous injection into the atmosphere of fine particles from the incomplete burning of the fuel. The carbon dioxide heats the Earth. The fine particles, through their higher albedo, cool it. It may be that until 1940 the greenhouse effect was winning, and since then the increased albedo is winning. The ominous possibility that human activities may cause inadvertent climate modification makes the interest in planetary climatology rather important. There are worrisome positive feedback possibilities on a planet with declining temperatures. For example, an increased burning of fossil fuels in a short-term attempt to stay warm can result in more rapid long-term cooling. We live on a planet in which agricultural technology is responsible for the food of more than 1 billion people. The crops have not been bred for hardiness against climatic variations. Human beings can no longer undertake great migrations in response to climatic change, or at least it is more difficult on a planet controlled by nation-states. It is becoming imperative to understand the causes of climatic variations and to develop the possibility of performing climatic re-engineering of the Earth. Oddly enough, some of the most interesting hints on the nature of such climatic changes appear to be coming from studies not of the Earth at all, but of Mars. Mariner 9 was injected into Martian orbit on November 14, 1971. It had a useful scientific lifetime of a full terrestrial year and procured 7,200 photographs covering the planet from pole to pole, as well as tens of thousands of spectra and other scientific information. As we saw earlier, when Mariner 9 arrived at Mars, there was virtually no detail whatever to be seen on the surface, because the planet was in the throes of a great global dust storm. It was readily observed that the atmospheric temperatures increased, but the surface temperatures decreased during the dust storm, and this simple observation immediately provides at least one clear case of the cooling of a planet by the massive injection of dust into its atmosphere. Calculations have been performed that use precisely the same physics for both the Earth and Mars and treat them as two different examples of the general problem of the climatic effects of massive dust injection into a planetary atmosphere. There was another and entirely unexpected climatological finding by Mariner 9, the discovery of numerous sinuous channels replete with tributaries covering the equatorial and mid-latitudes of Mars. In all cases where relevant data exist, the channels are going in the proper direction, downhill. Some of them show braided patterns, sand bars, slumping of the banks, streamlined teardrop-shaped interior islands, and other characteristic morphological signs of terrestrial river valleys. But there is a great problem with the interpretation of the Martian channels as dry riverbeds or arroyos. Liquid water apparently cannot exist on Mars today. The pressures are simply too low. Carbon dioxide on Earth is known as both a solid and a gas, but never as a liquid except in high-pressure storage tanks. In the same way, water on Mars can exist as a solid, ice or snow, or as vapor, but not as a liquid. For this reason, some geologists are reluctant to accept the theory that at one time the channels contained liquid water. Yet they are dead ringers for terrestrial rivers, and at least many of them have forms inconsistent with other possible structures such as collapsed lava tubes, which may be responsible for sinuous valleys on the Moon. Furthermore, there is an apparent concentration of such channels toward the Martian equator. The one striking fact about the equatorial regions of Mars is that they are the only places on the planet where the average daytime temperature is above the freezing point of water, and no other liquid is simultaneously cosmically abundant of low viscosity and with a freezing point below Martian equatorial temperatures. If, then, the channels were made by running water on Mars, that water apparently must have run at a time when the Martian environment was significantly different from what it is today. Today, Mars has a thin atmosphere, low temperatures, and no liquid water. At some time in the past, it may have had higher pressures, perhaps somewhat higher temperatures and extensive running water. Such an environment appears to be more hospitable to forms of life based on familiar terrestrial biochemical principles than the present Martian environment. A detailed study of the possible causes of such major climatic changes on Mars has laid stress on a feedback mechanism known as advective instability. The Martian atmosphere is composed primarily of carbon dioxide. There seem to be large repositories of frozen CO2 in at least one of the two polar caps. The pressure of CO2 in the Martian atmosphere is quite close to the pressure of CO2 expected in equilibrium with frozen carbon dioxide at the temperature of the cold Martian pole. This is a situation quite similar to the pressure in a laboratory vacuum system determined by the temperature of a cold finger in the system. At the present time, the Martian atmosphere is so thin that hot air rising from the equator and settling at the poles plays a very small role in heating the high latitudes. But let us imagine that the temperature in the polar regions is somehow slightly increased. The total atmospheric pressure increases. The efficiency of heat transport by advection from equator to pole also increases. Polar temperatures increase still further, and we see the possibility of a runaway to high temperatures. Likewise, a decrease in temperature from whatever cause could bring about a runaway toward a lower temperature. The physics of this Martian situation is easier to work out than the comparable case on Earth, because on Earth, the major atmospheric constituents, oxygen and nitrogen, are not condensable at the poles. For a major increase in pressure to occur on Mars, the amount of heat absorbed in the polar regions of the planet must be increased by some 15 or 20% for a period of at least a century. 3 possible sources of variation in the heating of the cap have been identified. And they are, interestingly enough, very similar to the 3 fashionable models of terrestrial climatic change discussed above. In the first, variations of the tilt of the Martian rotational axis toward the Sun are invoked. Such variations are much more striking than for the Earth because Mars is close to Jupiter, the most massive planet in the solar system, and the gravitational perturbations by Jupiter are pronounced. Here, variations in global pressure and temperature will occur on 100,000 to million-year timescales. Secondly, a variation in the albedo of the polar regions can cause major climatic variations. We can already see substantial sand and dust storms on Mars, because of which the polar caps seasonally darken and brighten. There has been one suggestion that the climate of Mars may be made more hospitable if a hardy species of polar plant can be developed that will lower the albedo of the Martian polar regions. Finally, there is the possibility of variations in the luminosity of the Sun. Some of the channels on Mars have an occasional impact crater in them, and crude dating of the channels from the frequency of impacts from interplanetary space shows that some of them must be about 1 billion years old. This is reminiscent of the last epoch of high global temperatures on the planet Earth and raises the captivating possibility of synchronous major variations in climate between the Earth and Mars. The subsequent Viking missions to Mars have increased our knowledge about the channels in a major way, have provided quite independent evidence for a dense earlier atmosphere, and have demonstrated a great repository of frozen carbon dioxide in the polar ice. When the Viking results are fully assimilated, they promise to add greatly to our knowledge of the present environment, as well as the past history of the planet, and of the comparison between the climates of the Earth and Mars. When scientists are faced with extremely difficult theoretical problems, there is always the possibility of performing experiments. In studies of the climate of an entire planet, however, experiments are expensive and difficult to perform, and have potentially awkward social consequences. By the greatest good fortune, nature has come to our aid by providing us with nearby planets with significantly different climates and significantly different physical variables. Perhaps the sharpest test of theories of climatology is that they be able to explain the climates of all the nearby planets, Earth, Mars, and Venus. Insights gained from the study of one planet will inevitably aid the study of the others. Comparative planetary climatology appears to be a discipline just in the process of birth, with major intellectual interest and practical applications. Chapter 15, Calliope and the Kaaba. We imagine them flitting, cheek to jowl, these drift rocks of cosmic ash thousandfold afloat between Jupiter and Mars. Frigga, Fanny, Adelheid Lacrimosa names to conjure with, Dakotan Black Hills, a light opera staged on a barrier reef, and swarm they may have crumbly as blue cheese, that moment, when the solar system broke wind. But now, they lumber so wide apart from each, to its neighbor's pinprick glow slant, millions and millions of watertight miles, only in the longest view. Do they graze like one herd on a breathless tundra? Diane Ackerman, The Planets, New York, Morrow, 1976. One of the 7 wonders of the ancient world was the Temple of Diana at Ephesus, in Asia Minor, an exquisite example of Greek monumental architecture. The Holy of Holies in this temple was a great black rock, probably metallic, that had fallen from the skies, a sign from the gods, perhaps an arrowhead shot from the crescent moon, the symbol of Diana the Huntress. Not many centuries later, perhaps even at the same time, another great black rock, according to the belief of many, fell out of the sky onto the Arabian Peninsula. There, in pre-Islamic times, it was emplaced in a Meccan temple, the Kaaba, and offered something akin to worship. Then, in the 7th and 8th centuries AD, came the stunning success of Islam, founded by Muhammad, who lived out most of his days not far from this large, dark stone, the presence of which might conceivably have influenced his choice of career. The earlier worship of the stone was incorporated into Islam, and today a principal focus of every pilgrimage to Mecca is that same stone, often called the Kaaba after the temple that enshrines it. All religions have shamelessly co-opted their predecessors, e.g., consider the Christian festival of Easter, where the ancient fertility rites of the spring equinox are today cunningly disguised as eggs and baby animals. Indeed, the very name Easter is, according to some etymologies, a corruption of the name of the great Near Eastern earth, mother goddess Astarte. The Diana of Ephesus is a later and Hellenized version of Astarte and Cybele. In primitive times, a great boulder falling out of a clear blue sky must have provided onlookers with a memorable experience. But it had a greater importance. At the dawn of metallurgy, iron from the skies was, in many parts of the world, the purest available form of this metal. The military significance of iron swords and the agricultural significance of iron plowshares made metal from the sky a concern of practical men. Rocks still fall from the skies, farmers still occasionally break their plows on them, museums still pay a bounty for them, and very rarely one falls through the eaves of a house, narrowly missing a family in its evening hypnagogic ritual before the television set. We call these objects meteorites, but naming them is not the same as understanding them. Where, in fact, do meteorites come from? Between the orbits of Mars and Jupiter are thousands of irregularly shaped, tumbling little worlds called asteroids or planetoids. Asteroid is not a good term for them because they are not like stars. Planetoid is much better because they are like planets, only smaller. But asteroid is the more widely used term by far. Ceres, the first asteroid to be found, was discovered telescopically on January 1, 1801, an auspicious finding on the first day of the 19th century by G. Piazzi, an Italian monk. Ceres is about 1,000 kilometers in diameter and is by far the largest asteroid. By comparison, the diameter of the Moon is 3,464 kilometers. Since then, more than 2,000 asteroids have been discovered. Asteroids are given a number indicating their order of discovery. But following Piazzi's lead, a great effort was also made to give them names, female names, preferably from Greek mythology. However, 2,000 asteroids is a great many, and the nomenclature becomes a little ragged toward the end. We find 1 Ceres, 2 Pallas, 3 Juno, 4 Vesta, 16 Psyche, 22 Calliope, 34 Circe, 55 Pandora, 80 Sappho, 232 Russia, 324 Bamberga, 433 Eros, 710 Gertrude, 739 Mandeville, 747 Winchester, 904 Rockefelleria, 916 America, 1112 Natasha, 1's 2024 Fantasia, 1's 2079 Uganda, 1056 Icarus, 1620 Geographos, 1685 Toro, and 694 Eckard, Drake University, spelled backwards. 1984 Orwell is, unfortunately, a lost opportunity. Many asteroids have orbits that are highly elliptical or stretched out, not at all like the almost perfectly circular orbits of Earth or Venus. Some asteroids have their far points from the Sun beyond the orbit of Saturn. Some have their near points to the Sun close to the orbit of Mercury. Some, like 1685 Toro, live out their days between the orbits of Earth and Venus. Since there are so many asteroids on very elliptical orbits, collisions are inevitable over the lifetime of the solar system. Most collisions will be of the overtaking variety, one asteroid nudging up to another, making a soft splintering crash. Since the asteroids are so small, their gravity is low, and the collision fragments will be splayed out into space, into slightly different orbits from those of the parent asteroids. It can be calculated that such collisions will produce on occasion fragments that by accident intercept the Earth, fall through its atmosphere, survive the ablation of entry, and land at the feet of a quite properly astonished itinerant tribesman. The few meteorites that have been tracked as they enter the Earth's atmosphere originated back in the main asteroid belt between Mars and Jupiter. Laboratory studies of the physical properties of some meteorites show them to have originated where the temperatures are those of the main asteroid belt. The evidence is clear. The meteorites ensconced in our museums are fragments of asteroids. We have on our shelves pieces of cosmic objects. But which meteorites come from which asteroids? Until the last few years, answering this question was beyond the powers of planetary scientists. Recently, however, it has become possible to perform spectrophotometry of asteroids in visible and near-infrared radiation to examine the polarization of sunlight reflected off asteroids as the geometry of the asteroid, the Sun and Earth changes, and to examine the middle infrared emission of the asteroids. These asteroid observations and comparable studies of meteorites and other minerals in the laboratory have provided the first fascinating hints on the correlation between specific asteroids and specific meteorites. More than 90% of the asteroids studied fall into one of two composition groups, stony iron or carbonaceous. Only a few percent of the meteorites on Earth are carbonaceous, but carbonaceous meteorites are very friable and rapidly weather to powder under typical terrestrial conditions. They probably also fragment more readily upon entry into the Earth's atmosphere. Since stony iron meteorites are much hardier, they are disproportionately represented in our museum collections of meteorites. The carbonaceous meteorites are rich in organic compounds, including amino acids, the building blocks of proteins, and may be representative of the materials from which the solar system was formed some 4.6 billion years ago. Among the asteroids which appear to be carbonaceous are 1 Ceres, 2 Pallas, 19 Fortuna, 324 Bamberga, and 654 Zelinda. If asteroids that are carbonaceous on the outside are also carbonaceous on the inside, then most of the asteroidal material is carbonaceous. They are generally dark objects, reflecting only a small percent of the light shining on them. Recent evidence suggests that Phobos and Deimos, the two moons of Mars, may also be carbonaceous, and are perhaps carbonaceous asteroids that have been captured by Martian gravity. Typical asteroids showing properties of stony iron meteorites are 3 Juno, 8 Flora, 12 Victoria 89, Julia, and 433 Eros. Several asteroids fit into some other category. 4 Vesta resembles a kind of meteorite called a basaltic achondrite, while 16 Psyche and 22 Calliope appear to be largely iron. The iron asteroids are interesting because geophysicists believe that the parent body of an object greatly enriched in iron must have been molten so as to differentiate, to separate out the iron from the silicates in the initial chaotic jumble of the elements in primordial times. On the other hand, for the organic molecules in carbonaceous meteorites to have survived at all, they must never have been raised to temperatures hot enough to melt rock or iron. Thus, different histories are implied for different asteroids, from the comparison of asteroidal and meteoritic properties, from laboratory studies of meteorites and computer projections back in time of asteroidal motions. It may one day be possible to reconstruct asteroid histories. Today, we do not even know whether they represent a planet that was prevented from forming because of the powerful gravitational perturbations of nearby Jupiter, or whether they are the remnants of a fully formed planet that somehow exploded. Most students of the subject incline to the former hypothesis because no one can figure out how to blow up a planet which is just as well. Eventually, we may be able to piece together the whole story. There may also be in-hand meteorites which do not come from asteroids. Perhaps there are fragments of young comets, or of the moons of Mars, or of the surface of Mercury, or of the satellites of Jupiter, sitting dusty and ignored in some obscure museum. But it is clear that the true picture of the origin of the meteorites is beginning to emerge. The Holy of Holies in the Temple of Diana at Ephesus has been destroyed. But the Kaaba has been carefully preserved, although there seems never to have been a true scientific examination of it. There are some who believe it to be a dark, stony, rather than metallic meteorite. Recently, 2 geologists have suggested, on admittedly quite fragmentary evidence, that it is instead an agate. Some Muslim writers believe that the color of the Kaaba was originally white, not black, and that the present color is due to its repeated handling. The official view of the keeper of the black stone is that it was placed in its present position by the patriarch Abraham and fell from a religious rather than an astronomical heaven, so that no conceivable physical test of the object could be a test of Islamic doctrine. It would nevertheless be of great interest to examine, with the full armory of modern laboratory techniques, a small fragment of the Kaaba. Its composition could be determined with precision. If it is a meteorite, its cosmic ray exposure age, the time spent from fragmentation to arrival on Earth, could be established, and it would be possible to test hypotheses of origin, such as, for example, the idea that some 5 million years ago, about the time of the origin of the Horninids, the Kaaba was chipped off an asteroid named 22 Calliope, orbited the Sun for ages of geological time, and then accidentally encountered the Arabian Peninsula 2,500 years ago. Unexpected discoveries are useful for calibrating pre-existing ideas. G.W.F. Hegel has had a very powerful imprint on professional philosophy of the 19th and early 20th centuries, and a profound influence on the future of the world because Karl Marx took him very seriously, although sympathetic critics have argued that Marx's arguments would have been more compelling had he never heard of Hegel. In 1799 or 1800, Hegel confidently stated, using presumably the full armamentarium of philosophy available to him, that no new celestial objects could exist within the solar system. 1 year later, the asteroid Ceres was discovered. Hegel then seems to have returned to pursuits less amenable to disproof. Chapter 16. The Golden Age of Planetary Exploration, the unquiet republic of the maze of planets, struggling fierce towards heaven's free wilderness. Percy Bysshe Shelley, Prometheus Unbound, 1820. Much of human history can, I think, be described as a gradual and sometimes painful liberation from provincialism, the emerging awareness that there is more to the world than was generally believed by our ancestors. With awesome ethnocentrism, tribes all over the earth called themselves the people or all men, relegating other groups of humans with comparable accomplishments to subhuman status. The high civilization of ancient Greece divided the human community into Hellenes and barbarians, the latter named after an uncharitable imitation of the languages of non-Greeks, barbar, that same classical civilization which in so many respects is the antecedent of our own, called its small inland sea the Mediterranean, which means the middle of the earth. For thousands of years, China called itself the Middle Kingdom, and the meaning was the same. China was at the center of the universe, and the barbarians lived in outer darkness. Such views or their equivalent are only slowly changing, and it is possible to see some of the roots of racism and nationalism in their pervasive early acceptance by virtually all human communities. But we live in an extraordinary time when technological advances and cultural relativism have made such ethnocentrism much more difficult to sustain. The view is emerging that we all share a common life raft in a cosmic ocean, that the Earth is, after all, a small place with limited resources, that our technology has now attained such powers that we are able to affect profoundly the environment of our tiny planet. This deprovincialization of mankind has been aided powerfully, I believe, by space exploration, by exquisite photographs of the Earth taken from a great distance showing a cloudy blue spinning ball set like a sapphire in the endless velvet of space, but also by the exploration of other worlds, which have revealed both their similarities and their differences to this home of mankind. We still talk of the world as if there were no others, just as we talk about the sun and the moon. But there are many others. Every star in the sky is a sun. The rings of Uranus represent millions of previously unsuspected satellites orbiting Uranus, the seventh planet. And as space vehicles have demonstrated so dramatically in the last decade and a half, there are other worlds, nearby, relatively accessible, profoundly interesting, and not a one closely similar to ours. As these planetary differences and the Darwinian insight that life elsewhere is likely to be fundamentally different from life here become more generally perceived, I believe they will provide a cohesive and unifying influence on the human family which inhabits for a time this unprepossessing world among an immensity of others. Planetary exploration has many virtues. It permits us to refine insights derived from such earthbound sciences as meteorology, climatology, geology, and biology, to broaden their powers and improve their practical applications here on Earth. It provides cautionary tales on the alternative fates of worlds. It is an aperture to future high technologies important for life here on Earth. It provides an outlet for the traditional human zest for exploration and discovery, our passion to find out, which has been to a very large degree responsible for our success as a species. And it permits us, for the first time in history, to approach with rigor, with a significant chance of finding out the true answers, questions on the origins and destinies of worlds, the beginnings and ends of life, and the possibility of other beings who live in the skies, questions as basic to the human enterprise as thinking is, as natural as breathing. Interplanetary unmanned spacecraft of the modern generation extend the human presence to bizarre and exotic landscapes far stranger than any in myth or legend. Propelled to escape velocity near the Earth, they adjust their trajectories with small rocket motors and tiny puffs of gas. They power themselves with sunlight and with nuclear energy. Some take only a few days to traverse the lake of space between Earth and Moon. Others may take a year to Mars, 4 years to Saturn, or a decade to traverse the inland sea between us and distant Uranus. They float serenely on pathways predetermined by Newtonian gravitation and rocket technology, their bright metal gleaming awash in the sunlight which fills the spaces between the worlds. When they arrive at their destinations, some will fly by, garnering a brief glimpse of an alien planet, perhaps with a retinue of moons, before continuing on farther into the depths of space. Others insert themselves into orbit about another world to examine it at close range, perhaps for years before some essential component runs down or wears out. Some spacecraft will make landfall on another world, decelerating by atmospheric friction or parachute drag or the precision firing of retrorockets before gently setting down somewhere else. Some landers are stationary, condemned to examine a single spot on a world awaiting exploration. Others are self-propelled, slowly wandering to a distant horizon, which holds no man knows what. And still others are capable of remotely acquiring rock and soil, a sample of another world, and returning it to the Earth. All these spacecraft have sensors that extend astonishingly the range of human perception. There are devices that can determine the distribution of radioactivity over another planet from orbit. that can feel from the surface the faint rumble of a distant planet quake deep below, that can obtain three-dimensional color or infrared images of a landscape like none ever seen on Earth. These machines are, at least to a limited degree, intelligent. They can make choices on the basis of information they themselves receive. They can remember with great accuracy a detailed set of instructions which, if written out in English, would fill a good-sized book. They are obedient and can be re-instructed by radio messages sent to them from human controllers on Earth, and they have returned, mostly by radio, a rich and varied harvest of information on the nature of the solar system we inhabit. There have been flybys, crash landers, soft landers, orbiters, automated roving vehicles, and unmanned returned sample missions from our nearest celestial neighbor, the Moon, as well as, of course, 6 successful and heroic manned expeditions in the Apollo series. There has been a flyby of Mercury, orbiters, entry probes, and landers on Venus, flybys, orbiters, and landers to Mars, and flybys of Jupiter and Saturn. Phobos and Deimos, the 2 small moons of Mars, have been examined close-up, and tantalizing images have been obtained of a few of the moons of Jupiter. We have caught our first glimpses of the ammonia clouds and great storm systems of Jupiter, the cold, salt-covered surface of its moon, Io, the desolate, crater-pocked, ancient and broiling Mercurian wasteland, and the wild and eerie landscape of our nearest planetary neighbor, Venus, where the clouds are composed of an acid rain that falls continuously but never patters the surface because that hilly landscape, illuminated by sunlight diffusing through the perpetual cloud layer, is everywhere at 900 degrees Fahrenheit. And Mars, what a puzzle, what a joy, enigma and delight is Mars, with ancient river bottoms, immense sculpted polar terraces, a volcano almost 80,000 feet high, raging windstorms, balmy afternoons, and an apparent initial defeat of our first pioneering effort to answer the question of questions, whether the planet harbors, now or ever, a homegrown form of life. There are on Earth only 2 spacefaring nations, only 2 powers so far able to send machines much beyond the Earth's atmosphere, the United States and the Soviet Union. The United States has accomplished the only manned missions to another body, the only successful Mars landers, and the only expeditions to Mercury, Jupiter, and Saturn. The Soviet Union has pioneered the automated exploration of the Moon, including the only unmanned rovers and return sample missions on any celestial objects, and the first entry probes and landers on Venus since the end of the Apollo program. Venus and the Moon have become to a certain degree Russian turf, and the rest of the solar system visited only by American space vehicles. While there is a certain degree of scientific cooperation between the 2 spacefaring nations, this planetary territoriality has come about by default rather than by agreement. There have in recent years been a set of very ambitious but unsuccessful Soviet missions to Mars, and the United States launched a modest but successful set of Venus orbiters and entry probes in 1978. The solar system is very large, and there is much to explore. Even tiny Mars has a surface area comparable to the land area of the Earth. For practical reasons, it is much easier to organize separate but coordinated missions launched by 2 or more nations than cooperative multinational ventures. In the 16th and 17th centuries, England, France, Spain, Portugal, and Holland each organized on a grand-scale missions of global exploration and discovery in vigorous competition. But the economic and religious motives of exploratory competition then do not seem to have their counterparts today, and there's every reason to think that national competition in the exploration of the planets will, at least for the foreseeable future, be peaceful. The lead times for planetary missions are very long. The design, fabrication, testing, integration, and launch of a typical planetary mission takes many years. A systematic program of planetary exploration requires a continuing commitment. The most celebrated American achievements on the Moon and planets, Apollo, Pioneer, Mariner, and Viking, were initiated in the 1960s. At least until recently, the United States has made only one major commitment to planetary exploration in the whole of the decade of the 1970s, The Voyager missions launched in the summer of 1977 to make the first systematic flyby examination of Jupiter, Saturn, their 25 or so moons, and the spectacular rings of the latter. This absence of new starts has produced a real crisis in the community of American scientists and engineers, responsible for the succession of engineering successes and high scientific discovery that began in 1962 with the Mariner 2 flyby of Venus. There has been an interruption in the pace of exploration. Workers have been laid off and drifted to quite different jobs, and there is a real problem in providing continuity to the next generation of planetary exploration. For example, the earliest likely response to the spectacularly successful and historic Viking exploration of Mars will be a mission that does not even arrive at the Red Planet before 1985, a gap in Martian exploration of almost a decade. And there is not the slightest guarantee that there will be a mission even then. This trend, a little like dismissing most of the shipwrights, sail weavers, and navigators of Spain in the early 16th century, shows some slight signs of reversal. Recently approved was Project Galileo, a middle 1980s mission to perform the first orbital reconnaissance of Jupiter and to drop the first probe into its atmosphere, which may contain organic molecules synthesized in a manner analogous to the chemical events which on Earth led to the origin of life. But the following year, Congress so reduced the funds available for Galileo that it is, at the present writing, teetering on the brink of disaster. In recent years, the entire NASA budget has been well below 1% of the federal budget. The funds spent on planetary exploration have been less than 15% of that. Requests by the planetary science community for new missions have been repeatedly rejected, as one senator explained to me. The public has not, despite Star Wars and Star Trek, written to Congress in support of planetary missions, and scientists do not constitute a powerful lobby. And yet, there are a set of missions on the horizon that combine extraordinary scientific opportunity with remarkable popular appeal. Solar sailing and comet rendezvous. In ordinary interplanetary missions, spacecraft are obliged to follow trajectories that require a minimum expenditure of energy. The rockets burn for short periods of time in the vicinity of Earth, and the spacecraft mainly coast for the rest of the journey. We have done as well as we have not because of enormous booster capability, but because of great skill with severely constrained systems. As a result, we must accept small payloads, long mission times, and little choice of departure or arrival dates. But just as on Earth, we are considering moving from fossil fuels to solar power. So it is in space. Sunlight exerts a small but palpable force called radiation pressure. A sail-like structure with a very large area for its mass can use radiation pressure for propulsion. By positioning the sail properly, we can be carried by sunlight both inwards toward and outwards away from the sun. With a square sail about half a mile on each side, but thinner than the thinnest mylar, interplanetary missions can be accomplished more efficiently than with conventional rocket propulsion. The sail would be launched into Earth orbit by the manned shuttlecraft, unfurled and strutted. It would be an extraordinary sight, easily visible to the naked eye as a bright point of light. With a pair of binoculars, detail on such a sail could be made out, perhaps even what on 17th century sailing ships was called the device, some appropriate graphic symbol, perhaps a representation of the planet Earth. Attached to the sail would be a scientific spacecraft designed for a particular application. One of the first and most exciting applications being discussed is a comet rendezvous mission, perhaps a rendezvous with Halley's Comet in 1986. Comets spend most of their time in interstellar space and should provide major clues on the early history of the solar system and the nature of the matter between the stars. Solar sailing to Halley's Comet might not only provide close-up pictures of the interior of a comet, about which we now know close to nothing, but also astonishingly return a piece of a comet to the planet Earth. The practical advantages and the romance of solar sailing are both evident in this example, and it is clear that it represents not just a new mission, but a new interplanetary technology. Because the development of solar sailing technology is behind that of ion propulsion, it is the latter that may propel us on our first missions to the comets. Both propulsion mechanisms have their place in future interplanetary travel, but in the long term, I believe solar sailing will make the greater impact. Perhaps by the early 21st century, there will be interplanetary regattas competing for the fastest time from Earth to Mars, Mars rovers. Before the Viking mission, no terrestrial spacecraft had successfully landed on Mars. There had been several Soviet failures, including at least one, which was quite mysterious and possibly attributable to the hazardous nature of the Martian landscape. Thus, both Viking 1 and Viking 2 were, after painstaking efforts, successfully landed in two of the dullest places we could find on the Martian surface. The lander stereo cameras showed distant valleys and other inaccessible vistas. The orbital cameras showed an extraordinarily varied and geologically exuberant landscape which we could not examine close-up with the stationary Viking lander. Further Martian exploration, both geological and biological, cries out for roving vehicles capable of landing in the safe but dull places and wandering hundreds or thousands of kilometers to the exciting places. Such a rover would be able to wander to its own horizon every day and produce a continuous stream of photographs of new landscapes, new phenomena, and very likely major surprises on Mars. Its importance would be improved still further if it operated in tandem with a Mars polar orbiter, which would geochemically map the planet, or with an unmanned Martian aircraft which would photograph the surface from very low altitudes. Titan lander. Titan is the largest moon of Saturn and the largest satellite in the solar system. See Chapter 13. It is remarkable for having an atmosphere denser than that of Mars and is probably covered with a layer of brownish clouds composed of organic molecules. Unlike Jupiter and Saturn, it has a surface on which we can land, and its deep atmosphere is not so hot as to destroy the organic molecules. A Titan entry probe and lander mission would probably be part of a Saturn orbital mission, which might also include a Saturn entry probe, Venus Orbital Imaging Radar. The Soviet Venera 9 and 10 missions have returned the first close-up photographs of the surface of Venus. Because of the permanent cloud pall, the surface features of Venus are not visible through Earth-bound optical telescopes. However, Earth-based radar and the radar system aboard the small Pioneer Venus orbiter have now begun to map Venus surface features and have revealed mountains and craters and volcanoes as well as stranger morphology. A proposed Venus orbital imaging radar would provide pole-to-pole radar pictures of Venus with much higher detail than can be achieved from the surface of the Earth, and would permit a preliminary reconnaissance of the Venus surface comparable to that achieved from Mars in 1971-72 by Mariner 9's solar probe. The Sun is the nearest star, the only one we are likely to be able to examine close up, at least for many decades. A near approach to the Sun would be of great interest, would help in understanding its influence on Earth, and would also provide vital additional tests of such theories of gravitation as Einstein's general theory of relativity. A solar probe mission is difficult for two reasons: the energy required to undo the Earth's and the probe's motion around the Sun so it can fall into the Sun, and the intolerable heating as the probe approaches the Sun. The first problem can be solved by launching the spacecraft out to Jupiter and then using Jupiter's gravitation to fling it into the Sun. Since there are many asteroids interior to Jupiter's orbit, this might possibly be a useful mission for studying asteroids as well. An approach to the second problem, at first sight remarkable for its naivete, is to fly into the Sun at night. On Earth, nighttime is of course merely the interposition of the solid body of the Earth between us and the Sun. Likewise, for a solar probe, there are some asteroids that come rather close to the Sun. A solar probe would approach the Sun in the shadow of a sun-grazing asteroid, meanwhile making observations of the asteroid as well. Near the point of closest approach of the asteroid to the Sun, the probe would emerge from the asteroidal shadow and plunge, filled with a fluid that resists heating, as deeply into the atmosphere of the Sun as it could until it melted and vaporized, atoms from the Earth added to the nearest star. Manned missions, as a rule of thumb, a manned mission costs from 50 to 100 times more than a comparable unmanned mission. Thus, for scientific exploration alone, unmanned missions employing machine intelligence are preferred. However, there may well be reasons other than scientific for exploring space: social, economic, political, cultural, or historical. The manned missions most frequently talked about are space stations orbiting the Earth and perhaps devoted to harvesting sunlight and transmitting it in microwave beams down to an energy-starved Earth and a permanent lunar base. Also being discussed are rather grand schemes for the construction of permanent space cities in Earth orbit, constructed from lunar or asteroidal materials. The cost of transporting materials from such low-gravity worlds as the Moon or an asteroid to Earth orbit is much less than transporting the same materials from our high-gravity planet. Such space cities might ultimately be self-propagating, new ones constructed by older ones. The costs of these large manned stations have not yet been estimated reliably, but it seems likely that all of them, as well as a manned mission to Mars, would cost in the $100 billion to $200 billion range. Perhaps such schemes will one day be implemented. There is much that is far-reaching and historically significant in them. But those of us who have fought for years to organize space ventures costing less than 1%, as much may be forgiven for wondering whether the required funds will be allocated and whether such expenditures are socially responsible. However, for substantially less money, an important expedition that is preparatory for each of these manned ventures could be mustered: an expedition to an Earth-crossing carbonaceous asteroid. The asteroids occur mostly between the orbits of Mars and Jupiter. A small fraction of them have trajectories that carry them across Earth's orbit, and occasionally within a few million miles of the Earth. Many asteroids are mainly carbonaceous, with large quantities of organic materials and chemically bound water. The organic matter is thought to have condensed in the very earliest stages of the formation of the solar system from interstellar gas and dust, some 6 billion years ago, and their study and comparison with cometary samples would be of extraordinary scientific interest. I do not think that materials from a carbonaceous asteroid are likely to be criticized in the same way that the Apollo-returned lunar samples were, as being only rocks. Moreover, a manned landing on such an object would be an excellent preparation for the eventual exploitation of resources in space. And finally, landing on such an object would be fun. Because the gravity field is so low, it would be possible for an astronaut to do a standing high jump of about 10 kilometers. These Earth-crossing objects, which are being discovered at a rapidly increasing pace, are called by a name selected long before manned spaceflight, the Apollo objects. They may or may not be the dead husks of comets, but whatever their origin, they are of great interest. Some of them are the easiest objects in space for humans to get to, using only the shuttle technology, which will be available in another few years. These sorts of missions I have outlined are well within our technological capability and require a NASA budget not much larger than the present one. They combine scientific and public interest, which very often share coincident objectives. Were such a program carried out, we would have made a preliminary reconnaissance of all the planets and most of the moons from Mercury to Uranus, made a representative sampling of asteroids and comets, and discovered the boundaries and contents of our local swimming hole in space. As the finding of rings around Uranus reminds us, major and unexpected discoveries are waiting for us. Such a program would also have made the first halting steps in the utilization of the solar system by our species, tapping the resources on other worlds, arranging for human habitation in space, and ultimately reworking or terraforming the environments of other planets so that human beings can live there with minimal inconvenience. Human beings will have become a multi-planet species. The transitional character of these few decades is evident. Unless we destroy ourselves, it is clear that humanity will never again be restricted to a single world. Indeed, the ultimate existence of cities in space and the presence of human colonies on other worlds will make it far more difficult for the human species to self-destruct. It is clear that we have entered, almost without noticing it, a golden age of planetary exploration. As in many comparable cases in human history, the opening of horizons through exploration is accompanied by an opening of artistic and cultural horizons. I do not imagine that many people in the 15th century ever wondered if they were living in the Italian Renaissance, but the hopefulness, the exhilaration, the opening of new ways of thought, the technological developments, the goods from abroad, and the deprovincialization of that age were then apparent to thoughtful men and women. We have the ability and the means, and I very much hope, the will for a comparable endeavor today, for the first time in human history. It is within the power of this generation to extend the human presence to the other worlds of the solar system, with awe for their wonders and a thirst for what they have to teach us. Part 5. The Future, Chapter 17. Will you walk a little faster? Will you walk a little faster? Said a whiting to a snail. There's a porpoise close behind us, and he's treading on my tail. Lewis Carroll, Alice in Wonderland. For much of human history we could travel only as fast as our legs would take us for any sustained journey, only a few miles an hour. Great journeys were undertaken, but very slowly. For example, 20,000 or 30,000 years ago, human beings crossed the Bering Strait and for the first time entered the Americas, gradually working their way down to the southernmost tip of South America, in Tierra del Fuego, where Charles Darwin encountered them on the memorable voyage of HMS Beagle. A concerted and single-minded effort of a dedicated band to walk from the straits between Asia and Alaska to Tierra del Fuego might have succeeded in a matter of years. In fact, it probably took thousands of years for diffusion of the human population to carry it so far south. The original motivation for traveling fast must have been, as the whiting's plaint reminds us, to escape from enemies and predators, or else to seek enemies and prey. A few thousand years ago, a remarkable discovery was made: the horse can be domesticated and ridden. The idea is a very peculiar one, the horse not having been evolved for humans to ride. If looked at objectively, it is only a little less silly than, say, an octopus riding a grouper. But it worked, and especially after the invention of the wheel and the chariot, horseback or horse-drawn vehicles represented for millennia the most advanced transportation technology available to the human species. One can travel as much as 10 or perhaps even 20 miles an hour with horse technology. We have emerged from horse technology only very recently, as for example our use of the term horsepower to rate automobile engines clearly shows. An engine rated at 375 horsepower has very roughly the pulling capacity of 375 horses. A team of 375 horses would make a very interesting sight. Arrayed in ranks of 5 horses each, the team would extend for about 2/10 of a mile in length, and would be astonishingly unwieldy. On many roads, the front rank of horse would be out of sight of the driver, and, of course, 375 horses do not travel 375 times as fast as one horse. Even with enormous teams of horses, the speed of transportation was only 10 or so times faster than when we could depend upon only our legs. Thus, the changes of the last century in transportation technology are striking. We humans have relied on legs for millions of years, horses for thousands. The internal combustion engine for less than 100, and rockets for transportation for a few decades. But these products of human inventive genius have enabled us to travel on the land and on the surface of the waters 100 times faster than we can walk, in the air 1,000 times faster, and in space more than 10,000 times faster. It used to be that the speed of communication was the same as the speed of transportation. There were a few fast communication methods earlier in our history. For example, signal flags or smoke signals, or even 1 or 2 attempts at arrays of signal towers with mirrors employed to reflect sunlight or moonlight from one to another. News of the recapture of the fortress of Győr by Hungarian commandos from the Turks was apparently conveyed to the Habsburg Emperor Rudolf II through such a device. The moonbeam telegraph, invented by the English astrologer John Dee, which apparently consisted of 10 relay stations placed at intervals of 40 kilometers between Győr and Prague. But with only a few exceptions, these methods proved impractical, and communications proceeded no faster than a man or a horse. This is no longer true. Communication by telephone and radio is now at the velocity of light, 186,000 miles per second, or about 2/3 of a billion miles per hour. This is not simply the latest advance, it is the last advance. So far as we know from Einstein's special theory of relativity, the universe is constructed in such a way, at least around here, that no material object and no information can be transmitted faster than the velocity of light. This is not an engineering barrier, like the so-called sound barrier, but a fundamental cosmic speed limit built deeply into the fabric of nature. Still, 2/3 of a billion miles per hour is fast enough for most practical purposes. What is remarkable is that in communications technology we have already reached this ultimate limit and have adapted to it so well. There are few people who emerge breathless and palpitating from a routine long-distance telephone call, astounded at the speed of transmission. We take this almost instantaneous means of communication for granted, yet in transportation technology, while we have not achieved speeds at all approaching the velocity of light, we find ourselves colliding with other limits, physiological and technological. Our planet turns. When it is midday at one spot on the Earth, it is the dead of night on the other side. The Earth has therefore been conveniently arranged into 24 time zones of more or less equal width, making strips of longitude around the planet. If we fly very fast, we create situations our minds can accommodate, but our bodies can abide only with great difficulty. It is a commonplace today to fly in relatively short trips westward and arrive before we leave. For example, when we take less than an hour to fly between 2 points separated by one time zone. When I take a 9 p.m. flight to London, it is already tomorrow at my destination. When I arrive after a 5 or 6 hour flight, it is late at night for me, but the beginning of the business day at my destination. My body senses something wrong. My circadian rhythms go awry, and it takes a few days to get adjusted to English time. A flight from New York to New Delhi is, in this respect, even more vexing. I find it very interesting that two of the most gifted and inventive science fiction writers of the 20th century, Isaac Asimov and Ray Bradbury, both refuse to fly. Their minds have come to grips with interplanetary and interstellar spaceflight, but their bodies rebel at a DC-3. The rate of change in transportation technology has simply been too great for many of us to accommodate conveniently. Much stranger possibilities are now practical. The Earth turns on its axis once every 24 hours. The circumference of the Earth is 25,000 miles. Thus, if we were able to travel at 25,024 equals 1,040 miles per hour, we could just compensate for the Earth's rotation, and traveling westward at sunset could maintain ourselves at sunset for the entire journey, even if we circumnavigated the planet. In fact, such a journey would also maintain us at the same local time as we journey westward from time zone to time zone until we cross the international dateline and plunge precipitously into tomorrow. But 1,040 miles per hour is less than twice the speed of sound, and there are worldwide dozens of kinds of aircraft, chiefly military, that are capable of such speeds. Some commercial aircraft, such as the Anglo-French Concorde, have comparable capabilities. The question, I think, is not, can we go faster, but do we have to? There has been concern expressed, some of it, in my view, quite appropriately, about whether the conveniences supersonic transports provide can possibly compensate for their overall cost and their ecological impact. Most of the demand for high-speed, long-distance travel comes from businessmen and government officials who need to have conferences with their opposite numbers in other states or countries. But what is really involved here is not the transportation of material, but the transportation of information. I think much of the necessity for high-speed transport could be avoided if the existing communications technology were better used. I have many times participated in government or private meetings in which there were, say, 20 participants, each of whom was paid $500 for transportation and living expenses merely to attend the meeting, the cost of which was therefore $10,000 just to get the participants together. But all the participants ever exchange is information: video phones, leased telephone lines, and facsimile reproducers to transmit paper copies of notes and diagrams would, I believe, serve as well or even better. There is no significant function of such a meeting, including private discussions among the participants in the corridor, that cannot be performed less expensively and at least equally conveniently with communications rather than transportation technology. There are certainly advances in transportation that seem to me promising and desirable, Vertical takeoff and landing VTOL aircraft are a remarkable boon for isolated and remote communities in case of medical or other emergencies. But the recent advances in transportation technology that I find most appealing are rubber fins for snorkel and scuba diving and hang gliders. These are technological advances much in the spirit of those sought by Leonardo da Vinci in mankind's first serious technological pursuit of flight in the 15th century. They permit an individual human being with little more than his own resources to enter at a speed that is adequately exhilarating another medium entirely. With the depletion of fossil fuels, I think it very likely that automobiles powered by internal combustion engines will be with us for at most a few decades longer. The transportation of the future will simply have to be different. We can imagine quite comfortable and adequately speedy steam, solar, fuel cell, or electric ground vehicles, generating very little pollution and employing a technology comfortably accessible to the user. Many responsible medical experts are concerned that we in the West, and increasingly even in developing countries, are becoming too sedentary. Driving an automobile exercises very few muscles. The demise of the automobile surely has many positive aspects when viewed in the long run, one of which is a return to the oldest transportation mechanism, walking, and to bicycling, which is in many ways the most remarkable. I can easily imagine a healthy and stable future society in which walking and bicycling are the primary means of transportation, with pollution-free low-speed ground cars and railed public transportation systems widely available, and the most sophisticated transportation devices used relatively rarely by the average person. The one application of transportation technology that requires the most sophisticated technology is spaceflight. The returns in immediate practical benefits, scientific knowledge, and appealing exploration provided by unmanned spaceflight are very impressive, and I would expect an increasing rate of space vehicle launches by many nations in the next few decades, using more subtle forms of transportation, as described in the previous chapter. Nuclear electric, solar sailing, and ion propulsion schemes have been proposed and are to some degree under development. As nuclear fusion power plants are developed for Earth-bound applications in a few decades, there should be a development of fusion space engines as well. The gravitational forces of planets have already been used to give velocities otherwise unobtainable. Mariner 10 reached Mercury only because it flew so close to Venus that Venus's gravity provided a significant boost in speed. And Pioneer 10 was boosted into an orbit that will carry it out of the solar system entirely, only because of a close passage by the giant planet Jupiter. In a way, Pioneer 10 and 11 and Voyager 1 and 2 are our most advanced transportation systems. They are leaving the solar system at a speed of roughly 43,000 miles per hour, carrying messages to anyone who may intercept them out there in the dark of the night sky from the people of the Earth, who only a little while ago could travel no faster than a few miles per hour. In manned Earth orbital flights, still other problems arise. Consider a religious Muslim or Jew circling the Earth once every 90 minutes. Is he obligated to celebrate the Sabbath every 7th orbit? Space flight provides access to environments very different from those in which we and our customs have grown up. Chapter 18, Via Cherry Tree, to Mars, oh, for a muse of fire, that would ascend. The brightest heaven of invention, William Shakespeare, Henry V prologue. It is a lazy afternoon in an exquisite New England autumn. In about 10 weeks, it will be January 1st, 1900, and your diary, into which are committed the events and ideas of your young life, will never again bear an entry with a date in the 1800s. You have just turned 17. You are looking forward to being a sophomore in high school, but you are now at home, in part because your mother is seriously ill with tuberculosis, and in part because of your own chronic stomach pains. You are bright, with a certain flair for the sciences, but no one has ever indicated that you might have an extraordinary talent. You are complacently viewing the New England countryside from the limb of a tall old cherry tree which you have climbed, when suddenly you are struck by an idea, an overpowering and compelling vision that it might be possible, in fact, rather than in fancy, to voyage to the planet Mars. When you descend from the cherry tree, you know that you are a very different boy from the one who climbed it. Your life's work is clearly set out for you, and for the next 45 years your dedication never wavers. You have been smitten by the vision of flight to the planets. You are deeply moved and quietly awed by the vision in the cherry tree. The next year, on the anniversary of that vision, you climb the tree again to savor the joy and meaning of the experience, and forever, after you make a point in your diary of calling the anniversary of that experience Anniversary Day, every October 19th until your death in the middle 1940s, by which time your theoretical insights and practical innovations have solved essentially all technological impediments to interplanetary flight. 4 years after your death, a WAC corporal mounted on the nose of a V-2 is successfully fired to an altitude of 250 miles, for all practical purposes to the threshold of space. All essential design elements of the WAC corporal and the V-2 and the very concept of the multiple staging of rockets have been worked out by you. A quarter of a century later, unmanned space vehicles will have been launched to all the planets known to ancient man. A dozen men will have set foot on the moon, and 2 exquisitely miniaturized spacecraft named Viking will be on their way to Mars to attempt the first search for life on that planet. Robert H. Goddard never questioned or equivocated on the resolve he made in the cherry tree on the farm of his great-aunt Tsarina in Worcester, Massachusetts. While there were others who had comparable visions, notably Konstantin Eduardovich Tsiolkovsky in Russia, Goddard represented a unique combination of visionary dedication and technological brilliance. He studied physics because he needed physics to get to Mars. He was for many years professor of physics and chairman of the physics department at Clark University in his hometown of Worcester. In reading the notebooks of Robert Goddard, I am struck by how powerful his exploratory and scientific motivations were, and how influential speculative ideas, even erroneous ones, can be on the shaping of the future. In the few years surrounding the turn of the century, Goddard's interests were profoundly influenced by the idea of life on other worlds. He was intrigued by the claims of W.H. Pickering of the Harvard College Observatory that the moon has a perceptible atmosphere, active volcanism, variable frost patches, and even changing dark markings which Pickering interpreted variously as the growth of vegetation or even as the migration of enormous insects across the floor of the crater Eratosthenes. Goddard was captivated by the science fiction of H.G. Wells and Garrett P. Serviss, particularly the latter's Edison's Conquest of Mars, which Goddard reported, gripped my imagination tremendously. He attended and enjoyed lectures by Percival Lowell, who was an eloquent advocate of the proposition that intelligent beings inhabit the planet Mars. And yet, through all of this, while his imagination was intensely stimulated, Goddard managed to retain a sense of skepticism very rare in young people given to interplanetary epiphanies high up in cherry trees. The actual conditions may be entirely different from those which Professor Pickering suggests. The only antidote for fallacies is, in a word, to take nothing for granted. On January 20, 1902, we know from Goddard's notebook, he wrote an essay on the habitability of other worlds. The paper had not been found among Goddard's writings, which seemed to me a great pity, since it might have given us a better understanding of the extent to which the search for extraterrestrial life was a prime motive in Goddard's life work. In his early postdoctoral years, Goddard successfully pursued an experimental verification of his ideas on solid and liquid-fueled rocket flight. In this endeavor, he was supported principally by 2 men, Charles Greeley Abbott and George Ellery Hale. Abbott was then a young scientist at the Smithsonian Institution, of which he later became secretary, the quaint designation by which the executive officer of that organization is still known. Hale was the driving force behind American observational astronomy at the time. Before he died, he had founded the Yerkes, Mount Wilson, and Mount Palomar observatories, each housing in its time the largest telescope in the world. Both Abbott and Hale were solar physicists, and it seems clear that both had been captured by the young Goddard's vision of a rocket sailing free above the obscuring blanket of the Earth's atmosphere, able to view the sun and stars unimpeded, but Goddard soared far beyond this daring vision. He talked and wrote of experiments on the composition and circulation of the upper atmosphere of the Earth, of performing gamma-ray and ultraviolet observations of the sun and stars from above the Earth's atmosphere. He conceived of a space vehicle passing 1,000 miles above the surface of Mars by a curious historical accident, just the low point in the orbits of the Mariner 9 and Viking spacecraft. Goddard calculated that a reasonably sized telescope at such a vantage point would be able to photograph features tens of meters across on the surface of the red planet, which is the resolution of the Viking orbiter cameras. He conceived of slow interstellar flight at velocities and timescales just equivalent to that of the Pioneer 10 and 11 spacecraft. Our first interstellar emissaries, Goddard's spirit soared higher still. He conceived, not casually, but quite seriously, of solar-powered spacecraft, and in a time when any practical application of nuclear energy was publicly ridiculed, nuclear propulsion for spacecraft over vast interstellar distances. Goddard imagined a time in the far distant future when the sun has grown cold and the solar system become uninhabitable, when manned interstellar spacecraft would be outfitted by our remote descendants to visit the stars, not merely the nearby stars, but also remote star clusters in the Milky Way galaxy. He could not imagine relativistic spaceflight, and so hypothesized a method of suspended animation of the human crew, or even more imaginative, a means of sending the genetic material of human beings, which would automatically, at some very distant time, be allowed to recombine and produce a new generation of people. With each expedition, he wrote, there should be taken all the knowledge, literature, art in a condensed form and description of tools, appliances, and processes in as condensed, light, and indestructible a form as possible, so that the new civilization could begin where the old ended. These final speculations, entitled The Last Migration, were sealed in an envelope with instructions to be read only by an optimist. And that he surely was not a Pollyanna who chooses to ignore the problems and evils of our times, but rather a man committed to the improvement of the human condition and the creation of a vast prospect for the future of our species. Goddard's dedication to Mars was never far from his mind. In the wake of one of his first experimental successes, he was induced to write a press release on the details of his launch and its ultimate significance. He wished to discuss spacecraft to Mars, but was dissuaded on the ground that this was too fantastic. As a compromise, he talked about sending a quantity of magnesium flash powder, which would make a visible bright flare on the moon when it landed. This caused a sensation in the press. Goddard was for many years after disparagingly referred to as the Moon Man, and he remained rueful about his relations with the press ever after. An editorial in the New York Times which criticized Goddard for having forgotten that a rocket will not work in the vacuum of space because it has nothing to push against may have contributed to his unease. The Times discovered Newton's third law of motion and retracted its error only in the age of Apollo. Goddard mused, from that day, the whole thing was summed up in the public mind, in the words moon rocket. And thus it happened that in trying to minimize the sensational side, I had really made more of a stir than if I had discussed transportation to Mars, which would probably have been considered as ridiculous by the press representative and doubtless never mentioned. Goddard's notebooks are not filled with psychological insights. That was not, at least not very much, the spirit of the times in which he lived. But there is a remark in Goddard's notebooks that can be only a flash of poignant self-insight. God pity a one-dream man. That surely is what Goddard was. He knew great satisfaction in seeing the advances in rocket technology, but it must have been agonizingly slow. There are so many letters from Abbott urging faster progress, and so many responses from Goddard citing practical impediments. Goddard never lived to see the beginning of rocket astronomy and high-altitude meteorology, much less flights to the moon or planets. But all these things are happening because of what are very clearly the technological fruits of Goddard's genius. October 19, 1976, was the 77th anniversary day of the Martian vision of Robert H. Goddard. On that day, there were 2 functioning orbiters and 2 working landers on Mars, the Viking spacecraft whose origins can be traced with utter confidence back to a boy in a cherry tree in a New England autumn in 1899. Among its many other objectives, Viking had the task of checking out the possibility of life on Mars, the prospect that was so powerful a motivation for Goddard so many years before. Curiously, we are still not sure what the Viking biology results mean. Some think that microbial life may have been discovered, others think it unlikely. It is clear that a major program of future exploration of Mars will be required to understand just where in cosmic evolution this neighboring world lies and what its connection is with the state of evolution on our own planet. From its earliest stages, rocket technology developed because of an interest in life on other worlds. And now that we have landed on Mars, obtained tantalizing and enigmatic biological results. The follow-on missions, roving vehicles, and returned sample canisters, in turn, require further developments in spacecraft technology, a mutual causality that I think Goddard would have appreciated. In a commencement address at Clark University on May 18, 1978, I made some similar remarks. Dorothy Mosikowski in the rare book room at Clark's Goddard Memorial Library then searched for and found this little essay which had been listed as lost. In it, we discover that Goddard was attracted to but cautious about the possibility of life on Mars, certain of the existence of extrasolar planetary systems, and deduced that among these countless planets there are conditions of heat and light equivalent to those we experience. And if this is the case, and the planet is near our age and size, there may very likely exist human beings like ourselves, probably with strange costumes and still stranger manners. But he also says, it is for the distant future to answer if we will ever realize truth from our surmises. Although, remarkably, he was in Worcester in the year 1909 when Sigmund Freud and Carl Gustav Jung gave the first comprehensive discussion in the English language of those institutionalized insights called psychoanalysis. Many American psychiatrists got their first glimpses of the subject from Freud's Clark University lectures. One wonders if the middle-aged bearded Viennese physician and the young mustachioed American physics graduate student nodded to each other in passing on the Clark University campus on their way to their separate destinies. Chapter 19, Experiments. In Space. We ever long for visions of beauty. We ever dream of unknown worlds. Maxim Gorky, until relatively. Recently, astronomy suffered from a serious impediment and remarkable peculiarity. It was the only thoroughly non-experimental science. The materials of study were all up there, and we and our machines were all down here. No other science was so severely constrained. In physics and chemistry, of course, all is forged on the anvil of experiment, and those who doubt a given conclusion are free to perform a wide range of alternative manipulations of matter and energy in an attempt to extract contradictions or alternative explanations. Evolutionary biologists, even those of very patient temperaments, cannot afford to wait a few million years to observe one species evolve into another. But experiments on common amino acid sequences, enzyme structure, nucleic acid codes, chromosomal banding, and anatomy, physiology, and behavior make a compelling case for the fact that evolution has occurred and clearly show which plant or animal groups, such as human beings, are related to which others, such as the great apes. It is true that geophysicists studying the deep interior of the Earth cannot travel to the Wietrich discontinuity between core and mantle, or just yet to the Mohorovičić discontinuity between mantle and crust. But batholiths extruded from the deep interior can be found here and there on the surface and examined. The geophysicists have relied largely on seismic data, and here, like astronomers, they could not force the favors of nature, but were compelled to await their voluntary bestowal. For example, in a seismic event situated on the other side of the Earth so that one of two nearby seismometers would be in the shadow of the Earth's core and the other not. But impatient seismologists can and have set off their own chemical and nuclear explosions to ring Earth like a bell. And there are intriguing recent hints that it may be possible to turn earthquakes on and off. Those geologists intolerant of inferential reasoning could always go to the field and examine contemporary erosion processes, but there was no exact astronomical equivalent of the hard rock geologist. We have been restricted to the electromagnetic radiation reflected and emitted by astronomical objects. We have not been able to examine pieces of stars or planets in our laboratories, or to fly into such objects to examine them in situ. Ground-based passive observations have restricted us to a narrow fraction of the conceivable data on astronomical objects. Our position has been much worse than that of the fabled 6 blind men in pursuit of the nature of the elephant. It has been more like one blind man in a zoo. We were standing there for centuries stroking a left hind foot. It is not surprising that we did not deduce tusks, or notice that the foot did not belong to an elephant at all. If, by accident, the orbital plane of the double star was in our line of sight, we would see eclipses, otherwise not. We could not move to a position in space from which the eclipses could be observed. If we were observing a galaxy when a supernova was exploding, we could examine the supernova spectrum, otherwise not. We do not have the ability to perform experiments on supernova explosions, which is just as well. We could not examine in the laboratory the electrical, thermal, mineralogical, and organic chemical properties of the lunar surface. We were restricted to inferences from the visible light reflected and the infrared and radio waves emitted by the moon, aided by occasional natural experiments such as eclipses and lunations. But all that is gradually changing. Ground-based astronomers have, at least for nearby objects, an experimental tool, radar astronomy. At our convenience, at our choice of frequency, polarization, bandpass, and pulse length, we can irradiate a nearby moon or planet with microwaves and examine the returned signal. We can wait for the object to rotate underneath the beam and illuminate some other place on its surface. Radar astronomy has delivered a host of new conclusions on the rotation periods of Venus and Mercury and related problems in the tidal evolution of the solar system. On the craters of Venus, the fragmented surface of the moon, the elevations of Mars, and the size and composition of the particles in the rings of Saturn. And radar astronomy is just beginning. We are still restricted to low altitudes, and for the outer solar system to sun-facing hemispheres. But with the newly resurfaced Arecibo telescope of the National Astronomy and Ionosphere Center in Puerto Rico, we will be able to map the surface of Venus to a resolution of 1 kilometer better than the best ground-based photographic resolution of the lunar surface and obtain a host of new information on the asteroids, the Galilean satellites of Jupiter, and the rings of Saturn. For the first time, we are poking around in cosmic stuff, electromagnetically fingering the solar system. A much more powerful technique of experimental as opposed to observational astronomy is spacecraft exploration. We can now travel into the magnetospheres and atmospheres of the planets. We can land on and rove over their surfaces. We can collect material directly from the interplanetary medium. Our first preliminary steps into space have shown us a wide range of phenomena we never knew existed. The Van Allen trapped particle belts of the Earth, the mass concentrations beneath the circular Maria of the Moon, the sinuous channels and great volcanoes of Mars, the cratered surfaces of Phobos and Deimos. But what I am most struck by is that before the advent of space vehicles, astronomers did very well, hamstrung though they were. The interpretations of the observations available to them were remarkably good. Space vehicles are ways of checking out the conclusions drawn inferentially by astronomers, a method of determining whether astronomical deductions on very distant objects so far away as to be entirely inaccessible by space vehicles in the near future, should be believed. One of the earliest major debates in astronomy was on whether the Earth or the Sun was at the center of the solar system. The Ptolemaic and Copernican views explain the apparent motion of the moon and planets to comparable precision for the practical problem of predicting the positions of the moon and planets as seen from the surface of the Earth. It hardly mattered which hypothesis was adopted. But the philosophical implications of the geocentric and heliocentric hypotheses were quite different, and there were ways of finding out which was right. In the Copernican view, Venus and Mercury should go through phases like the moon. In the Ptolemaic view, they should not. When Galileo, using one of the first astronomical telescopes, observed a crescent Venus, he knew he had vindicated the Copernican hypothesis. But space vehicles provide a more immediate test. According to Ptolemy, The planets are affixed to immense crystalline spheres. But when Mariner 2 or Pioneer 10 penetrated the locales of Ptolemy's supposed crystal spheres, no impediment to their motion was detected, and, more directly, the acoustic and other micrometeorite detectors heard not even the faintest whisper of tinkling, much less the sound of smashed crystal. There's something very satisfying and immediate about this sort of test. There are probably no Ptolemyists in our midst, but there might be some with lingering doubts about whether Venus could not be made to go through phases in some modified geocentric hypothesis. Those people can now rest easy before space vehicles. The German astrophysicist Ludwig Biermann was intrigued by the observations of the apparent acceleration of bright knots in the well-developed tails of comets passing through the inner solar system. Biermann showed that the radiation pressure of sunlight was inadequate to account for the observed acceleration, and made the novel suggestion that there were charged particles streaming out from the sun which, in interaction with the comet, produced the observed acceleration. Well, maybe. But could it not be equally due to, say, chemical explosions in the nucleus of the comet, or some other explanation? But the first successful interplanetary spacecraft, Mariner 2, in the course of its flyby of Venus, determined the existence of a solar wind with velocities and electron densities in just the range that Biermann had calculated would be necessary to accelerate his knots. In the same period, there was a debate on the nature of the solar wind. In one view, that of Eugene Parker of the University of Chicago, it was caused by hydrodynamical flow out from the sun. In another view, by evaporation from the top of the solar atmosphere. In the hydrodynamic explanation, there should be no fractionation by mass. That is, the atomic composition of the solar wind should be the same as that of the sun. But in the evaporation hypothesis, the lighter atoms escape the sun's gravity more easily, and heavy elements should be preferentially depleted in the solar wind. Interplanetary spacecraft have found that the ratio of hydrogen to helium in the solar wind is precisely that in the sun, and have thereby provided convincing support for the hydrodynamic hypothesis of the origin of the solar wind. In these examples from solar wind physics, we find that the spacecraft experiments provided the means for making critical judgments among competing hypotheses. In retrospect, we find that there were astronomers such as Biermann and Parker who were right for the right reasons, but there were others equally bright who disbelieved them and might have gone on disbelieving them had not the critical spacecraft experiments been performed. What is remarkable is not that there were alternative hypotheses which we now see to be incorrect, but rather that on the basis of the very meager data available, anyone was smart enough to divine the correct answer, inferentially using intuition, physics, and common sense. Before the Apollo missions, the uppermost layer of the lunar surface could be examined by visible, infrared, and radio observations during both lunations and eclipses, and the polarization of sunlight reflected off the lunar surface had been measured. From these observations, Thomas Gold of Cornell University prepared a dark powder which, in the laboratory, reproduced the observed properties of the lunar surface very well. This gold dust can even be purchased for a modest price from the Edmund Scientific Company. A naked eye comparison of lunar dust returned by Apollo astronauts with gold dust shows them to be almost indistinguishable in particle size distribution, and in electrical and thermal properties, they are a very close match. However, their chemical compositions are very different. Gold dust is primarily Portland cement, charcoal, and hairspray. The moon has a less exotic composition. But the observed lunar properties available to gold before Apollo did not strongly depend on the chemical composition of the lunar surface. He was able to deduce very well that fraction of the lunar surface properties which was relevant to pre-1969 observations of the moon. From the study of the available radio and radar data, we were able to deduce the high surface temperature and high surface pressures of Venus before the first Soviet Venera entry probe made in situ observations on the atmosphere, and subsequent Venera probes on the surface. Likewise, we correctly deduced the existence of elevation differences on Mars as great as 20 kilometers, although we were mistaken in thinking that dark areas were systematically at high elevations on the planet. Perhaps one of the most interesting such confrontations of astronomical inference with spacecraft observations is the case of the magnetosphere of Jupiter. In 1955, Kenneth Franklin and Bernard Burke were testing a radio telescope near Washington, D.C., intended for mapping galactic radio emission at a frequency of 22 Hz. They noticed irregularly recurring interference on their records, which they at first thought was due to some conventional source of radio noise, such as a faulty ignition system on some nearby tractor, but they soon discovered that the timing of the interference corresponded perfectly well with transits overhead of the planet Jupiter. They had discovered that Jupiter was a powerful source of decameter radio emission. Subsequently, Jupiter was found to be a bright source at decimeter wavelengths as well, but the spectrum was very peculiar. At a wavelength of a few centimeters, very low temperatures of around 140 degrees K were found, temperatures comparable to those uncovered for Jupiter at infrared wavelengths, but at decimeter wavelengths up to 1 meter, the brightness temperature increased very rapidly with wavelength approaching 100,000 degrees K. This was too high a temperature for thermal emission, the radio radiation that all objects put out, simply because they are at a temperature above absolute zero. Frank Drake, then, of the National Radio Astronomy Observatory, proposed in 1959 that this spectrum implied that Jupiter was a source of synchrotron emission, the radiation that charged particles emit in their direction of motion when traveling close to the speed of light. On Earth, synchrotrons are convenient devices used in nuclear physics for accelerating electrons and protons to such high velocities, and it is in synchrotrons that such emission was first generally studied. Synchrotron emission is polarized, and the fact that the decimeter radiation from Jupiter is also polarized was an additional point in favor of Drake's hypothesis. Drake suggested that Jupiter was surrounded by a vast belt of relativistic charged particles similar to the Van Allen radiation belt around the Earth, which had then just been discovered. If so, the decimeter emitting region should be much larger than the optical size of Jupiter. But conventional radio telescopes have inadequate angular resolution to make out any spatial detail whatever at the range of Jupiter. A radio interferometer can achieve such resolution, however. In the spring of 1960, very soon after the suggestion was made, V. Radhakrishnan and his colleagues at the California Institute of Technology employed an interferometer composed of two 90-foot diameter antennas mounted on railroad tracks and separable by almost 1/3 of a mile. They found that the region of decimeter emission around Jupiter was considerably larger than the ordinary optical disk of Jupiter, confirming Drake's proposal. Subsequent higher-resolution radio interferometry has shown Jupiter to be flanked by two symmetric ears of radio wave emission with the same general configuration as the Van Allen radiation belts of the Earth. The general picture has evolved that on both planets, electrons and protons from the solar wind are trapped and accelerated by the planetary magnetic dipole field and are constrained to spiral along the planet's lines of magnetic force, bouncing from one magnetic pole to the other. The radio-emitting region around Jupiter is identified with its magnetosphere. The stronger the magnetic field, the farther out from the planet the boundary of the magnetic field will be. In addition, matching the observed radio spectrum from synchrotron emission theory specifies a magnetic field strength. The field strength could not be specified to very great precision, but most estimates from radio astronomy in the late 1960s and early 1970s were in the range of 5 to 30 Gauss, some 10 to 60 times the surface magnetic field of the Earth at the equator. Radhakrishnan and colleagues also found that the polarization of the decimeter waves from Jupiter varied regularly as the planet rotated, as if the Jovian radiation belts were wobbling with respect to the line of sight. They proposed that this was due to a 9-degree tilt between the axis of rotation and the magnetic axis of the planet, not very different from the displacement between the north geographic and the north magnetic poles of Earth. Subsequent studies of the decimeter and decameter emission by James Warwick of the University of Colorado and others suggested that the magnetic axis of Jupiter is displaced a small fraction of a Jupiter radius from the axis of rotation, quite different from the terrestrial case where both axes intersect at the center of the Earth. It was also concluded that the south magnetic pole of Jupiter was in the northern hemisphere, that is, that a north-seeking compass on Jupiter would point south. There is nothing very bizarre about this suggestion. The Earth's magnetic field has flipped its direction many times during its history, and it is only by definition that the North Magnetic Pole is in the northern hemisphere of the Earth at the present time. From the intensity of the decimeter and decameter emission, astronomers also calculated what the energies and fluxes of electrons and protons in the Jovian magnetosphere might be. This is a very rich array of conclusions. But all of it is remarkably inferential. The whole elaborate superstructure was put to a critical test on December 3, 1973, when the Pioneer 10 spacecraft flew through the Jovian magnetosphere. There were magnetometers aboard which measured the strength and direction of the magnetic field at various positions in the magnetosphere, and there was a variety of charged particle detectors which measured energies and fluxes of the trapped electrons and protons. It is a stunning fact that virtually every one of the radio astronomical inferences was roughly confirmed by Pioneer 10 and its successor spacecraft, Pioneer 11. The surface equatorial magnetic field on Jupiter is about 6 Gauss and larger at the poles. The inclination of the magnetic to the rotational axis is about 10 degrees. The magnetic axis can be described as apparently displaced about 1/4 of a Jovian radius from the center of the planet. Farther out than 3 Jupiter radii, the magnetic field is approximately that of a dipole. Closer in, it is much more complex than had been estimated. The flux of charged particles received by Pioneer 10 along its trajectory through the magnetosphere was considerably larger than had been anticipated, but not so large as to inactivate the spacecraft. The survival of Pioneer 10 and 11 through the Jovian magnetosphere was more the result of good luck and good engineering than of the accuracy of pre-Pioneer magnetospheric theories. In general, the synchrotron theory of the decimeter emission from Jupiter is confirmed. All those radio astronomers turn out to have known what they were doing. We can now believe with much greater confidence than heretofore deductions made from synchrotron physics and applied to other, more distant and less accessible comic objects such as pulsars, quasars, or supernova remnants. In fact, the theories can now be recalibrated and their accuracy improved. Theoretical radio astronomy has for the first time been put to a critical experimental test, and it has passed with flying colors. Of the many major findings by Pioneer 10 and 11, I think this is its greatest triumph. It has confirmed our understanding of an important branch of cosmic physics. There is much about the Jovian magnetosphere and radio emissions that we still do not understand. The details of the decameter emissions are still deeply mysterious. Why are there localized sources of decameter emission on Jupiter probably less than 100 kilometers in size? What are these emission sources? Why do the decameter emission regions rotate about the planet with a very high time precision, better than 7 significant figures, but different from the rotation periods of visible features in the Jovian clouds? Why do the decameter bursts have a very intricate submillisecond fine structure? Why are the decameter sources beamed, that is, not emitting in all directions equally? Why are the decameter sources intermittent, that is, not on all the time? These mysterious properties of the Jovian decameter emission are reminiscent of the properties of pulsars. Typical pulsars have magnetic fields 1,000,000,000,000 times larger than Jupiter's. They rotate 100,000 times faster. They are 1,000th as old. They are 1,000 times more massive. The boundary of the Jovian magnetosphere moves at less than 1,000th of the speed of the light cone of a pulsar. Nevertheless, it is possible that Jupiter is a kind of pulsar that failed, a local and quite unprepossessing model of the rapidly rotating neutron stars, which are one end product of stellar evolution. Major insights into the still baffling problems of pulsar emission mechanisms and magnetosphere geometries may follow from close-up spacecraft observation of Jovian decameter emission, for example. By NASA's Voyager and Galileo missions, experimental astrophysics is developing rapidly. In another few decades, at the very latest, we should see direct experimental investigation of the interstellar medium. The heliopause, the boundary between the region dominated by the solar wind and that dominated by the interstellar plasma, is estimated to lie at not much more than 100 astronomical units, 9.3 billion miles, from the Earth. Now, if there were only a local solar system quasar and a backyard black hole, nothing fancy, you understand. Just little baby ones, we might, with in situ spacecraft measurements, check out the greater body of modern astrophysical speculation. If we can judge by past experience, each future venture in experimental spacecraft astrophysics will find that A, a major school of astrophysicists was entirely right. B, no one agreed on which school it was that was right until the spacecraft results were in, and C, an entire new corpus of still more fascinating and fundamental problems was unveiled by the space vehicle results, with the sole exception of the meteorites, see Chapter 15. I have discussed these successful inferences and their spacecraft confirmations in Chapters 12, 16, and 17 of The Cosmic Connection. Chapter 20, In Defense of Robots, William Shakespeare. Thou comest in such a questionable shape that I will speak to thee. Hamlet, Act I, Scene 4, the word robot, first introduced by the Czech writer Karel Čapek, is derived from the Slavic root for worker, but it signifies a machine rather than a human worker. Robots, especially robots in space, have often received derogatory notices in the press. We read that a human being was necessary to make the terminal landing adjustments on Apollo 11, without which the first manned lunar landing would have ended in disaster. That a mobile robot on the Martian surface could never be as clever as astronauts in selecting samples to be returned to Earth-bound geologists, and that machines could never have repaired, as men did, the Skylab sunshade so vital for the continuance of the Skylab mission. But all these comparisons turn out, naturally enough, to have been written by humans. I wonder a small self-congratulatory element, a whiff of human chauvinism, has not crept into these judgments. Just as whites can sometimes detect racism and men can occasionally discern sexism, I wonder whether we cannot here glimpse some comparable affliction of the human spirit, a disease that as yet has no name. The word anthropocentrism does not mean quite the same thing. The word humanism has been preempted by other and more benign activities of our kind. From the analogy with sexism and racism, I suppose the name for this malady is speciesism. The prejudice that there are no beings so fine, so capable, so reliable as human beings. This is a prejudice because it is at the very least a prejudgment, a conclusion drawn before all the facts are in. Such comparisons of men and machines in space are comparisons of smart men and dumb machines. We have not asked what sorts of machines could have been built for the $30 or so billion that the Apollo and Skylab missions cost. Each human being is a superbly constructed, astonishingly compact, self-ambulatory computer capable on occasion of independent decision-making and real control of his or her environment. And, as the old joke goes, these computers can be constructed by unskilled labor, but there are serious limitations to employing human beings in certain environments. Without a great deal of protection, human beings would be inconvenienced on the ocean floor, the surface of Venus, the deep interior of Jupiter, or even on long space missions. Perhaps the only interesting results of Skylab that could not have been obtained by machines is that human beings in space for a period of months undergo a serious loss of bone calcium and phosphorus, which seems to imply that human beings may be incapacitated under 0 grams for missions of 6 to 9 months or longer. But the minimum interplanetary voyages have characteristic times of a year or two. Because we value human beings highly, we are reluctant to send them on very risky missions. If we do send human beings to exotic environments, we must also send along their food, their air, their water, amenities for entertainment and waste recycling and companions. By comparison, machines require no elaborate life support systems, no entertainment, no companionship, and we do not yet feel any strong ethical prohibitions against sending machines on one way or suicide. Missions, certainly. For simple missions, machines have proved themselves many times over. Unmanned vehicles have performed the first photography of the whole Earth and of the far side of the Moon, the first landings on the Moon, Mars, and Venus, and the first thorough orbital reconnaissance of another planet. In the Mariner 9 and Viking missions to Mars, here on Earth it is increasingly common for high-technology manufacturing, for example, chemical and pharmaceutical plants, to be performed largely or entirely under computer control. In all these activities, machines are able to some extent to sense errors, to correct mistakes, to alert human controllers some great distance away about perceived problems. The powerful abilities of computing machines to do arithmetic hundreds of millions of times faster than unaided human beings are legendary. But what about really difficult matters? Can machines in any sense think through a new problem? Can they make discussions of the branched contingency tree variety which we think of as characteristically human? That is, I ask question 1. If the answer is A, I ask question 2. But if the answer is B, I ask question 3, and so on. Some decades ago, the English mathematician A.M. Turing described what would be necessary for him to believe in machine intelligence. The condition was simply that he could be in teletype communication with a machine and be unable to tell that it was not a human being. Turing imagined a conversation between a man and a machine of the following quality. Interrogator. In the first line of your sonnet, which reads, "Shall I compare thee to a summer's day? Would not a spring day do as well or better? Witness. It wouldn't scan." Interrogator. How about a winter's day? That would scan all right. Witness. Yes, but nobody wants to be compared to a winter's day. Interrogator. Would you say Mr. Pickwick reminded you of Christmas? Witness. In a way, interrogator. Yet Christmas is a winter's day, and I do not think Mr. Pickwick would mind the comparison. Witness. I don't think you're serious. By a winter's day one means a typical winter's day rather than a special one like Christmas. No device of this sophistication has yet been built, although I'm not sure how many humans would pass Turing's human test. But the amount of effort and money put into artificial intelligence has been quite limited, and there are only about a half-dozen major centers of such activity in the world. One of the more striking results obtained in a very limited universe of discourse, that of children's blocks, has come from the work of Terry Winograd, then at the Massachusetts Institute of Technology. Here is a dialogue between man and machine. The machine having been programmed by Winograd, Q. What does the box contain? A. The blue pyramid and the blue box. Q. How many blocks are not in the box? A. 4 of them. Q. Is at least one of them narrower than the one which I told you to pick up? A. Yes, the red cube. Is there a steeple? A. Sorry, I don't know the word steeple. Q. A steeple is a stack which contains 2 green cubes and a pyramid, for example. A. I understand. Q. Are there any steeples now? A. No. Q. Build one. The machine does. It reaches out its mechanical hand, moves the cubes, and builds the structure that has just been described. Q. When did you pick up the pyramid? A. While I was stacking up the red cube, the large red block, and the large green cube. Q. Why? A. To get rid of it. Q. Why did you clear off that cube? A. To put it on the large green cube. As another example, a machine psychiatrist has been developed by Joseph Weizenbaum, also at MIT. This is a much simpler program than Winograd's, since it involves non-directive psychotherapy, which, generally speaking, requires extremely simple-minded computer programs. Here is a striking dialogue between a human being and a computer psychotherapist. There is certainly a selection effect here. Many other such machine-human psychiatric dialogues are not nearly so striking. But I suppose most human-human psychiatric dialogues are not very striking either. In this interaction, in order to spell out clearly the respective roles of therapist and patient, the computer therapist types uppercase, while the patient types lowercase. Men are all alike. In what way? They're always bugging us about something or other. Can you think of a specific example? Well, my boyfriend made me come here. Your boyfriend made you come here. He noticed that I'm depressed much of the time. I am sorry to hear you're depressed. He's right. I am unhappy. Do you think coming here will help you not to be unhappy? I need some help. That much is clear. What would it mean to you if you got some help? Perhaps I could learn to get along with my mother. Tell me more about your family. My mother takes care of me. Who else in your family takes care of you? My father, your father. You are like my father in some ways. What resemblance do you see? You are not very aggressive. But I don't think you want me to notice that. What makes you think I am not very aggressive? You don't argue with me. Why do you think I don't argue with you? You are afraid of me. Does it please you to believe I am afraid of you? It pleases my father to think I am afraid of him. What else comes to mind when you think of your father? Bullies, those that have anything to do with the fact that your boyfriend made you come here. This astonishing, one is very tempted to say perceptive response from the computer is, of course, pre-programmed. But then, so are the responses of human psychotherapists. In a time when more and more people in our society seem to be in need of psychiatric counseling, and when time-sharing of computers is widespread, I can even imagine the development of a network of computer psychotherapeutic terminals, something like arrays of large telephone booths, in which, for a few dollars a session, we are able to talk to an attentive, tested, and largely non-directive psychotherapist. Ensuring the confidentiality of the psychiatric dialogue is one of several important steps still to be worked out. Another sign of the intellectual accomplishments of machines is in games, even exceptionally simple computers. Those that can be wired by a bright 10-year-old can be programmed to play perfect tic-tac-toe. Some computers can play world-class checkers. Chess is, of course, a much more complicated game than tic-tac-toe or checkers. Here, programming a machine to win is more difficult, and novel strategies have been used, including several rather successful attempts to have a computer learn from its own experience in playing previous chess games. Computers can learn, for example, empirically, the rule that it is better in the beginning game to control the center of the chessboard than the periphery. The 10 best chess players in the world still have nothing to fear from any present computer. But the situation is changing. Recently, a computer for the first time did well enough to enter the Minnesota State Chess Open. This may be the first time that a non-human has entered a major sporting event on the planet Earth, and I cannot help but wonder if robot golfers and designated hitters may be attempted sometime in the next decade, to say nothing of dolphins in freestyle competition. The computer did not win the Chess Open, but this is the first time one has done well enough to enter such a competition. Chess-playing computers are improving extremely rapidly. I have heard machines demeaned, often with a just audible sigh of relief, for the fact that chess is an area where human beings are still superior. This reminds me very much of the old joke in which a stranger remarks with wonder on the accomplishments of a checker-playing dog. The dog's owner replies, "Oh, it's not all that remarkable. He loses 2 games out of 3. A machine that plays chess in the middle range of human expertise is a very capable machine. Even if there are thousands of better human chess players, there are millions who are worse. To play chess requires strategy, foresight, analytical powers, and the ability to cross-correlate large numbers of variables and to learn from experience. These are excellent qualities in those whose job it is to discover and explore, as well as those who watch the baby and walk the dog. With this as a more or less representative set of examples of the state of development of machine intelligence, I think it is clear that a major effort over the next decade could produce much more sophisticated examples. This is also the opinion of most of the workers in machine intelligence. In thinking about this next generation of machine intelligence, it is important to distinguish between self-controlled and remotely controlled robots. A self-controlled robot has its intelligence within it. A remotely controlled robot has its intelligence at some other place, and its successful operation depends upon close communication between its central computer and itself. There are, of course, intermediate cases where the machine may be partly self-activated and partly remotely controlled. It is this mix of remote and in-situ control that seems to offer the highest efficiency for the near future. For example, we can imagine a machine designed for the mining of the ocean floor. There are enormous quantities of manganese nodules littering the abyssal depths. They were once thought to have been produced by meteorite infall on Earth, but are now believed to be formed occasionally in vast manganese fountains, produced by the internal tectonic activity of the Earth. Many other scarce and industrially valuable minerals are likewise to be found on the deep ocean bottom. We have the capability today to design devices that systematically swim over or crawl upon the ocean floor, that are able to perform spectrometric and other chemical examinations of the surface material, that can automatically radio back to ship or land all findings, and that can mark the locales of especially valuable deposits, for example by low-frequency radio homing devices. The radio beacon will then direct great mining machines to the appropriate locales. The present state-of-the-art in deep-sea submersibles and in spacecraft environmental sensors is clearly compatible with the development of such devices. Similar remarks can be made for offshore oil drilling, for coal and other subterranean mineral mining, and so on. The likely economic returns from such devices would pay not only for their development, but for the entire space program many times over. When the machines are faced with particularly difficult situations, they can be programmed to recognize that the situations are beyond their abilities and to inquire of human operators working in safe and pleasant environments what to do next. The examples just given are of devices that are largely self-controlled. The reverse also is possible, and a great deal of very preliminary work along these lines has been performed in the remote handling of highly radioactive materials in laboratories of the U.S. Department of Energy. Here, I imagine a human being who is connected by radio link with a mobile machine. The operator is in Manila, say, the machine in the Mindanao Deep. The operator is attached to an array of electronic relays which transmits and amplifies his movements to the machine and which can, conversely, carry what the machine finds back to his senses. So when the operator turns his head to the left, the TV cameras on the machine turn left, and the operator sees on a great hemispherical TV screen around him the scene the machine's searchlights and cameras have revealed. When the operator in Manila takes a few strides forward in his wired suit, the machine in the abyssal depths ambles a few feet forward. When the operator reaches out his hand, the mechanical arm of the machine likewise extends itself, and the precision of the man-machine interaction is such that precise manipulation of material at the ocean bottom by the machine's fingers is possible. With such devices, human beings can enter environments otherwise closed to them forever. In the exploration of Mars, unmanned vehicles have already soft-landed, and only a little further in the future, they will roam about the surface of the red planet, as some now do on the Moon. We are not ready for a manned mission to Mars. Some of us are concerned about such missions because of the dangers of carrying terrestrial microbes to Mars, and Martian microbes, if they exist, to Earth, but also because of their enormous expense. The Viking landers deposited on Mars in the summer of 1976 have a very interesting array of sensors and scientific instruments which are the extension of human senses to an alien environment. The obvious post-Viking device for Martian exploration, one which takes advantage of the Viking technology, is a Viking rover in which the equivalent of an entire Viking spacecraft, but with considerably improved science, is put on wheels or tractor treads and permitted to rove slowly over the Martian landscape. But now we come to a new problem, one that is never encountered in machine operation on the Earth's surface. Although Mars is the second closest planet, it is so far from the Earth that the light travel time becomes significant. At a typical relative position of Mars and the Earth, the planet is 20 light minutes away. Thus, if the spacecraft were confronted with a steep incline, it might send a message of inquiry back to Earth. 40 minutes later, the response would arrive saying something like, "For heaven's sake, stand dead still." But by then, of course, an unsophisticated machine would have tumbled into the gully. Consequently, any Martian rover requires slope and roughness sensors. Fortunately, these are readily available and are even seen in some children's toys. When confronted with a precipitous slope or large boulder, the spacecraft would either stop until receiving instructions from the Earth in response to its query and televised picture of the terrain, or back off and start in another and safer direction. Much more elaborate contingency decision networks can be built into the onboard computers of spacecraft of the 1980s. For more remote objectives to be explored further in the future, we can imagine human controllers in orbit around the target planet or on one of its moons. In the exploration of Jupiter, for example, I can imagine the operators on a small moon outside the fierce Jovian radiation belts controlling with only a few seconds delay the responses of a spacecraft floating in the dense Jovian clouds. Human beings on Earth can also be in such an interaction loop if they are willing to spend some time on the Enterprise. If every decision in Martian exploration must be fed through a human controller on Earth, the rover can traverse only a few feet an hour. But the lifetimes of such rovers are so long that a few feet an hour represents a perfectly respectable rate of progress. However, as we imagine expeditions into the farthest reaches of the solar system and ultimately to the stars, it is clear that self-controlled machine intelligence will assume heavier burdens of responsibility. In the development of such machines, we find a kind of convergent evolution. Viking is, in a curious sense, like some great outsized, clumsily constructed insect. It is not yet ambulatory, and it is certainly incapable of self-reproduction, but it has an exoskeleton, it has a wide range of insect-like sensory organs, and it is about as intelligent as a dragonfly. But Viking has an advantage that insects do not. It can, on occasion, by inquiring of its controllers on Earth, assume the intelligence of a human being. The controllers are able to reprogram the Viking computer on the basis of decisions they make. As the field of machine intelligence advances and as increasingly distant objects in the solar system become accessible to exploration, we will see the development of increasingly sophisticated onboard computers, slowly climbing the phylogenetic tree from insect intelligence to crocodile intelligence to squirrel intelligence, and in the not very remote future, I think, to dog intelligence. Any flight to the outer solar system must have a computer capable of determining whether it is working properly. There is no possibility of sending to the Earth for a repairman. The machine must be able to sense when it is sick and skillfully doctor its own illnesses. A computer is needed that is able either to fix or replace failed computer, sensor, or structural components. Such a computer, which has been called STAR, self-testing and repairing computer, is on the threshold of development. It employs redundant components, as biology does. We have 2 lungs and 2 kidneys, partly because each is protection against failure of the other. But a computer can be much more redundant than a human being who has, for example, but 1 head and 1 heart. Because of the weight premium on deep space exploratory ventures, there will be strong pressures for continued miniaturization of intelligent machines. It is clear that remarkable miniaturization has already occurred. Vacuum tubes have been replaced by transistors, wired circuits by printed circuit boards, and entire computer systems by silicon chip microcircuitry. Today, a circuit that used to occupy much of a 1930 radio set can be printed on the tip of a pin. If intelligent machines for terrestrial mining and space exploratory applications are pursued, the time cannot be far off when household and other domestic robots will become commercially feasible. Unlike the classical anthropoid robots of science fiction, there is no reason for such machines to look any more human than a vacuum cleaner does. They will be specialized for their functions. But there are many common tasks ranging from bartending to floor washing that involve a very limited array of intellectual capabilities, albeit substantial stamina and patience. All-purpose ambulatory household robots which perform domestic functions as well as a proper 19th century English butler are probably many decades off, but more specialized machines, each adapted to a specific household function, are probably already on the horizon. It is possible to imagine many other civic tasks and essential functions of everyday life carried out by intelligent machines. By the early 1970s, garbage collectors in Anchorage, Alaska, and other cities won wage settlements guaranteeing them salaries of about $20,000 per annum. It is possible that the economic pressures alone may make a persuasive case for the development of automated garbage collecting machines. For the development of domestic and civic robots to be a general civic good, the effective re-employment of those human beings displaced by the robots must, of course, be arranged, but over a human generation that should not be too difficult, particularly if there are enlightened educational reforms. Human beings enjoy learning. We appear to be on the verge of developing a wide variety of intelligent machines capable of performing tasks too dangerous, too expensive, too onerous, or too boring for human beings. The development of such machines is, in my mind, one of the few legitimate spin-offs of the space program. The efficient exploitation of energy in agriculture, upon which our survival as a species depends, may even be contingent on the development of such machines. The main obstacle seems to be a very human problem, the quiet feeling that comes stealthily and unbidden, and argues that there is something threatening or inhuman about machines performing certain tasks as well as or better than human beings, or a sense of loathing for creatures made of silicon and germanium rather than proteins and nucleic acids. But in many respects, our survival as a species depends on our transcending such primitive chauvinism. In part, our adjustment to intelligent machines is a matter of acclimatization. There are already cardiac pacemakers that can sense the beat of the human heart. Only when there is the slightest hint of fibrillation does the pacemaker stimulate the heart. This is a mild but very useful sort of machine intelligence. I cannot imagine the wearer of this device resenting its intelligence. I think in a relatively short period of time there will be a very similar sort of acceptance for much more intelligent and sophisticated machines. There is nothing inhuman about an intelligent machine. It is indeed an expression of those superb intellectual capabilities that only human beings, of all the creatures on our planet, now possess. Chapter 21. The Past and Future of American Astronomy. What has been done is little, scarcely a beginning, yet it is much in comparison with the total blank of a century past, and our knowledge will, we are easily persuaded, appear in turn the merest ignorance to those who come after us. Yet it is not to be despised, since by it we reach up groping to touch the hem of the garment of the Most High Angdes M. Clerk, A Popular History of Astronomy, London, Adam and Charles Black, 1893. The world has changed since 1899, but there are few fields which have changed more in the development of fundamental insights and in the discovery of new phenomena than astronomy. Here are a few titles of recent papers published in the scientific magazines: the Astrophysical Journal and Icarus, G240, 72, a new magnetic white dwarf with unusual polarization, relativistic stellar stability, preferred frame effects, detection of interstellar methylamine, a new list of 52 degenerate stars, the age of Alpha Centauri, do OB runaways have collapsed companions, finite nuclear size effects on neutrino pair Bremsstrahlung in neutron stars, gravitational radiation from stellar collapse, a search for a cosmological component of the soft X-ray background in the direction of M31, the photochemistry of hydrocarbons in the atmosphere of Titan, the content of uranium, thorium, and potassium in the rocks of Venus as measured by Venera 8, HCN radio emission from comet Kohoutek, a radar brightness and altitude image of a portion of Venus, and a Mariner 9 photographic atlas of the moons of Mars. Our astronomical ancestors would have extracted a glimmer of meaning from these titles, but I think their principal reaction would have been one of incredulity. When I was asked to chair the 75th Anniversary Committee of the American Astronomical Society in 1974, I thought it would provide a pleasant opportunity to acquaint myself with the state of our subject at the end of the past century. I was interested to see where we had been, where we are today, and, if possible, something of where we may be going. In 1897, the Yerkes Observatory, then the largest telescope in the world, was given a formal dedication, and a scientific meeting of astronomers and astrophysicists was held in connection with the ceremony. A second meeting was held at the Harvard College Observatory in 1898, and a third at the Yerkes Observatory in 1899, by which time what is now the American Astronomical Society had been officially founded. The astronomy of 1897 to 1899 seems to have been vigorous, combative, dominated by a few strong personalities, and aided by remarkably short publication times, the average time between submission and publication for papers in the Astrophysical Journal, APJ. In this period seems to be better than in Astrophysical Journal letters today. The fact that a great many papers were from the Yerkes Observatory where the journal was edited may have had something to do with this. The opening of the Yerkes Observatory at Williams Bay, Wisconsin, which has the year 1895 imprinted upon it, was delayed more than a year because of the collapse of the floor, which narrowly missed killing the astronomer E. Barnard. The accident is mentioned in APJ 6149, but one finds no hint of negligence there. However, the British Journal Observatory 2393 clearly implies careless construction and a cover-up to shield those responsible. We also discover on the same page of Observatory that the dedication ceremonies were postponed for some weeks to accommodate the travel schedule of Mr. Yerkes, the robber baron donor. The Astrophysical Journal says that the dedication ceremonies were necessarily postponed from October 4th, 1897, but does not say YAP. J was edited by George Ellery Hale, the director of the Yerkes Observatory, and by James E. Keeler, who in 1898 became the director of the Lick Observatory on Mount Hamilton in California. However, there was a certain domination of APJ. By Williams Bay, perhaps because the Lick Observatory dominated the publications of the Astronomical Society of the Pacific Past in the same period. Volume 5 of the Astrophysical Journal has no fewer than 13 plates of the Yerkes Observatory, including one of the powerhouse. The first 50 pages of Volume 6 have a dozen more plates of the Yerkes Observatory. The Eastern dominance of the American Astronomical Society is also reflected by the fact that the first president of the Astronomical and Astrophysical Society of America was Simon Newcomb of the Naval Observatory in Washington, and the first vice presidents Young and Hale. West Coast astronomers complained about the difficulties in traveling to the third conference of astronomers and astrophysicists at Yerkes, and seemed to have voiced some pleasure that promised demonstrations with the Yerkes 40-inch refractor for this ceremony had to be postponed because of cloudy weather. This was about the most in the way of inter-observatory rancor that can be found in either journal. But in the same period, Observatory had a keen nose for American astronomical gossip. From Observatory, we find that there was a civil war at the Lick Observatory and a scandal associated with Edward Holden, the director before Keeler, who was said to have permitted rats in the drinking water at Mount Hamilton. It also published a story about a test chemical explosion scheduled to go off in the San Francisco Bay Area and to be monitored by a seismic device on Mount Hamilton. At the appointed moment, no staff member could see any sign of needle deflection except for Holden, who promptly dispatched a messenger down the mountain to alert the world to the great sensitivity of the Lick seismometer. But soon up the mountain came another messenger with the news that the test had been postponed. A much faster messenger was then dispatched to overtake the first, and an embarrassment to the Lick Observatory was, observatory notes narrowly averted. The youth of American astronomy in this period is eloquently reflected in the proud announcement in 1900 that the Berkeley Astronomical Department would henceforth be independent of the Civil Engineering Department at the University of California. A survey by Professor George Airy, later the British Astronomer Royal, regretted being unable to report on astronomy in America in 1832 because essentially there was none. He would not have said that in 1899. There is never much sign in these journals of the intrusion of external as opposed to academic politics, except for an occasional notice such as the appointment by President McKinley of TJJ, C as Professor of Mathematics to the U.S. Navy, and a certain continuing chilliness in scientific debates between the personnel of the Lick and Potsdam, Germany observatories. Some signs of the prevailing attitudes of the 1890s occasionally trickle through. For example, in a description of an eclipse expedition to Siloam, Georgia on May 28, 1900, even some of the whites were lacking in a very deep knowledge of things eclipse-wise. Many thought it was a money-making scheme, and what I intended to charge for admission was a very important question, frequently asked. Another idea was that the eclipse could be seen only from the inside of my observatory, just here. I wish to express my appreciation of the high moral tone of the community, for, with a population of only 100, including the immediate neighborhood, it sustains 2 white and 2 colored churches, and during my stay I did not hear a single profane word. As an unsophisticated Yankee in the Southland, unused to Southern ways, I naturally made many little slips that were not considered just the thing. The smiles at my prefixing Mr. to the name of my colored helper caused me to change it to Colonel, which was entirely satisfactory to everybody. A board of visitors was appointed to resolve some never publicly specified problems at the U.S. Naval Observatory. A report of this group, which consisted of two obscure senators and professors, Edward C. Pickering, George C. Comstock, and Hale, is illuminating because it mentions dollar amounts. We find that the annual running costs of the major observatories in the world were Naval Observatory, $85,000, Paris Observatory, $53,000, Greenwich Observatory, England, $49,000, Harvard Observatory, $46,000, and Pulkowa Observatory, Russia, $36,000. The salaries of the two directors of the U.S. Naval Observatory were $4,000 each, and at the Harvard Observatory, $5,000. The distinguished board of visitors recommended that in a schedule of salaries which could be expected to attract astronomers of the class desired, the salary of directors of observatories should be $6,000. At the Naval Observatory, computers, exclusively human at the time, were paid $1,200 per annum, but at the Harvard Observatory only $500 per annum, and were almost exclusively women. In fact, all salaries at Harvard, except for the directors, were significantly lower than at the Naval Observatory. The committee stated, "The great difference in salaries at Washington and Cambridge, especially for the officers of lower grade, is probably unavoidable. This is partly due to civil service rules." An additional sign of astronomical impecuniosity is the announcement of the post of volunteer research assistant at Yerkes, which had no associated pay but which was said to provide good experience for students with higher degrees. Then, as now, astronomy was besieged by paradoxers, proponents of fringe or crackpot ideas. One proposed a telescope with 91 lenses in series as an alternative to a telescope with a smaller number of lenses of larger aperture. The British in this period were similarly plagued, but in perhaps a gentler way. For example, an obituary in the monthly notices of the Royal Astronomical Society, 59/2026, of Henry Perigal, informs us that the deceased had celebrated his 94th birthday by becoming a member of the Royal Institution, but was elected a Fellow of the Royal Astronomical Society in 1850. However, our publications contain nothing from his pen. The obituary describes the remarkable way in which the charm of Mr. Perigal's personality won him a place which might have seemed impossible of attainment for a man of his views, for there is no masking the fact that he was a paradoxer pure and simple, his main conviction being that the moon did not rotate, and his main astronomical aim in life being to convince others, and especially young men not hardened in the opposite belief, of their grave error. To this end he made diagrams, constructed models, and wrote poems, bearing with heroic cheerfulness the continued disappointment of finding none of them of any avail. He has, however, done excellent work apart from this unfortunate misunderstanding. The number of American astronomers in this period was very small. The bylaws of the Astronomical and Astrophysical Society of America state that a quorum is constituted by 20 members. By the year 1900, only 9 doctorates had been granted in astronomy in America. In that year, there were 4 astronomical doctorates, 2 from Columbia University for G. N. Bauer and Carolyn Furness, 1 from the University of Chicago for Forrest Ray Moulton, and 1 from Princeton University for Henry Norris Russell. Some idea of what was considered important scientific work in this period can be garnered from the prizes that were awarded. E. Barnard received the gold medal of the Royal Astronomical Society in part for his discovery of the Jovian moon, Jupiter 5, and for his astronomical photography with a portrait lens. His steamer, however, was caught in an Atlantic storm, and he did not arrive in time for the celebration ceremony. He is described as requiring several days to recover from the storm, whereupon the RAS hospitably gave a second dinner for him. Barnard's lecture seems to have been spectacular and made full use of that recently improved audio-visual aid, the lantern slide projector. In his discussion of his photograph of the region of the Milky Way near Theta Ophiuchus, he concluded that the entire groundwork of the Milky Way has a substratum of nebulous matter. Meanwhile, H.K. Palmer reported no nebulosity in photographs of the globular cluster M13. Barnard, who was a superb visual observer, expressed considerable doubts about Percival Lowell's view of an inhabited and canal-infested Mars in his thanks to Barnard for his lecture. The president of the Royal Astronomical Society, Sir Robert Ball, voiced concern that henceforth he should regard the canals in Mars with some suspicion. Nay, even the seas of Mars, the dark areas, had partly fallen under a ban. Perhaps the lecturer's recent experiences on the Atlantic might explain something of this mistrust. Lowell's views were not then in favor in England, as another notice in Observatory indicated. In response to an inquiry on which books had most pleased and interested him in 1896, Professor Norman Lockyer replied, Mars by Percival Lowell, Sentimental Tommy by J. M. Barrie. No time for reading seriously. Prizes in astronomy for 1898, awarded by the Académie Française, included one to Seth Chandler for the discovery of the variation in latitude, one to Belopolsky, partly for studies of spectroscopic binary stars, and one to Schott for work on terrestrial magnetism. There was also a prize competition for the best treatise on the theory of perturbations of Hyperion, a moon of Saturn. We are informed that the only essay presented was that by Dr. G. W. Hill of Washington, to whom the prize was awarded. The Astronomical Society of the Pacific's Bruce Medal was awarded in 1899 to Dr. Arthur Owers of Berlin. The dedicatory address included the following remarks. Today, Owers stands at the head of German astronomy. In him is seen the highest type of investigator in our time, one perhaps better developed in Germany than in any other country. The work of men of this type is marked by minute and careful research, untiring industry in the accumulation of facts, caution in propounding new theories or explanations, and, above all, the absence of effort to gain recognition by being the first to make a discovery. In 1899, the Henry Draper Gold Medal of the National Academy of Sciences was presented for the first time in 7 years. The recipient was Keeler. In 1898, Brooks, whose observatory was in Geneva, New York, announced the discovery of his 21st comet, which Brooks described as achieving his majority. Shortly thereafter, he received the Lalande Prize of the Académie Française for his record in discovering comets in 1897. In connection with an exhibition in Brussels, the Belgian government offered prizes for the solutions of certain problems in astronomy. These problems included the numerical value Ovard prizes for the solutions of certain problems in astronomy. These problems included the numerical value of the acceleration due to gravity on Earth, the secular acceleration of the Moon, the net motion of the solar system through space, the variation of latitude, the photography of planetary surfaces, and the nature of the canals of Mars. A final topic was the invention of a method to observe the solar corona in the absence of an eclipse. Monthly Notices 2014-5 commented, "If this pecuniary reward does induce anyone to solve this last problem, or in fact any of the others, we think the money will be well spent." However, reading the scientific papers of this time, one gets the impression that the focus had shifted to other topics than those for which prizes were being given. Sir William and Lady Huggins performed laboratory experiments which showed that at low pressures the emission spectrum of calcium exhibited only the so-called H and K lines. They concluded that the Sun was composed chiefly of hydrogen, helium, coronium, and calcium. Huggins had earlier established a stellar spectral sequence which he believed was evolutionary. The Darwinian influence in science was very strong in this period, and among American astronomers T.J.J. C's work was notably dominated by a Darwinian perspective. It is interesting to compare Huggins's spectral sequence with the present Morgan-Keenan spectral types. Huggins' stellar spectral sequence, order of, increasing age star, and modern spectral type in parentheses, Young Sirius, A1V, Altair, A75V, Rigel, B8IAA, DEED, A2IA, Vega, A0V, Capella, G8G0, Arcturus, K13, Aldebaran, K53, Sun, G0. Old Betelgeuse M2I note, The modern stellar spectral sequence runs from early to late spectral types as O, B, A, F, G, K, M Higgins was very nearly right. We can see here the origin of the present terms early and late spectral type, which reflect the Darwinian spirit of late Victorian science. It is also clear that there is a reasonably continuous gradation of spectral types here, and the beginnings, through the later Hartsprung-Russell diagram of modern theories of stellar evolution. There were major developments in physics during this period, and readers of APJ were alerted to them by the reprinting of summaries of important papers. Experiments were still being performed on the basic radiation laws. In some papers, the level of physical sophistication was not of the highest caliber, as for example in an article in PASP 1118, where the linear momentum of Mars is calculated as the single product of the mass of the planet and the linear velocity of the surface. It concluded, the planet, exclusive of the cap, has a momentum of 183 3/8 septillion foot-pounds. Exponential notation for large numbers was evidently not in wide use. In this time we have the publication of visual and photographic-like curves, for example, of stars in M5 and experiments in filter photography of Orion by Keeler. An obviously exciting topic was time-variable astronomy, which must then have generated something of the excitement that pulsars, quasars, and X-ray sources do today. There were many studies of variable velocities in the line of sight from which were derived the orbits of spectroscopic binaries, as well as periodic variations in the apparent velocity of Omicron Ceti from the Doppler displacement of H gamma and other spectral lines. The first infrared measurements of stars were performed at the Yerkes Observatory by Ernest F. Nichols. The study concludes, we do not receive from Arcturus more heat than would reach us from a candle at a distance of 5 or 6 miles. No further calculations are given. The first experimental observations of the infrared opacity of carbon dioxide and water vapor were performed in this period by Rubens and Ashkenaz, who essentially discovered the V2 fundamental of carbon dioxide at 15 microns and the pure rotation spectrum of water. There is preliminary photographic spectroscopy of the Andromeda Nebula by Julius Scheiner at Potsdam, Germany, who concludes correctly that the previous suspicion that the spiral nebulae are star clusters is now raised to a certainty. As an example of the level of personal vituperation tolerated at this time, the following is an extract from a paper by Scheiner in which W.W. Campbell is criticized. In the November number of the Astrophysical Journal, Professor Campbell attacks with much indignation some remarks of mine criticizing his discoveries. Such sensitiveness is somewhat surprising on the part of one who is himself given to severely taking others to task. Further, an astronomer who frequently observes phenomena which others cannot see and fails to see those which others can, must be prepared to have his opinions contested. If, as Professor Campbell complains, I have only supported my views by a single example, I was only withheld by courteous motives from adding another. Namely, the fact that Professor Campbell cannot perceive the lines of aqueous vapor in the spectrum of Mars which were seen by Huggins and Vogel in the first place, and, after Mr. Campbell had called their existence in question, were again seen and identified with certainty by Professor Wilsing and myself. The amount of water vapor in the Martian atmosphere that is now known to exist would have been entirely indetectable by the spectroscopic methods then in use. Spectroscopy was a dominant element in late 19th century science. APJ was busily publishing Rowland's solar spectrum, which ran to 20,000 wavelengths, each to 7 significant figures. It published a major obituary of Bunsen. Occasionally, the astronomers took note of the extraordinary nature of their discoveries. It is simply amazing that the feeble twinkling light of a star can be made to produce such an autographic record of substance and condition of the inconceivably distant luminary. A major topic of debate for the Astrophysical Journal was whether spectra should be shown with red to the left or to the right. Those who favored red to the left cited the analogy of the piano where high frequencies are to the right, but APJ opted gamely for red to the right. Some room for compromise was available on whether in lists of wavelengths red should be at the top or at the bottom. Feelings ran high, and Huggins wrote to say that any change would be little less than intolerable, but the apt J won anyway. Another major discussion in this period was on the nature of sunspots, G. Johnstone Stoney proposed that they were caused by a layer of condensed clouds in the photosphere of the sun, but Wilson and Fitzgerald objected to this on the ground that no conceivable condensates could exist at these high temperatures, with the possible exception of carbon. They suggested instead, and very vaguely, that sunspots are due to reflection by convection streams of gas. Evershed had a more ingenious idea. He thought that sunspots were holes in the outer photosphere of the sun, permitting us to see to much greater and hotter depths. But why are they dark? He proposed that all the radiation would be moved from the visible to the inaccessible ultraviolet. This, of course, was before the Planck distribution of radiation from a hot object was understood. It was not at this time thought impossible that the spectral distributions of black bodies of different temperatures should cross, and some experimental curves of this period indeed showed such crossing due, as we now know, to emissivity and absorptivity differences. Ramsay had recently discovered the element krypton, which was said to have among 14 detectable spectral lines, one at 5570 Opere, coincident with the principal line of the aurora, EB, Frost concluded. Thus it seems that the true origin of that hitherto perplexing line has been discovered. We now know it is due to oxygen. There were a great many papers on instrumental design, one of the more interesting being by Hale. In January 1897, he suggested that both refracting and reflecting telescopes were needed, but noted that there was a clear movement toward reflectors, especially equatorial code telescopes. In a historical memoir, Hale mentions that the 40-inch lens was available to the Yerkes Observatory only because a previous plan to build a large refractor near Pasadena, California, had fallen through. What, I wonder, would the history of astronomy have been like if the plan had succeeded? Curiously enough, Pasadena seems to have made an offer to the University of Chicago to have the Yerkes Observatory situated there. It would have been a long commute for 1897. At the end of the 19th century, solar system studies displayed the same mixture of future promise and current confusion that the stellar work did. One of the most notable papers of the period by Henry Norris Russell is called The Atmosphere of Venus. It is a discussion of the extension of the cusps of the crescent Venus, based in part on the author's observations with the 5-inch finder telescope of the Great Equatorial of the Halsted Observatory at Princeton. Perhaps the young Russell was not yet considered fully reliable, operating larger telescopes at Princeton. The essence of the analysis is correct by present standards. Russell concluded that refraction of sunlight was not responsible for the extension of the cusps, and that the cause was to be found in the scattering of sunlight. The atmosphere of Venus, like our own, contains suspended particles of dust or fog of some sort, and what we see is the upper part of this hazy atmosphere illuminated by rays that have passed close to the planet's surface. He later says that the apparent surface may be a dense cloud layer. The height of the haze is calculated as about 1 kilometer above what we would now call the main cloud deck, a number that is just consistent with limb photography by the Mariner 10 spacecraft. Russell thought, from the work of others, that there was some spectroscopic evidence for water vapor and oxygen in a thin Venus atmosphere, but the essence of his argument has stood the test of time remarkably well. William H. Pickering's discovery of Phoebe, the outermost satellite of Saturn, was announced, and Andrew E. Douglas of the Lowell Observatory published observations that led him to conclude that Jupiter 3 rotates about 1 hour slower than its period of revolution, a conclusion incorrect by 1 hour. Others who estimated periods of rotation were not quite so successful, for example. There was a Leo Brenner who observed from the Menorah Observatory in a place called Lucin Piccolo. Brenner severely criticized Percival Lowell's estimate of the rotation period of Venus. Brenner himself compared 2 drawings of Venus in white light made by 2 different people 4 years apart, from which he deduced a rotation period of 23 hours, 57 minutes and 36.37728 seconds, which he said agreed well with the mean of his own most reliable drawings. Considering this, Brenner found it incomprehensible that there could still be partisans of a 224 7-day rotation period and concluded that an inexperienced observer, an unsuitable telescope, an unhappily chosen eyepiece, a very small diameter of the planet observed with an insufficient power, and a low declination altogether explained Mr. Lowell's peculiar drawings. The truth, of course, lies not between the extremes of Lowell and Brenner, but rather at the other end of the scale, with a minus sign, a retrograde period of 243 days. In another communication, Herr Brenner begins, "Gentlemen, I have the honor to inform you that Mrs. Manora has discovered a new division in the Saturnian ring system, from which we discover that there is a Mrs. Manora at the Manora Observatory in Lucimpicolo, and that she performs observations along with Herr Brenner. Then follows a description of how the Encke, Cassini, Antoniadi, Struve, and Manora divisions are all to be kept straight. Only the first two have stood the test of time. Herr Brenner seems to have faded into the mists of the 19th century. At the second conference of astronomers and astrophysicists at Cambridge, there was a paper on the suggestion that asteroid rotation, if any, might be deduced from a light curve, but no variation of the brightness with time was found, and Henry Parkhurst concluded, "I think it is safe to dismiss the theory. It is now a cornerstone of asteroid studies." In a discussion of the thermal properties of the moon, made independently of the one-dimensional equation of heat conduction but based on laboratory emissivity measurements, Frank Very concluded that a typical lunar daytime temperature is about 100 degrees Celsius, exactly the right answer. His conclusion is worth quoting. "Only the most terrible of Earth's deserts, where the burning sands blister the skin and the men, beasts, and birds drop dead, can approach noontide on the cloudless surface of our satellite. Only the extreme polar latitudes of the moon can have an endurable temperature by day, to say nothing of the night, when we should have to become troglodytes to preserve ourselves from such intense cold." The expository styles were often fine. Earlier in the decade, Maurice Loewy and Pierre Puiseux at the Paris Observatory had published an atlas of lunar photographs, the theoretical consequences of which were discussed in APJ 551. The Paris group proposed a modified volcanic theory for the origin of the lunar craters, rills, and other topographic forms, which was later criticized by E. Barnard after he examined the planet with the 40-inch telescope. Barnard was then criticized by the Royal Astronomical Society for his criticism, and so on. One of the arguments in this debate had a deceptive simplicity. Volcanoes produce water. There is no water on the moon, therefore the lunar craters are not volcanic. While most of the lunar craters are not volcanic, this is not a convincing argument because it neglects the problem of possible repositories for water. Very's conclusions on the temperature of the lunar poles could have been read with some profit. Water there freezes out as frost. The other possibility is that water might escape from the moon to space. This was recognized by Stoney in a remarkable paper called Of Atmospheres Upon Planets and Satellites. He deduced that there should be no lunar atmosphere because of the very rapid escape to space of gases from the low lunar gravity, or any large buildup of the lightest gases, hydrogen and helium, on Earth. He believed that there was no water vapor in the Martian atmosphere and that Mars' atmosphere and caps were probably carbon dioxide. He implied that hydrogen and helium were to be expected on Jupiter and that Triton, the largest moon of Neptune, might have an atmosphere. Each of these conclusions is in accord with present-day findings or opinions. He also concluded that Titan should be airless, a prediction with which some modern theorists agree, although Titan seems to have another view of the matter. See Chapter 13. In this period, there are also a few breathtaking speculations, such as one by the Reverend J. M. Bacon that it would be a good idea to perform astronomical observations from high altitudes from, for example, a free balloon. He suggested that there would be at least two advantages: better seeing and ultraviolet spectroscopy. Goddard later made similar proposals for rocket-launched observatories, Chapter 18. Hermann Vogel had previously found by eyeball spectroscopy an absorption band at 6183 EVs in the body of Saturn. Subsequently, the International Color Photo Company of Chicago made photographic plates, which were so good that wavelengths as long as H-alpha in the red could be detected for a fifth magnitude star. This new emulsion was used at Yerkes, and Hale reported that there was no sign of the 6183 Abor band for the rings of Saturn. The band is now known to be at 6,160 Wf, 3 of methane. Another reaction to Percival Lowell's writings can be gleaned from the address of James Keeler at the dedication of the Yerkes Observatory. It is to be regretted that the habitability of the planets, a subject of which astronomers profess to know little, has been chosen as a theme for exploitation by the romancer, to whom the step from habitability to inhabitants is a very short one. The result of his ingenuity is that fact and fancy become inextricably tangled in the mind of the layman, who learns to regard communication with the inhabitants of Mars as a project deserving serious consideration, for which he may even wish to give money to scientific societies, and who does not know that it is condemned as a vagary by the very men whose labors have excited the imagination of the novelist. When he is made to understand the true state of our knowledge of these subjects, he is much disappointed and feels a certain resentment towards science, as if it had imposed upon him. Science is not responsible for these erroneous ideas which, having no solid basis, gradually die out and are forgotten. The address of Simon Newcomb on this occasion contains some remarks which apply generally, if a little idealistically, to the scientific endeavor. Is the man thus moved into the exploration of nature by an unconquerable passion more to be envied or pitied? In no other pursuit does such certainty come to him who deserves it. No life is so enjoyable as that whose energies are devoted to following out the inborn impulses of one's nature. The investigator of truth is little subject to the disappointments which await the ambitious man in other fields of activity. It is pleasant to be one of a brotherhood extending over the world in which no rivalry exists except that which comes out of trying to do better work than anyone else. While mutual admiration stifles jealousy, as the great captain of industry is moved by the love of wealth and the politician by the love of power, so the astronomer is moved by the love of knowledge for its own sake and not for the sake of its application. Yet he is proud to know that his science has been worth more to mankind than it has cost. He feels that man does not live by bread alone. If it is not more than bread to know the place we occupy in the universe, it is certainly something that we should place not far behind the means of subsistence. After reading through the publications of astronomers 3/4 of a century ago, I felt an irresistible temptation to imagine the 150th anniversary meeting of the American Astronomical Society, or whatever name it will have metamorphosed into by then, and guess how our present endeavors will be viewed. In examining the late 19th century literature, we are amused at some of the debates on sunspots, and impressed that the Zeeman effect was not considered a laboratory curiosity, but something to which astronomers should devote considerable attention. These two threads intertwined as if prefigured a few years later in G. E. Hale's discovery of large magnetic field strengths in sunspots. Likewise, we find innumerable papers in which the existence of a stellar evolution is assumed, but its nature remains hidden, in which the Kelvin-Helmholtz gravitational contraction was considered the only possible stellar energy source, and nuclear energy remained entirely unanticipated. But at the same time, and sometimes in the same volume of the Astrophysical Journal, there is acknowledgement of curious work being done on radioactivity by a man named Becquerel in France. Here again we see the two apparently unrelated threads moving through our few years' snapshot of late 19th century astronomy, and destined to intertwine 40 years later. There are many related examples, for instance, in the interpretation of series spectra of non-hydrogenic elements obtained at the telescope and pursued in the laboratory. New physics and new astronomy were the complementary sides of the emerging science of astrophysics. Accordingly, it is difficult not to wonder how many of the deepest present debates, for example, on the nature of quasars, or the properties of black holes, or the emission geometry of pulsars, must await an intertwining with new developments in physics. If the experience of 75 years ago is any guide, there will already be people today who dimly guess which physics will join with which astronomy, and a few years later the connection will be considered obvious. We also see in the 19th century material a number of cases where the observational methods or their interpretations are clearly in default by present standards. Planetary periods deduced to 10 significant figures by the comparison of two drawings made by different people of features we now know to be unreal to begin with is one of the worst examples. But there are many others, including a plethora of double star measurements of widely separated objects, which are mainly physically unconnected stars, a fascination with pressure and other effects on the frequencies of spectral lines when no one is paying any attention to curve of growth analysis, and acrimonious debates on the presence or absence of some substance based solely upon naked eye spectroscopy. Also curious is the sparseness of the physics in late Victorian astrophysics. Reasonably sophisticated physics is almost exclusively the province of geometrical and physical optics, the photographic process, and celestial mechanics. To make theories of stellar evolution based on stellar spectra without wondering much about the dependence of excitation and ionization on temperature, or attempting to calculate the subsurface temperature of the moon without ever solving Fourier's equation of heat conduction seems to me to be less than quaint. In seeing elaborate empirical representations of laboratory spectra, the modern reader becomes impatient for Bohr and Schrödinger and their successors to come along and develop quantum mechanics. I wonder how many of our present debates and most celebrated theories will appear from the vantage point of the year 2049, marked by shoddy observations, indifferent intellectual powers, or inadequate physical insight. I have the sense that we are today more self-critical than scientists were in 1899, that because of the larger population of astronomers, we check each other's results more often, and that, in part, because of the existence of organizations like the American Astronomical Society. The standards of exchange and discussion of results have risen significantly. I hope our colleagues of 2049 will agree. The major advance between 1899 and 1974 must be considered technological. But in 1899, the world's largest refractor had been built. It is still the world's largest refractor. A reflector of 100-inch aperture was beginning to be considered. We have improved on that aperture only by a factor of 2 in the intervening years. But what would our colleagues of 1899, living after Hertz but before Marconi, have made of the Arecibo Observatory, or the Very Large Array or Very Long Baseline Interferometry, VLBI, or checking out the debate on the period of rotation of Mercury by radar Doppler spectroscopy, or testing the nature of the lunar surface by returning some of it to Earth, or pursuing the problem of the nature and habitability of Mars by orbiting it for a year and returning 7,200 photographs of it, each of higher quality than the best 1899 photographs of the Moon. Or landing on the planet with imaging systems, microbiology experimentation, seismometers, and gas chromatograph, mass spectrometers, which did not even vaguely exist in 1899, or testing cosmological models by orbital ultraviolet spectroscopy of interstellar deuterium, when neither the models to be tested nor the existence of the atom that tests it were known in 1899, much less the technique of observation. It is clear that in the past 75 years, American and world astronomy has moved enormously beyond even the most romantic speculations of the late Victorian astronomers, and in the next 75 years. It is possible to make pedestrian predictions. We will have completely examined the electromagnetic spectrum from rather short gamma rays to rather long radio waves. We will have sent unmanned spacecraft to all of the planets and most of the satellites in the solar system. We will have launched spacecraft into the sun to do experimental stellar structure, beginning perhaps because of the low temperatures with the sunspots. Hale would have appreciated that. I think it possible that 75 years from now, we will have launched subrelativistic spacecraft traveling at about 0.1 the speed of light to the nearby stars. Among other benefits, such missions would permit direct examination of the interstellar medium and give us a longer baseline for VLBI than many are thinking of today. We will have to invent some new superlative to succeed very, perhaps ultra. The nature of pulsars, quasars, and black holes should by then be well in hand, as well as the answers to some of the deepest cosmological questions. It is even possible that we will have opened up a regular communications channel with civilizations on planets of other stars, and that the cutting edge of astronomy as well as many other sciences will come from a kind of encyclopedia galactica transmitted at very high bit rates to some immense array of radio telescopes. But in reading the astronomy of 75 years ago, I think it likely that, except for interstellar contact, these achievements, while interesting, will be considered rather old-fashioned astronomy, and that the real frontiers and the fundamental excitement of the science will be in areas that depend on new physics and new technology, which we can today at best dimly glimpse. Chapter 22. The Quest for Extraterrestrial Intelligence. Now the sirens have a still more fatal weapon than their song, namely their silence. Someone might possibly have escaped from their singing, but from their silence, certainly never. Franz Kafka, Parables. Through all of our history, we have pondered the stars and mused whether humanity is unique or if, somewhere else in the dark of the night sky, there are other beings who contemplate and wonder as we do, fellow thinkers in the cosmos. Such beings might view themselves and the universe differently. Somewhere else there might be very exotic biologies and technologies and societies. In a cosmic setting vast and old beyond ordinary human understanding, we are a little lonely, and we ponder the ultimate significance, if any, of our tiny but exquisite blue planet. The search for extraterrestrial intelligence is the search for a generally acceptable cosmic context for the human species. In the deepest sense, the search for extraterrestrial intelligence is a search for ourselves. In the last few years, in 1/1,000,000th the lifetime of our species on this planet, we have achieved an extraordinary technological capability which enables us to seek out unimaginably distant civilizations even if they are no more advanced than we. That capability is called radio astronomy and involves single radio telescopes, collections or arrays of radio telescopes, sensitive radio detectors, advanced computers for processing received data, and the imagination and skill of dedicated scientists. Radio astronomy has, in the last decade, opened a new window on the physical universe. It may also, if we are wise enough to make the effort, cast a profound light on the biological universe. Some scientists working on the question of extraterrestrial intelligence, myself among them, have attempted to estimate the number of advanced technical civilizations defined operationally as societies capable of radio astronomy in the Milky Way galaxy. Such estimates are little better than guesses. They require assigning numerical values to quantities such as the numbers and ages of stars, the abundance of planetary systems, and the likelihood of the origin of life, which we know less well, and the probability of the evolution of intelligent life and the lifetime of technical civilizations, about which we know very little indeed. When we do the arithmetic, the sorts of numbers we come up with are characteristically around 1,000,000 technical civilizations. 1,000,000 civilizations is a breathtakingly large number, and it is exhilarating to imagine the diversity, lifestyles, and commerce of those 1,000,000 worlds. But the Milky Way galaxy contains some 250 billion stars, and even with 1,000,000 civilizations, less than one star in 200,000 would have a planet inhabited by an advanced civilization. Since we have little idea which stars are likely candidates, we will have to examine a very large number of them. Such considerations suggest that the quest for extraterrestrial intelligence may require a significant effort. Despite claims about ancient astronauts and unidentified flying objects, there is no firm evidence for past visitations of the Earth by other civilizations. See chapters 5 and 6. We are restricted to remote signaling, and of the long-distance techniques available to our technology, radio is by far the best. Radio telescopes are relatively inexpensive. Radio signals travel at the speed of light, faster than which nothing can go, and the use of radio for communication is not a short-sighted or anthropocentric activity. Radio represents a large part of the electromagnetic spectrum, and any technical civilization anywhere in the galaxy will have discovered radio early, just as in the last few centuries we have explored the entire electromagnetic spectrum from short gamma rays to very long radio waves. Advanced civilizations might very well use some other means of communication with their peers, but if they wish to communicate with backward or emerging civilizations, there are only a few obvious methods, the chief of which is radio. The first serious attempt to listen for possible radio signals from other civilizations was carried out at the National Radio Astronomy Observatory in Green Bank, West Virginia in 1959 and 1960. It was organized by Frank Drake, now at Cornell University, and was called Project Ozma after the Princess of the Land of Oz, a place very exotic, very distant, and very difficult to reach. Drake examined two nearby stars, Epsilon Eridani and Tau Ceti, for a few weeks, with negative results. Positive results would have been astonishing because, as we have seen, even rather optimistic estimates of the number of technical civilizations in the galaxy imply that several 100,000 stars must be examined in order to achieve success by random stellar selection. Since Project Ozma, there have been 6 or 8 other such programs, all at a rather modest level in the United States, Canada, and the Soviet Union. All results have been negative. The total number of individual stars examined to date in this way is less than 1,000. We have performed something like 0.1% of the required effort. However, there are signs that much more serious efforts may be mustered in the reasonably near future. All the observing programs to date have involved quite tiny amounts of time on large telescopes, or when large amounts of time have been committed, only very small radio telescopes could be used. A comprehensive examination of the problem was recently made by a NASA committee chaired by Philip Morrison of the Massachusetts Institute of Technology. The committee identified a wide range of options, including new and expensive giant ground-based and spaceborne radio telescopes. It also pointed out that major progress can be made at modest cost by the development of more sensitive radio receivers and of ingenious computerized data processing systems. In the Soviet Union, there is a state commission devoted to organizing a search for extraterrestrial intelligence, and the large Rayton 600 radio telescope in the Caucasus, recently completed, is devoted part-time to this effort. Hand in hand with the recent spectacular advances in radio technology, there has been a dramatic increase in the scientific and public respectability of the entire subject of extraterrestrial life. A clear sign of the new attitude is the Viking missions to Mars, which are to a significant extent dedicated to the search for life on another planet. But along with the burgeoning dedication to a serious search, a slightly negative note has emerged, which is nevertheless very interesting. A few scientists have lately asked a curious question. If extraterrestrial intelligence is abundant, why have we not already seen its manifestation? Think of the advances by our own technical civilization in the past 10,000 years, and imagine such advances continued over millions or billions of years more. If only a tiny fraction of advanced civilizations are millions or billions of years more advanced than ours, why have they not produced artifacts, devices, or even industrial pollution of such magnitude that we would have detected it? Why have they not restructured the entire galaxy for their convenience? Skeptics also ask why there is no clear evidence of extraterrestrial visits to Earth. We have already launched slow and modest interstellar spacecraft. A society more advanced than ours should be able to ply the spaces between the stars conveniently, if not effortlessly. Over millions of years, such societies should have established colonies which might themselves launch interstellar expeditions. Why are they not here? The temptation is to deduce that there are at most a few advanced extraterrestrial civilizations, either because statistically we are one of the first technical civilizations to have emerged, or because it is the fate of all such civilizations to destroy themselves before they are much further along than we. It seems to me that such despair is quite premature. All such arguments depend on our correctly surmising the intentions of beings far more advanced than ourselves. And when examined more closely, I think these arguments reveal a range of interesting human conceits. Why do we expect that it will be easy to recognize the manifestations of very advanced civilizations? Is our situation not closer to that of members of an isolated society in the Amazon basin, say, who lack the tools to detect the powerful international radio and TV traffic that is all around them. Also, there is a wide range of incompletely understood phenomena in astronomy. Might the modulation of pulsars or the energy source of quasars, for example, have a technological origin? Or perhaps there is a galactic ethic of non-interference with backward or emerging civilizations. Perhaps there is a waiting time before contact is considered appropriate, so as to give us a fair opportunity to destroy ourselves first, if we are so inclined. Perhaps all societies significantly more advanced than our own have achieved an effective personal immortality and lose the motivation for interstellar gallivanting, which may, for all we know, be a typical urge only of adolescent civilizations. Perhaps mature civilizations do not wish to pollute the cosmos. There is a very long list of such perhapses, few of which we are in a position to evaluate with any degree of assurance. The question of extraterrestrial civilization seems to me entirely open. Personally, I think it far more difficult to understand a universe in which we are the only technological civilization, or one of a very few, than to conceive of a cosmos brimming over with intelligent life. Many aspects of the problem are, fortunately, amenable to experimental verification. We can search for planets of other stars, seek simple forms of life on such nearby planets as Mars, and perform more extensive laboratory studies on the chemistry of the origin of life. We can investigate more deeply the evolution of organisms and societies. The problem cries out for a long-term, open-minded, systematic search, with nature as the only arbiter of what is or is not likely. If there are 1,000,000 technical civilizations in the Milky Way galaxy, the average separation between civilizations is about 300 light-years. Since a light-year is the distance that light travels in 1 year, a little under 6 trillion miles, this implies that the one-way transit time for an interstellar communication from the nearest civilization is some 300 years. The time for a query and a response would be 600 years. This is the reason that interstellar dialogues are much less likely, particularly around the time of first contact, than interstellar monologues. At first sight, it seems remarkably selfless that a civilization might broadcast radio messages with no hope of knowing, at least in the immediate future, whether they have been received and what the response to them might be. But human beings often perform very similar actions as, for example, burying time capsules to be recovered by future generations, or even writing books, composing music, and creating art intended for posterity. A civilization that had been aided by the receipt of such a message in its past might wish similarly to benefit other emerging technical societies. For a radio search program to succeed, the Earth must be among the intended beneficiaries. If the transmitting civilization were only slightly more advanced than we are, it would possess ample radio power for interstellar communication, so much, perhaps, that the broadcasting could be delegated to relatively small groups of radio hobbyists and partisans of primitive civilizations. If an entire planetary government or an alliance of worlds carried out the project, the broadcasters could transmit to a very large number of stars, so large that a message is likely to be beamed our way, even though there may be no reason to pay special attention to our region of the sky. It is easy to see that communication is possible even without any previous agreement or contact between transmitting and receiving civilizations. There is no difficulty in envisioning an interstellar radio message that unambiguously arises from intelligent life. A modulated signal, beep, 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 comprising the numbers 1, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, the first dozen prime numbers, could have only a biological origin. No prior agreement between civilizations and no precautions against Earth chauvinism are required to make this clear. Such a message would be an announcement or beacon signal indicating the presence of an advanced civilization but communicating very little about its nature. The beacon signal might also note a particular frequency where the main message is to be found, or might indicate that the principal message can be found at higher time resolution at the frequency of the beacon signal. The communication of quite complex information is not very difficult, even for civilizations with extremely different biologies and social conventions. Arithmetical statements can be transmitted, some true and some false, each followed by an appropriate coded word in das and dits, for example. which would transmit the ideas of true and false concepts that many people might guess would be extremely difficult to communicate in such a context. But by far the most promising method is to send pictures. A repeated message that is the product of two prime numbers is clearly to be decoded as a two-dimensional array, or raster, that is, a picture. The product of three prime numbers might be a three-dimensional still picture or one frame of a two-dimensional motion picture. As an example of such a message, consider an array of zeros and ones which could be long and short beeps or tones on two adjacent frequencies, or tones of different amplitudes, or even signals with different radio polarizations. In 1974, such a message was transmitted to space from the 305-meter antenna at the Arecibo Observatory in Puerto Rico, which Cornell University runs for the National Science Foundation. The occasion was a ceremony marking the resurfacing of the Arecibo dish, the largest radio radar telescope on the planet Earth. The signal was sent to a collection of stars called M13, a globular cluster comprising about 1 million separate suns, which happened to be overhead at the time of the ceremony. Since M13 is 24,000 light-years away, the message will take 24,000 years to arrive there. If any responsive creature is listening, it will be 48,000 years before we receive a reply. The Arecibo message was clearly intended not as a serious attempt at interstellar communication, but rather as an indication of the remarkable advances in terrestrial radio technology. The decoded message says something like this: "Here is how we count. From 1 to 10, here are the atomic numbers of 5 chemical elements, hydrogen, carbon, nitrogen, oxygen, and phosphorus, that we think are interesting or important. Here are some ways to put these atoms together: the molecules, adenine, thymine, guanine, and cytosine, and a chain composed of alternating sugars and phosphates. These molecular building blocks are in turn put together to form a long molecule of DNA comprising about 4 billion links in the chain. The molecule is a double helix. In some way, this molecule is important for the clumsy-looking creature at the center of the message. That creature is 14 radio wavelengths, or about 176 centimeters high. There are about 4 billion of these creatures on the third planet from our star. There are 9 planets altogether, 4 little ones on the inside, 4 big ones toward the outside, and 1 little one at the extremity. This message is brought to you courtesy of a radio telescope 2,430 wavelengths, or 306 meters, in diameter. Yours truly. With many similar pictorial messages, each consistent with and corroborating the others, it is very likely that almost unambiguous interstellar radio communication could be achieved even between two civilizations that have never met. Our immediate objective is not to send such messages because we are very young and backward. We wish to listen. The detection of intelligent radio signals from the depths of space would approach in an experimental and scientifically rigorous manner many of the most profound questions that have concerned scientists and philosophers since prehistoric times. Such a signal would indicate that the origin of life is not an extraordinary, difficult, or unlikely event. It would imply that given billions of years for natural selection, simple forms of life evolve generally into complex and intelligent forms, as on Earth, and that such intelligent forms commonly produce an advanced technology, as has also occurred here. But it is not likely that the transmissions we receive will be from a society at our own level of technological advance. A society only a little more backward than ours will not have radio astronomy at all. The most likely case is that the message will be from a civilization far in our technological future. Thus, even before we decode such a message, we will have gained an invaluable piece of knowledge, that it is possible to avoid the dangers of the period through which we are now passing. There are some who look on our global problems here on Earth, at our vast national antagonisms, our nuclear arsenals, our growing populations, the disparity between the poor and the affluent, shortages of food and resources, and our inadvertent alterations of the natural environment, and conclude that we live in a system that has suddenly become unstable, a system that is destined soon to collapse. There are others who believe that our problems are soluble, that humanity is still in its childhood, that one day soon we will grow up. The receipt of a single message from space would show that it is possible to live through such technological adolescence. The transmitting civilization, after all, has survived. Such knowledge, it seems to me, might be worth a great price. Another likely consequence of an interstellar message is a strengthening of the bonds that join all human and other beings on our planet. The sure lesson of evolution is that organisms elsewhere must have separate evolutionary pathways, that their chemistry and biology and very likely their social organizations will be profoundly dissimilar to anything on Earth. We may well be able to communicate with them because we share a common universe, because the laws of physics and chemistry and the regularities of astronomy are universal. But they may always be in the deepest sense different, and in the face of this difference the animosities that divide the peoples of the earth may wither. The differences among human beings of separate races and nationalities, religions and sexes, are likely to be insignificant compared to the differences between all human and all extraterrestrial intelligent beings. If the message comes by radio, both transmitting and receiving civilizations will have in common at least a knowledge of radio physics. The commonality of the physical sciences is the reason that many scientists expect the messages from extraterrestrial civilizations to be decodable, probably in a slow and halting manner, but unambiguously nevertheless. No one is wise enough to predict in detail what the consequences of such a decoding will be because no one is wise enough to understand beforehand what the nature of the message will be. Since the transmission is likely to be from a civilization far in advance of our own, stunning insights are possible in the physical, biological, and social sciences in the novel perspective of a quite different kind of intelligence. But decoding will probably be a task of years and decades. Some have worried that a message from an advanced society might make us lose faith in our own, might deprive us of the initiative to make new discoveries, if it seemed that others had made those discoveries already, or might have other negative consequences. This is rather like a student dropping out of school because his teachers and textbooks are more learned than he is. We are free to ignore an interstellar message if we find it offensive. If we choose not to respond, there is no way for the transmitting civilization to determine that its message was received and understood on the tiny distant planet Earth. The translation of a radio message from the depths of space, about which we can be as slow and cautious as we wish, seems to pose few dangers to mankind. Instead, it holds the greatest promise of both practical and philosophical benefits. In particular, it is possible that among the first contents of such a message may be detailed prescriptions for the avoidance of technological disaster, for a passage through adolescence to maturity. Perhaps the transmissions from advanced civilizations will describe which pathways of cultural evolution are likely to lead to the stability and longevity of an intelligent species, and which other paths lead to stagnation or degeneration or disaster. There is, of course, no guarantee that such would be the contents of an interstellar message, but it would be foolhardy to overlook the possibility. Perhaps there are straightforward solutions, still undiscovered on Earth, to problems of food shortages, population growth, energy supplies, dwindling resources, pollution, and war. While there will surely be differences among civilizations, there may well be laws of development of civilizations which cannot be glimpsed until information is available about the evolution of many civilizations. Because of our isolation from the rest of the cosmos, we have information on the evolution of only one civilization, our own, and the most important aspect of that evolution, the future, remains closed to us. Perhaps it is not likely, but it is certainly possible that the future of human civilization depends on the receipt and decoding of interstellar messages from extraterrestrial civilizations. And what if we make a long-term, dedicated search for extraterrestrial intelligence and fail? Even then, we surely will not have wasted our time. We will have developed an important technology with applications to many other aspects of our own civilization. We will have added greatly to our knowledge of the physical universe, and we will have calibrated something of the importance and uniqueness of our species, our civilization, and our planet. For if intelligent life is scarce or absent elsewhere, we will have learned something significant about the rarity and value of our culture and our biological patrimony, painstakingly extracted over 4.6 billion years of tortuous evolutionary history. Such a finding will stress, as perhaps nothing else can, our responsibilities to the dangers of our time, because the most likely explanation of negative results after a comprehensive and resourceful search is that societies commonly destroy themselves before they are advanced enough to establish a high-power radio transmitting service. In an interesting sense, the organization of a search for interstellar radio messages, quite apart from the outcome, is likely to have a cohesive and constructive influence on the whole of the human predicament. But we will not know the outcome of such a search, much less the contents of messages from interstellar civilizations, if we do not make a serious effort to listen for signals. It may be that civilizations are divided into two great classes: those that make such an effort, achieve contact, and become new members of a loosely tied federation of galactic communities, and those that cannot or choose not to make such an effort, or who lack the imagination to try, and who in consequence soon decay and vanish. It is difficult to think of another enterprise within our capability and at a relatively modest cost that holds as much promise for the future of humanity. Part V. Ultimate. Questions. Chapter 23. A Sunday sermon, extinguished theologians lie about the cradle of every science as the strangled snakes beside the cradle of Hercules. T. H. Huxley, 1860. We have seen the highest circle of spiraling powers. We have named this circle God. We might have given it any other name we wished. Abyss, mystery, absolute darkness, absolute light, matter, spirit, ultimate hope, ultimate despair, silence. Nikos Kazantzakis, 1948. These days. I often find myself giving scientific talks to popular audiences. Sometimes I am asked to discuss planetary exploration and the nature of the other planets. Sometimes the origin of life or intelligence on Earth, sometimes the search for life elsewhere, and sometimes the grand cosmological perspective. Since I have more or less heard these talks before, the question period holds my greatest interest. It reveals the attitudes and concerns of people. The most common questions asked are on unidentified flying objects and ancient astronauts. What I believe are thinly disguised religious queries, almost as common, particularly after a lecture in which I discuss the evolution of life or intelligence, is, do you believe in God? Because the word God means many things to many people. I frequently reply by asking what the questioner means by God. To my surprise, this response is often considered puzzling or unexpected. Oh, you know God? Everyone knows who God is. Or, well, kind of a force that is stronger than we are and that exists everywhere in the universe. There are a number of such forces. One of them is called gravity, but it is not often identified with God. And not everyone does know what is meant by God. The concept covers a wide range of ideas. Some people think of God as an outsized light-skinned male with a long white beard sitting on a throne somewhere up there in the sky, busily tallying the fall of every sparrow. Others, for example, Baruch Spinoza and Albert Einstein, considered God to be essentially the sum total of the physical laws which describe the universe. I do not know of any compelling evidence for anthropomorphic patriarchs controlling human destiny from some hidden celestial vantage point, but it would be madness to deny the existence of physical laws. Whether we believe in God depends very much on what we mean by God. In the history of the world, there have been probably tens of thousands of different religions. There is a well-intentioned pious belief that they are all fundamentally identical. In terms of an underlying psychological resonance, there may indeed be important similarities at the cores of many religions, but in the details of ritual and doctrine, and the apology is considered to be authenticating, the diversity of organized religions is striking. Human religions are mutually exclusive on such fundamental issues as one God versus many, the origin of evil, reincarnation, idolatry, magic, and witchcraft, the role of women, dietary prescriptions, rites of passage, ritual sacrifice, direct or mediated access to deities, slavery, intolerance of other religions, and the community of beings to whom special ethical considerations are due. We do no service to religion in general or to any doctrine in particular if we paper over these differences. Instead, I believe we should understand the world views from which differing religions derive and seek to understand what human needs are fulfilled by those differences. Bertrand Russell once told of being arrested because he peacefully protested Britain's entry into World War I. The jailer asked, then a routine question for new arrivals, Russell's religion. Russell replied, agnostic, which he was asked to spell. The jailer smiled benignly, shook his head, and said, there's many different religions, but I suppose we all worship the same God. Russell commented that the remark cheered him for weeks, and there may not have been much else to cheer him in that prison, although he did manage to write the entire introduction to mathematical philosophy and started reading for his work. The analysis of mind within its confines. Many of the people who ask whether I believe in God are requesting reassurance that their particular belief system, whatever it is consistent with modern scientific knowledge. Religion has been scarred in its confrontation with science and many people, but by no means all are reluctant to accept a body of theological belief that is too obviously in conflict with what else we know. Apollo 8 accomplished the first manned lunar circumnavigation. In a more or less spontaneous gesture, the Apollo 8 astronauts read from the first verse of the book of Genesis. In part, I believe, to reassure the taxpayers back in the United States that there were no real inconsistencies between conventional religious outlooks and a manned flight to the moon. Orthodox Muslims, on the other hand, were outraged after Apollo 11 astronauts accomplished the first manned lunar landing because the moon has a special and sacred significance in Islam. In a different religious context, after Yuri Gagarin's first orbital flight, Nikita Khrushchev, the chairman of the Council of Ministers of the USSR, noted that Gagarin had stumbled on no gods or angels up there. That is, Khrushchev reassured his audience that manned orbital flight was not inconsistent with its beliefs. In the 1950s, a Soviet technical journal called Voprosy Filosofu, Problems in Philosophy, published an article that argued very unconvincingly. It seemed to me that dialectical materialism required there to be life on every planet. Sometime later, an agonized official rebuttal appeared, decoupling dialectical materialism from exobiology, a clear prediction in an area undergoing vigorous study permits doctrines to be subject to disproof. The last posture a bureaucratic religion wishes to find itself in is vulnerability to disproof, where an experiment can be performed on which the religion stands or falls. And so the fact that life has not been found on the moon has left the foundations of dialectical materialism unshaken. Doctrines that make no predictions are less compelling than those which make correct predictions. They are in turn more successful than doctrines that make false predictions. But not always. One prominent American religion confidently predicted that the world would end in 1914. Well, 1914 has come and gone, and while the events of that year were certainly of some importance, the world does not, at least so far as I can see, seem to have ended. There are at least 3 responses that an organized religion can make in the face of such a failed and fundamental prophecy. They could have said, oh, did we say 1914? So sorry, we meant 2014. A slight error in calculation. Hope you weren't inconvenienced in any way. But they did not. They could have said, well, the world would have ended, except we prayed very hard and interceded with God so he spared the earth. But they did not. Instead, they did something much more ingenious. They announced that the world had in fact ended in 1914, and if the rest of us hadn't noticed, that was our lookout. It is astonishing in the face of such transparent evasions that this religion has any adherents at all. But religions are tough. Either they make no contentions which are subject to disproof, or they quickly redesign doctrine after disproof. The fact that religions can be so shamelessly dishonest, so contemptuous of the intelligence of their adherents, and still flourish does not speak very well for the tough-mindedness of the believers. But it does indicate, if a demonstration were needed, that near the core of the religious experience is something remarkably resistant to rational inquiry. Andrew Dixon White was the intellectual guiding light, founder and first president of Cornell University. He was also the author of an extraordinary book called The Warfare of Science with Theology in Christendom. considered so scandalous at the time it was published that his co-author requested his name omitted. White was a man of substantial religious feeling, but he outlined the long and painful history of erroneous claims which religions had made about the nature of the world, and how, when people directly investigated the nature of the world and discovered it to be different from doctrinal contentions, such people were persecuted and their ideas suppressed. The aged Galileo was threatened by the Catholic hierarchy with torture because he proclaimed the earth to move. Spinoza was excommunicated by the Jewish hierarchy, and there is hardly an organized religion with a firm body of doctrine which has not at one time or another persecuted people for the crime of open inquiry. Cornell's own devotion to free and non-sectarian inquiry was considered so objectionable in the last quarter of the 19th century that ministers advised high school graduates that it was better to receive no college education than to attend so impious an institution. Indeed, this sage chapel was constructed in part to placate the pious, although I am glad to say it has from time to time made serious efforts at open-minded ecumenicism. Many of the controversies which White describes are about origins. It used to be believed that every event in the world, the opening of a morning glory, let us say, was due to direct micro-intervention by the deity. The flower was unable to open by itself. God had to say, "Hey, flower, open." The application of this idea to human affairs has often had desultory social consequences. For one thing, it seems to imply that we are not responsible for our actions. If the play of the world is produced and directed by an omnipotent and omniscient God, does it not follow that every evil that is perpetrated is God's doing? I know this idea is an embarrassment in the West, and attempts to avoid it include the contention that what seems to be evil is really part of the divine plan, too complex for us to fathom, or that God chose to cloud his own vision about the causality skein when he set out to make the world. There is nothing utterly impossible about these philosophical rescue attempts, but they do seem to have very much the character of propping up a teetering ontological structure. In addition, the idea of micro-intervention in the affairs of the world has been used to support the established social, political, and economic conventions. There was, for example, the idea of a divine right of kings, seriously argued by philosophers such as Thomas Hobbes. If you had revolutionary thoughts directed, let us say, toward George III, you were guilty of blasphemy and impiety, religious crimes, as well as such more commonplace political crimes as treason. There are many legitimate scientific issues relating to origins and ends. What is the origin of the human species? Where did plants and animals come from? How did life arise? The earth, the planets, the sun, the stars. Does the universe have an origin? And if so, what? And finally, a still more fundamental and exotic question, which many scientists would say is essentially untestable and therefore meaningless. Why are the laws of nature the way they are? The idea that a god or gods is necessary to effect one or more of these origins has been under repeated attack over the last few thousand years. Because we know something about phototropism and plant hormones, we can understand the opening of the morning glory independent of divine micro-intervention. It is the same for the entire skein of causality back to the origin of the universe. As we learn more and more about the universe, there seems less and less for God to do. Aristotle's view was of God as an unmoved prime mover, a roi faineant, a do-nothing king who establishes the universe in the first place, and then sits back and watches the intricate intertwined chains of causality course down through the ages. But this seems abstract and removed from everyday experience. It is a little unsettling and pricks at human conceits. Humans seem to have a natural abhorrence of an infinite regression of causes, and this distaste is at the root of the most famous and most effective demonstrations of the existence of God by Aristotle and Thomas Aquinas. But these thinkers lived before the infinite series was a mathematical commonplace. If the differential and integral calculus or transfinite arithmetic had been invented in Greece in the 5th century BC, and not subsequently suppressed, the history of religion in the West might have been very different, or at any rate, we would have seen less of the pretension that theological doctrine can be convincingly demonstrated by rational argument to those who reject alleged divine revelation, as Aquinas attempted in the Summa contra Gentiles. When Newton explained the motion of the planets by the universal theory of gravitation, it no longer was necessary for angels to push and pummel the planets about. When Pierre Simon, the Marquis de Laplace, proposed to explain the origin of the solar system, although not the origin of matter in terms of physical laws as well, even the necessity for a god involved in the origins of things seemed profoundly challenged. Laplace is said to have presented an edition of his seminal mathematical work, Mécanique Céleste, to Napoleon aboard ship in the Mediterranean during the Napoleonic expedition to Egypt, 1798 to 1799. A few days later, so the story goes, Napoleon complained to Laplace that he had found no mention of God in the text. Laplace's response has been recorded, "Sire, I have no need of that hypothesis." The idea of God as a hypothesis rather than as an obvious truth is by and large a modern idea in the West, although it was certainly discussed seriously and wryly by the Ionian philosophers of 2,400 years ago. It is often considered that at least the origin of the universe requires a God, indeed, an Aristotelian idea. This is a point worth looking at in a little more detail. First of all, it is perfectly possible that the universe is infinitely old and therefore requires no creator. This is consistent with existing knowledge of cosmology, which permits an oscillating universe in which the events since the Big Bang are merely the latest incarnation in an infinite series of creations and destructions of the universe. But secondly, let us consider the idea of a universe created somehow from nothing by God. The question naturally arises, and many 10-year-olds spontaneously think of it before being discouraged by their elders: where does God come from? If we answer that God is infinitely old or present simultaneously in all epochs, we have solved nothing, except perhaps verbally. We have merely postponed by one step coming to grips with the problem. A universe that is infinitely old and a God that is infinitely old are, I think, equally deep mysteries. It is not readily apparent why one should be considered more reliably established than the other. Spinoza might have said that the two possibilities are not really different ideas at all. I think it is wise when coming face to face with such profound mysteries to feel a little humility. The idea that scientists or theologians, with our present still puny understanding of this vast and awesome cosmos, can comprehend the origins of the universe is only a little less silly than the idea that Mesopotamian astronomers of 3,000 years ago, from whom the ancient Hebrews borrowed, during the Babylonian captivity, the cosmological accounts in the first chapter of Genesis, could have understood the origins of the universe. We simply do not know. The Hindu holy book, the Rig Veda, X 129, has a much more realistic view of the matter. Who knows for certain? Who shall here declare it? Whence was it born? Whence came creation? The gods are later than this world's formation. Who then can know the origins of the world? None knows whence creation arose, and whether he has or has not made it, he who surveys it from the lofty skies, only he knows, or perhaps he knows not. But the times we live in are very interesting ones. Questions of origins, including some questions relating to the origin of the universe, may in the next few decades be amenable to experimental inquiry. There is no conceivable answer to the grand cosmological questions which will not resonate with the religious sensibilities of human beings, but there is a chance that the answers will discomfit a great many bureaucratic and doctrinal religions. The idea of religion as a body of belief, immune to criticism, fixed forever by some founder is, I think, a prescription for the long-term decay of the religion, especially lately. In questions of origins and ends, the religious and the scientific sensibilities have much the same objectives. Human beings are built in such a way that we passionately wish to answer these questions, perhaps because of the mystery of our own individual origins. But our contemporary scientific insights, while limited, are much deeper than those of our Babylonian predecessors of 1000 BC religions unwilling to accommodate to change, both scientific and social, are, I believe, doomed. A body of belief cannot be alive and relevant, vibrant and growing, unless it is responsive to the most serious criticism that can be mustered against it. The First Amendment to the United States Constitution encourages a diversity of religions but does not prohibit criticism of religion. In fact, it protects and encourages criticism of religion. Religions ought to be subject to at least the same degree of skepticism as, for example, contentions about UFO visitations or Velikovskian catastrophism. I think it is healthy for the religions themselves to foster skepticism about the fundamental underpinnings of their evidential bases. There is no question that religion provides a solace and support, a bulwark in time of emotional need, and can serve extremely useful social roles. But it by no means follows that religion should be immune from testing, from critical scrutiny, from skepticism. It is striking how little skeptical discussion of religion there is in the nation that Tom Paine, the author of The Age of Reason, helped to found. I hold that belief systems that cannot survive scrutiny are probably not worth having. Those that do survive scrutiny probably have at least important kernels of truth within them. Religion used to provide a generally accepted understanding of our place in the universe that surely has been one of the major objectives of myth and legend, philosophy and religion, as long as there have been human beings. But the mutual confrontation of differing religions and of religion with science has eroded those traditional views, at least in the minds of many. The way to find out about our place in the universe is by examining the universe and by examining ourselves without preconceptions, with as unbiased a mind as we can muster. We cannot begin with an entirely clean slate, since we arrive at this problem with predispositions of hereditary and environmental origin. But after understanding such built-in biases, is it not possible to pry insights from nature? Proponents of doctrinal religions, ones in which a particular body of belief is prized and infidels scorned, will be threatened by the courageous pursuit of knowledge. We hear from such people that it may be dangerous to probe too deeply. Many people have inherited their religion, like their eye color. They consider it not a thing to think very deeply about, and in any case beyond our control. But those with a set of beliefs they profess to feel deeply about, which they have selected without an unbiased sifting through the facts and the alternatives, will feel uncomfortably challenged by searching questions. Anger at queries about our beliefs is the body's warning signal. Here lies unexamined and probably dangerous doctrinal baggage. Christianus Huygens wrote a remarkable book around 1670, in which bold and prescient speculations were made about the nature of the other planets in the solar system. Huygens was well aware that there were those who held such speculations and his astronomical observations objectionable, but perhaps they'll say, Huygens mused, it does not become us to be so curious and inquisitive in these things, which the Supreme Creator seems to have kept for his own knowledge, for since he has not been pleased to make any farther discovery or revelation of them, it seems little better than presumption to make any inquiry into that which he has thought fit to hide. But these gentlemen must be told, Huygens then thundered, that they take too much upon themselves when they pretend to appoint how far and no farther men shall go in their searches, and to set bounds to other men's industry, as if they knew the marks that God has placed to knowledge, or as if men were able to pass those marks. If our forefathers had been at this rate scrupulous, we might have been ignorant still of the magnitude and figure of the earth, or that there was such a place as America. If we look at the universe in the large, we find something astonishing. First of all, we find a universe that is exceptionally beautiful, intricately and subtly constructed. Whether our appreciation of the universe is because we are a part of that universe, whether, no matter how the universe were put together, we would have found it beautiful, is a proposition to which I do not pretend to have an answer. But there is no question that the elegance of the universe is one of its most remarkable properties. At the same time, there is no question that there are cataclysms and catastrophes occurring regularly in the universe and on the most awesome scale. There are, for example, quasar explosions which probably decimate the nuclei of galaxies. It seems likely that every time a quasar explodes, more than 1 million worlds are obliterated and countless forms of life, some of them intelligent, are utterly destroyed. This is not the traditional benign universe of conventional religiosity in the West, constructed for the benefit of living and especially of human beings. Indeed, the very scale of the universe, more than 100 billion galaxies, each containing more than 100 billion stars, speaks to us of the inconsequentiality of human events in the cosmic context. We see a universe simultaneously very beautiful and very violent. We see a universe that does not exclude a traditional Western or Eastern God, but that does not require one either. My deeply held belief is that if a God of anything like the traditional sort exists, our curiosity and intelligence are provided by such a God. We would be unappreciative of those gifts, as well as unable to take such a course of action if we suppressed our passion to explore the universe and ourselves. On the other hand, if such a traditional God does not exist, our curiosity and our intelligence are the essential tools for managing our survival. In either case, the enterprise of knowledge is consistent with both science and religion, and is essential for the welfare of the human species. White seems also to have been responsible for the exemplary custom of not awarding honorary doctoral degrees at Cornell University. He was concerned about a potential abuse, that honorary degrees would be traded for financial gifts and bequests. White was a man of strong and courageous ethical standards. Many statements about God are confidently made by theologians on grounds that today at least sound specious. Thomas Aquinas claimed to prove that God cannot make another God, or commit suicide, or make a man without a soul, or even make a triangle whose interior angles do not equal 180 degrees. But Bolyai and Lobachevsky were able to accomplish this last feat on a curved surface in the 19th century, and they were not even approximately gods. It is a curious concept, this, of an omnipotent God with a long list of things he is forbidden to do by the fiat of the theologians. It is a charming notion that Napoleon actually spent his days aboard ship perusing the highly mathematical Mécanique Céleste. But he was seriously interested in science and made an earnest attempt to survey the latest findings. See The Society of Arcueil, A View of French Science at the Time of Napoleon I, by Maurice Crosland, Cambridge, Harvard University Press, 1967. Napoleon did not pretend to read all of the Mécanique Céleste, and Riley wrote to Laplace on another occasion, "The first 6 months which I can spare will be employed in reading it." But he also remarked, on another of Laplace's books, "Your works contribute to the glory of the nation. The progress and perfection of mathematics are linked closely with the prosperity of the state." However, from astronomical arguments, Aristotle concluded that there were several dozen unmoved prime movers in the universe. Aristotelian arguments for a prime mover would seem to have polytheistic consequences that might be considered dangerous by contemporary Western theologians. This subject is rich in irony. Augustine was born in Africa in 354 AD, and in his early years was a Manichaean, an adherent of a dualistic view of the universe in which good and evil are in conflict on roughly equal terms, and which was later condemned as a heresy by Christian orthodoxy. The possibility that all was not right with Manichaeanism occurred to Augustine when he was studying its astronomy. He discovered that even the leading figures in the faith could not justify its murky astronomical notions. This contradiction between theology and science on matters astronomical was the initial impetus moving him toward Catholicism, the religion of his mother, which in later centuries persecuted scientists such as Galileo for trying to improve our understanding of astronomy. Augustine later became Saint Augustine, one of the major intellectual figures in the history of the Roman Catholic Church, and his mother became Saint Monica, after whom a suburb of Los Angeles is named. Bertrand Russell wondered what Augustine's view of the conflict between astronomy and theology would have been had he lived in the time of Galileo. Chapter 24. Gott and the Turtles. Now entertain conjecture of a time when creeping murmur and the pouring dark fills the wide vessel of the universe. William Shakespeare, Henry V, Act 5, Prologue. In the earliest myths and legends of our species, there is a common and understandable view of the cosmos. It is anthropocentric. There were gods, to be sure, but the gods had feelings and weaknesses and were very human. Their behavior was seen as capricious. They could be propitiated by sacrifice and prayer. They intervened regularly in human affairs. Various factions of gods supported opposing sides in human warfare. The Odyssey expresses a generally held view that it is wise to be kind to strangers. They may be gods in disguise. Gods mate with humans, and the offspring are generally indistinguishable, at least in appearance, from people. The gods live on mountains or in the sky or in some subterranean or submarine realm, at any rate, far off. It was difficult, unambiguously, to come upon a god, and so it was hard to check a story told about the gods. Sometimes their actions were controlled by more powerful beings yet, as the Fates controlled the Olympian gods. The nature of the universe as a whole, its origin and fate, were not considered well understood in the Vedic myths. Doubt is raised not only about whether the gods created the world, but even about whether the gods know who did create it. Hesiod in his Cosmogony says that the universe was created from or maybe by chaos, perhaps only a metaphor for the difficulty of the problem. Some ancient Asian cosmological views are close to the idea of an infinite regression of causes, as exemplified in the following apocryphal story. A Western traveler encountering an Oriental philosopher asks him to describe the nature of the world. It is a great ball resting on the flat back of the world turtle. Ah, yes, but what does the world turtle stand on? On the back of a still larger turtle? Yes, but what does he stand on? A very perceptive question. But it's no use, mister. It's turtles all the way down. We now know that we live on a tiny dust mote in an immense and humbling universe. The gods, if they exist, no longer intervene daily in human affairs. We do not live in an anthropocentric universe. And the nature, origin, and fate of the cosmos seem to be mysteries far more profound than they were perceived to be by our remote ancestors. But the situation is once again changing. Cosmology, the study of the universe as a whole, is becoming an experimental science. Information obtained by optical and radio telescopes on the ground, by ultraviolet and X-ray telescopes in Earth orbit, by the measurement of nuclear reactions in laboratories, and by determinations of the abundance of chemical elements in meteorites, is shrinking the arena of permissible cosmological hypotheses, and it is not too much to expect that we will soon have firm observational answers to questions once considered the exclusive preserve of philosophical and theological speculation. This observational revolution began from an unlikely source. In the second decade of this century, there was, as there still is in Flagstaff, Arizona, an astronomical facility called the Lowell Observatory, established by none other than Percival Lowell, for whom the search for life on other planets was a consuming passion. It was he who popularized and promoted the idea that Mars was crisscrossed with canals, which he believed to be the artifacts of a race of beings enamored of hydraulic engineering. We now know that the canals do not exist at all. They apparently were the product of wishful thinking and the limitations of observing through the Earth's murky atmosphere. Among his other interests, Lowell was concerned with the spiral nebulae, exquisite pinwheel-shaped luminous objects in the sky, which we now know to be distant collections of hundreds of billions of individual stars, like the Milky Way galaxy of which our Sun is a part. But at that time, there was no way to determine the distance to these nebulae, and Lowell was interested in an alternative hypothesis, that the spiral nebulae were not enormous, distant, multistellar entities, but rather smaller, closer objects which were the early stages of the condensation of an individual star out of the interstellar gas and dust. As such, gas clouds contract under their self-gravitation. The conservation of angular momentum requires that they speed up to rapid rotation and shrink to a thin disk. Rapid rotation can be detected astronomically by spectroscopy. Letting light from a distant object pass consecutively through a telescope, a narrow slit, and a glass prism or other device, which spreads white light out into a rainbow of colors. The spectrum of starlight contains bright and dark lines here and there in the rainbow, images of the slit of the spectrometer. An example is the bright yellow lines emitted by sodium, apparent as we throw a small piece of sodium into a flame. Material made of many different chemical elements will show many different spectral lines. The displacement of these spectral lines from their usual wavelengths when the light source is at rest gives us information on the velocity of the source toward and away from us. a phenomenon called the Doppler effect and familiar to us. In the physics of sound, as the increase or decrease in the pitch of an automobile horn as the car rapidly approaches or recedes, Lowell is thought to have asked a young assistant VM, Slipher, to check the larger spiral nebulae to determine whether one side showed spectral lines shifted toward the red and the other toward the blue, from which it would be possible to deduce the speed of rotation of the nebula. Slipher investigated the spectra of the nearby spiral nebulae, but found to his amazement that almost all of them showed a red shift, with virtually no sign of blue shifts anywhere in them. He had found not rotation, but recession. It was as if all the spiral nebulae were retreating from us. A much more extensive set of observations was obtained in the 1920s at the Mount Wilson Observatory by Edwin Hubble and Milton Humason. Hubble and Humason developed a method of determining the distance to the spiral nebulae. It became apparent that they were not condensing gas clouds relatively nearby in the Milky Way galaxy, but themselves great galaxies millions or more light-years away. To their amazement, they also found that the more distant the galaxy, the faster it was receding from us. Since it is unlikely that there is anything special about our position in the cosmos, this is best understood in terms of a general expansion of the universe. All galaxies recede from all others, so that an astronomer on any galaxy would observe all other galaxies apparently retreating. If we extrapolate such a mutual recession back into the past, we find that there was a time, perhaps 15 billion or 20 billion years ago, when all of the galaxies must have been touching, that is, confined to an extremely small volume of space. Matter in its present form could not survive such astonishing compressions. The very earliest stages of that expanding universe must have been dominated by radiation rather than matter. It is now conventional to talk of this time as the Big Bang. Three kinds of explanation have been offered for this expansion of the universe: the steady state, Big Bang, and oscillating universe cosmologies. In the steady state hypothesis, the galaxies recede from one another, the more distant galaxies moving with very high apparent velocities, their light shifted by the Doppler effect to longer and longer wavelengths. There will be a distance at which a galaxy will be moving so fast that it passes over what is called its event horizon and from our vantage point disappears. There is a distance so great that, in an expanding universe, there is no chance of getting information from beyond it. As time goes on, if nothing else intervenes, more and more galaxies will disappear over the edge. But in the steady-state cosmology, the matter lost over the edge is exactly compensated for by new matter continuously created everywhere, matter that eventually condenses into new galaxies. With the rate of disappearance of galaxies over the event horizon just balanced by the creation of new galaxies, the universe looks more or less identical from every place and in every epoch. In the steady-state cosmology, there is no Big Bang. 100 billion years ago, the universe would have looked just the same, and 100 billion years from now, likewise. But where does the new matter come from? How can matter be created from nothing? Proponents of the steady-state cosmology answer that it comes from whatever place proponents of the Big Bang get their bang from. If we can imagine all the matter in the universe discontinuously created from nothing 15 billion to 20 billion years ago, why are we unable to imagine it being created in a tenuous trickle everywhere continuously and forever? If the steady-state hypothesis is true, there was never a time when the galaxies were much closer. The universe in its largest structures is then unchanging and infinitely old. But as placid and, in a strange way, as satisfying as the steady-state cosmology is, there is strong evidence against it. Whenever a sensitive radio telescope is pointed anywhere in the sky, the constant chatter of a kind of cosmic static can be detected. The characteristics of this radio noise match almost exactly what we would expect if the early universe was hot and filled with radiation in addition to matter. The cosmic blackbody radiation is very nearly the same everywhere in the sky and looks very much to be the distant rumblings of the Big Bang cooled and enfeebled by the expansion of the universe, but coursing still down the corridors of time. The primeval fireball, the explosive event that initiated the expanding universe, can be observed. Supporters of the steady-state cosmology must now be reduced to positing a large number of special sources of radiation, which together somehow mimic exactly the cooled primeval fireball, or proposing that the universe far beyond the event horizon is steady-state, but by a peculiar accident, we live in a kind of expanding bubble, a violent pimple in a much vaster but more placid universe. This idea has the advantage or flaw, depending on your point of view, of being impossible to disprove by any conceivable experiment, and virtually all cosmologists have abandoned the steady-state hypothesis. If the universe is not in a steady state, then it is changing, and such changing universes are described by evolutionary cosmologies. They begin in one state, and they end in another. What are the possible fates of the universe in evolutionary cosmologies? If the universe continues to expand at its present rate and galaxies continue to disappear over the event horizon, there will eventually be less and less matter in the visible universe. The distances between galaxies will increase, and there will be fewer and fewer of the spiral nebulae for the successors of Slipher, Hubble, and Humason to view. Eventually, the distance from our galaxy to the nearest galaxy will exceed the distance to the event horizon, and astronomers will no longer be able to see even the nearest galaxy except in very old books and photographs. Because of the gravity that holds the stars in our galaxy together, the expanding universe will not dissipate our galaxy, but even here a strange and desolate fate awaits us. For one thing, the stars are evolving, and in tens or hundreds of billions of years most present stars will have become small and dark dwarf stars. The remainder will have collapsed to neutron stars or black holes. No new matter will be available for a vigorous younger generation of stars. The sun, the stars, the entire Milky Way galaxy will slowly turn off. The lights in the night sky will go out. But in such a universe there is a further evolution still. We are used to the idea of radioactive elements, certain kinds of atoms that spontaneously decay or fall to pieces. Ordinary uranium is one example. But we are less familiar with the idea that every atom except iron is radioactive given a long enough period of time. Even the most stable atoms will radioactively decay, emit alpha and other particles, and fall to pieces, leaving only iron if we wait long enough. How long? The American physicist Freeman Dyson of the Institute for Advanced Study calculates that the half-life of iron is about 10,500 years, a 1 followed by 500 zeros, a number so large that it would take a dedicated numerologist the better part of 10 minutes just to write it down. So if we wait just a little longer, 10,600 years would do just fine. Not only would the stars have gone out, but all the matter in the universe not in neutron stars or black holes would have decayed into the ultimate nuclear dust. Eventually, galaxies will have vanished altogether, suns will have blackened, matter disintegrated, and no conceivable possibility will remain for the survival of life or intelligence or civilizations. A cold and dark and desolate death of the universe. But need the universe expand forever? If I stand on a small asteroid and throw a rock up, it will leave the asteroid there being on such a worldlet not enough gravity to drag the rock back. If I throw the same rock at the same speed from the surface of the Earth, it will of course turn around and fall down because of the substantial gravity of our planet. But the same sort of physics applies to the universe as a whole. If there is less than a certain amount of matter, each galaxy will feel an insufficient tug from the gravitational attraction of the others to be slowed down appreciably, and the expansion of the universe will continue forever. On the other hand, if there is more than a certain critical mass, the expansion will eventually slow, and we will be saved from the desolation teleology of a universe that expands forever. What then would be the fate of the universe? Why then, an observer would see expansion eventually replaced by contraction, the galaxies slowly and then at an ever-increasing pace approaching one another. A careening, devastating smashing together of galaxies, worlds, life, civilizations, and matter until every structure in the universe is utterly destroyed and all the matter in the cosmos converted into energy, instead of a universe ending in cold and tenuous desolation, a universe finishing in a hot and dense fireball. It is very likely that such a fireball would rebound, leading to a new expansion of the universe, and, if the laws of nature remain the same, a new incarnation of matter, a new set of condensations of galaxies and stars and planets, a new evolution of life and intelligence. But information from our universe would not trickle into that next one, and from our vantage point, such an oscillating cosmology is as definitive and depressing an end as the expansion that never stops. The distinction between a Big Bang with expansion forever and an oscillating universe clearly turns on the amount of matter there is. If the critical amount of matter is exceeded, we live in an oscillating universe. Otherwise, we live in one that expands forever. The expansion times, measured in tens of billions of years, are so long that these cosmological issues do not affect any immediate human concerns. But they are of the most profound import for our view of the nature and fate of the universe and only a little more remotely of ourselves. In a remarkable scientific paper published in the December 15, 1974 issue of the Astrophysical Journal, a wide range of observational evidence is brought to bear on the question of whether the universe will continue to expand forever, an open universe, or whether it will gradually slow down and recontract, a closed universe, perhaps as part of an infinite series of oscillations. The work is by J. Richard Gott III and James E. Gunn, then both of the California Institute of Technology, and David N. Schramm and Beatrice M. Tinsley, then of the University of Texas. In one of their arguments, they review calculations of the amount of mass in and between galaxies in nearby, well-observed regions of space and extrapolate to the rest of the universe. They find that there is not enough matter to slow the expansion down. Ordinary hydrogen has a nucleus comprising a single proton. Heavy hydrogen, called deuterium, has a nucleus comprising one proton and one neutron. An astronomical telescope in Earth orbit called Copernicus has measured, for the first time, the amount of deuterium between the stars. Deuterium must have been made in the Big Bang in an amount that depends on the early density of the universe. The early density of the universe is connected with the present density of the universe. The amount of deuterium found by Copernicus implies a value to the early density of the universe and suggests that the present density is insufficient to prevent the universe from expanding forever, and what is said to be the best value of the Hubble constant, which specifies how much faster more distant galaxies are receding from us than nearby ones, is consistent with this whole story. Gott and his colleagues stressed that there may be loopholes in their argument, that it may be possible to hide intergalactic matter in ways which we could not then detect. Evidence for such missing mass has now begun to emerge. The high-energy astronomical observatories AEAO are a set of satellites orbiting the Earth and scanning the universe for particles and radiation that we cannot detect down here under our thick blanket of air. Satellites of this sort have detected intense emission of X-rays from clusters of galaxies, from intergalactic spaces where there was hitherto no hint of any matter. Extremely hot gas between the galaxies would be invisible to other experimental methods, and therefore missed in the inventory of cosmic matter made by Gott and his colleagues. What is more, ground-based radio astronomical studies with the Arecibo Observatory in Puerto Rico have shown that the matter in galaxies extends far beyond the optical light from the apparent edges of galaxies. When we look at a photograph of a galaxy, we see an edge or periphery beyond which there is no apparent luminous matter. But the Arecibo radio telescope has found that the matter fades off extremely slowly, and that there is substantial dark matter in the peripheries and exteriors of galaxies which had been missed by previous surveys. The amount of missing matter required to make the universe ultimately collapse is substantial. It is 30 times the matter in standard inventories, such as Gott's. But it may be that the dark gas and dust in the galactic outskirts, and the astonishingly hot gas glowing in X-rays between the galaxies, together constitute just enough matter to close the universe, prevent an expansion forever, but condemn us to an irrevocable end in a cosmic fireball 50 billion or 100 billion years hence. The issue is still teetering. The deuterium evidence points the other way. Our inventories of mass are still far from complete. But as new observational techniques develop, we will have the capability of detecting more and more of any missing mass, and so it would seem that the pendulum is swinging toward a closed universe. It is a good idea not to make up our minds prematurely on this issue. It is probably best not to let our personal preferences influence the decision. Rather, in the long tradition of successful science, we should permit nature to reveal the truth to us. But the pace of discovery is quickening. The nature of the universe emerging from modern experimental cosmology is very different from that of the ancient Greeks who speculated on the universe and the gods. If we have avoided anthropocentrism, if we have truly and dispassionately considered all alternatives, it may be that in the next few decades we will, for the first time, rigorously determine the nature and fate of the universe. And then we shall see if God knows. But there is still a debate on how much deuterium can be made in the hot insides of stars and later spewed back into the interstellar gas. If this is substantial, the present deuterium abundance will have less impact on the density of the early universe. Chapter 25. The Amniotic Universe. It is as natural to man to die as to be born, and to a little infant, perhaps, the one is as painful as the other. Francis Bacon of Death, 1612. The most beautiful thing we can experience is the mysterious. It is the source of all true art and science. He to whom this emotion is a stranger, who can no longer wonder and stand wrapped in awe, is as good as dead. His eyes are closed. To know that what is impenetrable to us really exists, manifesting itself as the highest wisdom and the most radiant beauty which our dull facilities can comprehend only in the most primitive forms. This knowledge, this feeling, is at the center of true religiousness. In this sense, and in this sense only, I belong to the ranks of the devoutly religious men. Albert Einstein. What I believe. 1930. William Wolcott died and went to heaven. Or so it seemed. Before being wheeled to the operating table, he had been reminded that the surgical procedure would entail a certain risk. The operation was a success, but just as the anesthesia was wearing off his heart, went into fibrillation, and he died. It seemed to him that he had somehow left his body and was able to look down upon it, withered and pathetic, covered only by a sheet lying on a hard and unforgiving surface. He was only a little sad, regarded his body one last time from a great height, it seemed, and continued a kind of upward journey. While his surroundings had been suffused by a strange, permeating darkness, he realized that things were now getting brighter, looking up, you might say, and then he was being illuminated from a distance, flooded with light. He entered a kind of radiant kingdom, and there, just ahead of him, he could make out in silhouette, magnificently lit from behind, a great godlike figure whom he was now effortlessly approaching. Wolcott strained to make out his face, and then awoke. In the hospital operating room where the defibrillation machine had been rushed to him, he had been resuscitated at the last possible moment. Actually, his heart had stopped, and by some definitions of this poorly understood process, he had died. Wolcott was certain that he had died, that he had been vouchsafed a glimpse of life after death and a confirmation of Judeo-Christian theology. Similar experiences, now widely documented by physicians and others, have occurred all over the world. These parathanatic or near-death epiphanies have been experienced not only by people of conventional Western religiosity, but also by Hindus and Buddhists and skeptics. It seems plausible that many of our conventional ideas about heaven are derived from such near-death experiences, which must have been related regularly over the millennia. No news could have been more interesting or more hopeful than that of the traveler returned, the report that there is a voyage and a life after death, that there is a God who awaits us, and that upon death we feel grateful and uplifted, awed and overwhelmed. For all I know, these experiences may be just what they seem, and a vindication of the pious faith that has taken such a pummeling from science in the past few centuries. Personally, I would be delighted if there were a life after death, especially if it permitted me to continue to learn about this world and others, if it gave me a chance to discover how history turns out. But I'm also a scientist, so I think about what other explanations are possible. How could it be that people of all ages, cultures, and eschatological predispositions have the same sort of near-death experience? We know that similar experiences can be induced with fair regularity cross-culturally by psychedelic drugs. Out-of-body experiences are induced by dissociative anesthetics such as the ketamines 2-ochlorophenyl 2-methylaminocyclohexanones. The illusion of flying is induced by atropine and other belladonna alkaloids, and these molecules, obtained for example from mandrake or Jimson weed, have been used regularly by European witches and North American curanderos healers to experience in the midst of religious ecstasy, soaring and glorious flight. MDA, 2,4-methylenedioxyamphetamine, tends to induce age regression and accessing of experiences from youth and infancy which we had thought entirely forgotten. DMT, N-dimethyltryptamine, induces micropsia and macropsia, the sense of the world shrinking or expanding respectively. A little like what happens to Alice after she obeys instructions on small containers reading, "Eat me or drink me." LSD, lysergic acid diethylamide, induces a sense of union with the universe, as in the identification of Brahman with Atman in Hindu religious belief. Can it really be that the Hindu mystical experience is pre-wired into us, requiring only 200 micrograms of LSD to be made manifest? If something like ketamine is released in times of mortal danger or near death, and people returning from such an experience always provide the same account of heaven and God, then must there not be a sense in which Western as well as Eastern religions are hardwired in the neuronal architecture of our brains? It is difficult to see why evolution should have selected brains that are predisposed to such experiences, since no one seems to die or fail to reproduce from a want of mystic fervor. Might these drug-inducible experiences, as well as the near-death epiphany, be due merely to some evolutionarily neutral wiring defect in the brain which, by accident, occasionally brings forth altered perceptions of the world? That possibility, it seems to me, is extremely implausible, and perhaps no more than a desperate rationalist attempt to avoid a serious encounter with the mystical. The only alternative, so far as I can see, is that every human being, without exception, has already shared an experience like that of those travelers who return from the land of death, the sensation of flight, the emergence from darkness into light, an experience in which at least sometimes a heroic figure can be dimly perceived, bathed in radiance and glory. There's only one common experience that matches this description. It is called birth. His name is Stanislav Grof. In some pronunciations, his first and last names rhyme. He is a physician and a psychiatrist who has, for more than 20 years, employed LSD and other psychedelic drugs in psychotherapy. His work long antedates the American drug culture, having begun in Prague, Czechoslovakia, in 1956, and continuing in recent years in the slightly different cultural setting of Baltimore, Maryland. Grof probably has more continuing scientific experience on the effects of psychedelic drugs on patients than anyone else. He stresses that, whereas LSD can be used for recreational and aesthetic purposes, it can have other and more profound effects, one of which is the accurate recollection of perinatal experiences. Perinatal is a neologism for around birth, and is intended to apply not just to the time immediately after birth, but to the time before as well. It is a parallel construction to parathanatic near death. He reports a large number of patients who, after a suitable number of sessions, actually re-experience rather than merely recollect profound experiences, long gone and considered intractable to our imperfect memories from perinatal times. This is, in fact, a fairly common LSD experience, by no means limited to Grof's patients. Grof distinguishes 4 perinatal stages recovered under psychedelic therapy. Stage 1 is the blissful complacency of the child in the womb, free of all anxiety, the center of a small, dark, warm universe, a cosmos in an amniotic sac. In its intrauterine state, the fetus seems to experience something very close to the oceanic ecstasy described by Freud as a fount of the religious sensibility. The fetus is, of course, moving. Just before birth, it is probably as alert, perhaps even more alert, than just after birth. It does not seem impossible that we may occasionally and imperfectly remember this Edenic, golden age when every need for food, oxygen, warmth, and waste disposal was satisfied before it was sensed, provided automatically by a superbly designed life support system, and in dim recollection years later, describe it as being one with the universe in stage 2. The uterine contractions begin. The walls to which the amniotic sac is anchored, the foundation of the stable intrauterine environment, become traitorous. The fetus is dreadfully compressed. The universe seems to pulsate, a benign world suddenly converted into a cosmic torture chamber. The contractions may last intermittently for hours. As time goes on, they become more intense. No hope of surcease is offered. The fetus has done nothing to deserve such a fate, an innocent whose cosmos has turned upon it, administering seemingly endless agony. The severity of this experience is apparent to anyone who has seen a neonatal cranial distortion that is still evident days after birth. While I can understand a strong motivation to obliterate utterly any trace of this agony, might it not resurface under stress? Might not, Groff asks, the hazy and repressed memory of this experience prompt paranoid fantasies and explain our occasional human predilections for sadism and masochism, for an identification of assailant and victim, for that childlike zest for destruction in a world which, for all we know, may tomorrow become terrifyingly unpredictable and unreliable. Groff finds recollections in the next stage connected with images of tidal waves and earthquakes, the analogues in the physical world of the intrauterine betrayal. Stage 3 is the end of the birth process, when the child's head has penetrated the cervix and might, even if the eyes are closed, perceive a tunnel illuminated at one end and sense the brilliant radiance of the extrauterine world. The discovery of light for a creature that has lived its entire existence in darkness must be a profound and, on some level, an unforgettable experience. And there, dimly made out by the low resolution of the newborn's eyes, is some godlike figure surrounded by a halo of light, the midwife or the obstetrician or the father. At the end of a monstrous travail, the baby flies away from the uterine universe and rises toward the lights and the gods. Stage 4 is the time immediately after birth when the perinatal apnea has dissipated, when the child is blanketed or swaddled, hugged, and given nourishment. If recollected accurately, the contrast between stages 1 and 2 and 2 and 4 for an infant utterly without other experience must be very deep and striking, and the importance of stage 3 as the passage between agony and at least a tender simulacrum of the cosmic unity of stage 1 must have a powerful influence on the child's later view of the world. There is, of course, room for skepticism in Groff's account and in my expansion upon it. There are many questions to be answered. Do children born before labor by cesarean section never recall the agonizing stage 2? Under psychedelic therapy? Do they report fewer images of catastrophic earthquakes and tidal waves than those born by normal deliveries? Conversely, are children born after the particularly severe uterine contractions induced in elective labor by the hormone oxytocin more likely to acquire the psychological burdens of stage 2? If the mother is given a strong sedative, will the baby upon maturity recall a very different transition from stage 1 directly to stage 4 and never report, in a parathanatic experience, a radiant epiphany? Can neonates resolve an image at the moment of birth, or are they merely sensitive to light and darkness? Might the description in the near-death experience of a fuzzy and glowing God without hard edges be a perfect recollection of an imperfect neonatal image? Are Groff's patients selected from the widest possible range of human beings, or are these accounts restricted to an unrepresentative subset of the human community? It is easy to understand that there might be more personal objections to these ideas, a resistance perhaps similar to the kind of chauvinism that can be detected in justifications of carnivorous eating habits. The lobsters have no central nervous system. They don't mind being dropped alive into boiling water. Well, maybe. But the lobster eaters have a vested interest in this particular hypothesis on the neurophysiology of pain. In the same way, I wonder if most adults do not have a vested interest in believing that infants possess very limited powers of perception and memory, that there is no way the birth experience could have a profound and, in particular, a profoundly negative influence. If Groff is right about all this, we must ask why such recollections are possible. Why? If the perinatal experience has produced enormous unhappiness, evolution has not selected out the negative psychological consequences. There are some things that newborn infants must do. They must be good at sucking, otherwise they will die. They must, by and large, look cute because, at least in previous epochs of human history, infants who in some way seemed appealing were better taken care of. But must newborn babies see images of their environment? Must they remember the horrors of the perinatal experience? In what sense is there survival value in that? The answer might be that the pros outweigh the cons. Perhaps the loss of a universe to which we are perfectly adjusted motivates us powerfully to change the world and improve the human circumstance. Perhaps that striving, questing aspect of the human spirit would be absent if it were not for the horrors of birth. I am fascinated by the point, which I stress in my book, The Dragons of Eden, that the pain of childbirth is especially marked in human mothers because of the enormous recent growth of the brain in the last few million years. It would seem that our intelligence is the source of our unhappiness in an almost literal way, but it would also imply that our unhappiness is the source of our strength as a species. These ideas may cast some light on the origin and nature of religion. Most Western religions long for a life after death. Eastern religions for relief from an extended cycle of deaths and rebirths, but both promise a heaven or satori, an idyllic reunion of the individual and the universe, a return to stage one. Every birth is a death. The child leaves the amniotic world. But devotees of reincarnation claim that every death is a birth, a proposition that could have been triggered by parathanatic experiences in which the perinatal memory was recognized as a recollection of birth. There was a faint rap on the coffin. We opened it, and it turned out that Abdul had not died. He had awakened from a long illness which had cast its spell upon him, and he told a strange story of being born once again. Might not the Western fascination with punishment and redemption be a poignant attempt to make sense of perinatal stage 2? Is it not better to be punished for something, no matter how implausible such as original sin, than for nothing? And stage 3 looks very much like a common experience shared by all human beings, implanted into our earliest memories and occasionally retrieved in such religious epiphanies as the near-death experience. It is tempting to try to understand other puzzling religious motifs in these terms. In utero, we know virtually nothing. In stage 2, the fetus gains experience of what might very well in later life be called evil, and then is forced to leave the uterus. This is entrancingly close to eating the fruit of the tree of the knowledge of good and evil and then experiencing the expulsion from Eden. In Michelangelo's famous painting on the ceiling of the Sistine Chapel, is the finger of God an obstetrical finger? Why is baptism, especially total immersion baptism, widely considered a symbolic rebirth? Is holy water a metaphor for amniotic fluid? Is not the entire concept of baptism and the born-again experience an explicit acknowledgement of the connection between birth and mystical religiosity? If we study some of the thousands of religions on the planet Earth, we are impressed by their diversity. At least some of them seem stupefyingly harebrained. In doctrinal details, mutual agreement is rare, but many great and good men and women have stated that behind the apparent divergences is a fundamental and important unity. Beneath the doctrinal idiocies is a basic and essential truth. There are two very different approaches to a consideration of tenets of belief. On the one hand, there are the believers who are often credulous, and who accept a received religion, literally, even though it may have internal inconsistencies or be in strong variance with what we know reliably about the external world or ourselves. On the other hand, there are the stern skeptics who find the whole business a farrago of weak-minded nonsense. Some who consider themselves sober rationalists resist even considering the enormous corpus of recorded religious experience. These mystical insights must mean something. But what human beings are, by and large, intelligent and creative, good at figuring things out. If religions are fundamentally silly, Why is it that so many people believe in them? Certainly, bureaucratic religions have throughout human history allied themselves with the secular authorities, and it has frequently been to the benefit of those ruling a nation to inculcate the faith. In India, when the Brahmins wished to keep the untouchables in slavery, they proffered divine justification. The same self-serving argument was employed by whites, who actually described themselves as Christians in the antebellum American South to support the enslavement of blacks. The ancient Hebrews cited God's direction and encouragement in the random pillage and murder they sometimes visited on innocent peoples. In medieval times, the Church held out the hope of a glorious life after death to those upon whom it urged contentment with their lowly and impoverished station. These examples can be multiplied indefinitely to include virtually all the world's religions. We can understand why the oligarchy might favor religion when, as is often the case, religion justifies oppression, as Plato, a dedicated advocate of book burning, did in the Republic. But why do the oppressed so eagerly go along with these theocratic doctrines? The general acceptance of religious ideas, it seems to me, can only be because there is something in them that resonates with our own certain knowledge, something deep and wistful, something every person recognizes as central to our being, and that common thread, I propose, is birth. Religion is fundamentally mystical, the gods inscrutable, the tenets appealing but unsound because, I suggest, blurred perceptions and vague premonitions are the best that the newborn infant can manage. I think that the mystical core of the religious experience is neither literally true nor perniciously wrong-minded. It is rather a courageous, if flawed, attempt to make contact with the earliest and most profound experience of our lives. Religious doctrine is fundamentally clouded because not a single person has ever at birth had the skills of recollection and retelling necessary to deliver a coherent account of the event. All successful religions seem at their nucleus to make an unstated and perhaps even unconscious resonance with the perinatal experience. Perhaps when secular influences are subtracted, it will emerge that the most successful religions are those which perform this resonance best. Attempts at rationalistic explanations of religious belief have been resisted vigorously. Voltaire argued that if God did not exist, man would be obliged to invent him, and was reviled for the remark. Freud proposed that a paternalistic God is partly our projection as adults of our perceptions of our fathers when we were infants. He also called his book on religion The Future of an Illusion. He was not despised as much as we might imagine for these views, but perhaps only because he had already demonstrated his disreputability by introducing such scandalous notions as infantile sexuality. Why is the opposition to rational discourse and reasoned argument in religion so strong? In part, I think it is because our common perinatal experiences are real but resist accurate recollection. But another reason, I think, has to do with the fear of death. Human beings and our immediate ancestors and collateral relatives, such as the Neanderthals, are probably the first organisms on this planet to have a clear awareness of the inevitability of our own end. We will die, and we fear death. This fear is worldwide and transcultural. It probably has significant survival value. Those who wish to postpone or avoid death can improve the world, reduce its perils, make children who will live after us, and create great works by which they will be remembered. Those who propose rational and skeptical discourse on things religious are perceived as challenging the remaining widely held solution to the human fear of death, the hypothesis that the soul lives on after the body's demise. Since we feel strongly, most of us, about wishing not to die, we are made uncomfortable by those who suggest that death is the end, that the personality and the soul of each of us will not live on. But the soul hypothesis and the God hypothesis are separable. Indeed, there are some human cultures in which the one can be found without the other. In any case, we do not advance the human cause by refusing to consider ideas that make us frightened. Those who raise questions about the God hypothesis and the soul hypothesis are by no means all atheists. An atheist is someone who is certain that God does not exist, someone who has compelling evidence against the existence of God. I know of no such compelling evidence, because God can be relegated to remote times and places and to ultimate causes We would have to know a great deal more about the universe than we do now to be sure that no such God exists. To be certain of the existence of God and to be certain of the non-existence of God seem to me to be the confident extremes in a subject so riddled with doubt and uncertainty as to inspire very little confidence indeed. A wide range of intermediate positions seems admissible, and considering the enormous emotional energies with which the subject is invested, a questing, courageous, and open mind seems to be the essential tool for narrowing the range of our collective ignorance on the subject of the existence of God. When I give lectures on borderline or pseudo or folk science along the lines of chapters 5 through 8 of this book, I am sometimes asked if similar criticism should not be applied to religious doctrine. My answer is, of course, yes. Freedom of religion, one of the rocks upon which the United States was founded, is essential for free inquiry, but it does not carry with it any immunity from criticism or reinterpretation for the religions themselves. The words question and quest are cognates. Only through inquiry can we discover truth. I do not insist that these connections between religion and perinatal experience are correct or original. Many of them are at least implicit in the ideas of Stanislav Grof and the psychoanalytic school of psychiatry, particularly Otto Rank, Sandor Ferenczi, and Sigmund Freud, but they are worth thinking about. There is, of course, a great deal more to the origin of religion than these simple ideas suggest. I do not propose that theology is physiology entirely, but it would be astonishing, assuming we really can remember our perinatal experiences, if they did not affect in the deepest way our attitudes on birth and death, sex and childhood, on purpose and ethics, on causality and God and cosmology. Astronomers studying the nature and origin and fate of the universe make elaborate observations, describe the cosmos in differential equations and the tensor calculus, examine the universe from X-rays to radio waves, count the galaxies, and determine their motions and distances, and when all is done, a choice is to be made between three different views: a steady-state cosmology, blissful and quiet; an oscillating universe in which the universe expands and contracts, painfully and forever; and a Big Bang expanding universe in which the cosmos is created in a violent event, suffused with radiation. Let there be light, and then grows and cools, evolves and becomes quiescent, as we saw in the previous chapter. But these three cosmologies resemble with an awkward, almost embarrassing precision the human perinatal experiences of Groff's stages 1, 2, and 3 plus 4, respectively. It is easy for modern astronomers to make fun of the cosmologies of other cultures. For example, the Dogon idea that the universe was hatched from a cosmic egg, chapter 6. But in light of the ideas just presented, I intend to be much more circumspect in my attitudes toward folk cosmologies. Their anthropocentrism is just a little bit easier to discern than ours. Might the puzzling Babylonian and biblical references to waters above and below the firmament, which Thomas Aquinas struggled so painfully to reconcile with Aristotelian physics, be merely an amniotic metaphor? Are we incapable of constructing a cosmology that is not some mathematical encrypting of our own personal origins? Einstein's equations of general relativity admit a solution in which the universe expands, but Einstein inexplicably overlooked such a solution and opted for an absolutely static, non-evolving cosmos. Is it too much to inquire whether this oversight had perinatal rather than mathematical origins? There is a demonstrated reluctance of physicists and astronomers to accept Big Bang cosmologies in which the universe expands forever, although conventional Western theologians are more or less delighted with the prospect. Might this dispute, based almost certainly on psychological predispositions, be understood in Grofian terms? I do not know how close the analogies are between personal perinatal experiences and particular cosmological models. I suppose it is too much to hope that the originators of the steady-state hypothesis were each born by caesarean section. But the analogies are very close, and the possible connection between psychiatry and cosmology seems very real. Can it really be that every possible mode of origin and evolution of the universe corresponds to a human perinatal experience? Are we such limited creatures that we are unable to construct a cosmology that differs significantly from one of the perinatal stages? Is our ability to know the universe hopelessly ensnared and enmired in the experiences of birth and infancy? Are we doomed to recapitulate our origins in a pretense of understanding the universe? Or might the emerging observational evidence gradually force us into an accommodation with and an understanding of that vast and awesome universe in which we float, lost and brave and questing? It is customary in the world's religions to describe Earth as our mother and the sky as our father. This is true of Uranus and Gaia in Greek mythology, and also among Native Americans, Africans, Polynesians, indeed most of the peoples of the planet Earth. However, the very point of the perinatal experience is that we leave our mothers. We do it first at birth and then again when we set out into the world by ourselves. As painful as those leave-takings are, they are essential for the continuance of the human species. Might this fact have some bearing on the almost mystical appeal that spaceflight has, at least for many of us? Is it not a leaving of Mother Earth, the world of our origins, to seek our fortune among the stars? This is precisely the final visual metaphor of the film 2001, A Space Odyssey. Konstantin Tsiolkovsky was a Russian schoolmaster, almost entirely self-educated, who around the turn of the century formulated many of the theoretical steps that have since been taken in the development of rocket propulsion and spaceflight. Tsiolkovsky wrote, "The Earth is the cradle of mankind, but one does not live in the cradle forever. We are set irrevocably, I believe, on a path that will take us to the stars, unless in some monstrous capitulation to stupidity and greed, we destroy ourselves first. And out there in the depths of space, it seems very likely that sooner or later we will find other intelligent beings. Some of them will be less advanced than we. Some, probably most, will be more all the spacefaring beings, I wonder. Be creatures whose births are painful. The beings more advanced than we will have capabilities far beyond our understanding. In some very real sense, they will appear to us as godlike. There will be a great deal of growing up required of the infant human species. Perhaps our descendants in those remote times will look back on us on the long and wandering journey the human race will have taken from its dimly remembered origins on the distant planet Earth, and recollect our personal and collective histories, our romance with science and religion with clarity and understanding and love. It is interesting to wonder why psychedelic molecules exist, especially in great abundance in a variety of plants. The psychedelics are unlikely to provide any immediate benefit for the plant. The hemp plant probably does not get high from its complement of 1-delta-hydrocannabinol, but human beings cultivate hemp because the hallucinogenic properties of marijuana are widely prized. There is evidence that in some cultures, psychedelic plants are the only domesticated vegetation. It is possible that in such ethnobotany a symbiotic relationship has developed between the plants and the humans. Those plants which by accident provide desired psychedelics are preferentially cultivated. Such artificial selection can exert an extremely powerful influence on subsequent evolution in relatively short time periods, say tens of thousands of years, as is apparent by comparing many domesticated animals with their wild forebears. Recent work also makes it likely that psychedelic substances work because they are close chemical congeners of natural substances produced by the brain, which inhibit or enhance neural transmission, and which may have among their physiological functions the induction of endogenous changes in perception or mood. A fascinating description of Groff's work and the entire range of psychedelics can be found in the forthcoming book, Psychedelic Drugs, Reconsidered by Lester Grinspoon and James Bacalar, New York, Basic Books, 1979. Groff's own description of his findings can be found in Realms of the Human Unconscious by S. Groff, New York, E. P. Dutton, 1976, and The Human Encounter with Death by S. Groff and J. Halifax, New York, E. P. Dutton, 1977. Astonishingly, oxytocin turns out to be an ergot derivative that is chemically related to psychedelics such as LSD. Since it induces labor, it is at least a plausible hypothesis that some similar natural substance is employed by nature to induce uterine contractions, but this would imply some fundamental connection for the mother and perhaps for the child between birth and psychedelic drugs. Perhaps it is therefore not so implausible that much later in life, under the influence of a psychedelic drug, we recall the birth experience, the event during which we first experienced psychedelic drugs. A different but not inconsistent hypothesis on the Eden metaphor, in phylogeny rather than ontogeny, is described in The Dragons of Eden. One curious variant is given in Arthur Schnitzler's Flight into Darkness. At all the moments of death of any nature, one lives over again his past life with a rapidity inconceivable to others. This remembered life must also have a last moment, and this last moment its own last moment, and so on, and hence dying is itself eternity, and hence, in accordance with the theory of limits, one may approach death, but can never reach it. In fact, the sum of an infinite series of this sort is finite, and the argument fails for mathematical as well as other reasons. But it is a useful reminder that we are often willing to accept desperate measures to avoid a serious confrontation with the inevitability of death. Kangaroos are born when they are little more than embryos, and must then make entirely unassisted a heroic journey hand over hand from birth canal to pouch. Many fail this demanding test. Those who succeed find themselves once again in a warm, dark, and protective environment. This one equipped with teats. Would the religion of a species of intelligent marsupials invoke a stern and implacable God who severely tests marsupial-kind? Would marsupial cosmology deduce a brief interlude of radiation in a premature Big Bang followed by a second dark, and then a much more placid emergence into the universe we know?